and many researchers. Specifically, Professor Sir, I want to thank the contribution giving to statistics for the emerging students. Thank you very much, sir. So now I'm going for the presentation side. So just I want to share. Is it visible?
Of course, it's visible.
Okay. So the topic what I chosen here for today's of my talk is recent developments in reliability sampling plan and its advances in smart manufacturing. So coming to the introduction part of the statistical quality control. Statistical quality control is one of the pioneering technique in statistics, which refers to the use of statistical tools in monitoring and maintaining the quality of products and service. Quality is not a one-time achievement. It is a continuous process. We need to keep on checking and evaluating the manufacturing items. So statistical quality control is broadly divided into two areas. One is process control and product control. There are different applications that are available process control, and different techniques and methodologies are available for product control. In that, what we talk about acceptance sampling plans. So SQC involves different tools to analyze the quality of the data and the real-time problems. One of the most widely used technique in day-to-day life. So acceptance sampling plans are widely used in our daily life by knowingly, unknowingly we are using, and we are experiencing the statistical techniques in our day-to-day life. So reliability sampling plan is one of the most important method in acceptance sampling, which is used to assess the life of the product. So here we're going to check the life of the item. How this acceptance sampling plan has evolved in your real world scenario. So in our day-to-day life, we have a population, we have a sample. From population, we draw a sample. So this quality control methodologies involves the techniques of samplings, the techniques of probability, the techniques of inference, all are jointly involved and evaluated as subject, where our aim is to accept a good lot and reject a bad lot. But sometimes we will accept a bad item and reject a good item. So these two are called by the accept the bad item, what we call by consumer risk beta, and rejecting a good item, what we call by the producer risk alpha. So based on that, we are evaluating a OC curve, and we make a decision that whether we are in the normal level or tighten level or reduced level to inspect the items, which is consecutively, whether the continuous production is continuous or not. So coming to the live testing sampling plans. So in reliability sampling plan is an important method in acceptance sampling plan, which is used to test the life of the product. So in real life scenario, when you go for live testing sampling plan, we want to know the life of the item, how many hours or how many time duration the particular product will survive or not. To demonstrating high reliability of the complicated system, it's difficult to test all the items, specifically in destructive testing. When you deal with the destructive testing, it's highly difficult for testing all the items or under to be tested. So in destructive situation as concerned, and we talk about the live testing of an item, we unable to go for 100% inspection, and we cannot accept the items without inspection. So there we required an sampling inspection. So system reliability models are therefore used to assess their reliability with a specified level of statistical confidence. So we assess the specified level of confidence of the items which are traditionally done through the live testing plans. So the goal is to make the inference about the overall reliability of the entire population based on the sample and the corresponding probability values, which I already said about the sampling and the probability. So today, we are in the Industry 4.0. So Industry 4.0 is also known as the fourth industrial revolution, refers to the integration of digital technologies and advanced automation in manufacturing process or comes into the picture. But even there as the four revolution came place and the IoT technologies, that is Internet of Things, which are very, very essential in the Industry 4.0. It represents a significant shift from the traditional manufacturing method to smart factories that leverage some technologies which are inbuilt, what we call by IoT, what we call by artificial intelligence, we call it as an expert system. We deal with big data analytics, robotics, and many more added in the manufacturing environment when we come about the smart manufacturing. So here, the main concept behind is today there are large-scale industries who are involved in the what we call by smart factories, which are involved in the manufacturing of the Industry 4.0, and there are small-scale industries which are using the traditional methodology of inspection or doing process are taking place in India and globe. So Industry 4.0 aims to create a smart factories that are more efficient and it should be more flexible and responsive to customer needs. So what is the expectation of the customer and how much the production has been increased? Why the production to be increased? Because of the demand in the skilled labor and because the need of the demand what available in the market, then there is a need arises to go for the smart factories that is based on the IoT and the AI. It enables real-time monitoring and optimization of production process and predictive maintenance, which reduce downtime and enhance supply chain management. So it all plays a key role to the Industry 4.0, where we talk about the smart manufacturing technology-driven approach comes into the picture. So smart manufacturing systems, what we call by any manufacturing which are made on smart techniques, that is IoT and AI and expert systems. So smart manufacturing technology-driven approach that utilize internet-connected machineries to monitor the production process. So the production process has a system. The system contains n number of components. All the components are assembled and make into final product. So the goal of smart manufacturing is to identify the opportunities for automating operations and you use data analytics to improve the manufacturing performance. So the main objective is to improve the manufacturing performance through the interconnected automatic systems. So when it comes to the picture, the final product should be a final product. That product should be inspected before going to the market. So the National Institute of Standards and Technology defines its fully integrated collaborative manufacturing systems that responds in real time to meet changing demands and conditions in the factory, in the supply network, and its customers' needs. So here, the smart manufacturing systems, according to the NIST, states that it is a fully integrated and a real time to meet changing demands. So due to the advancements in technologies and the smart factories are coming into the real life needs arises, customer need arises. So we need to go for the smart manufacturing system. So here, a wide range of category of manufacturing that employs computer integrated manufacturing levels are developed with more flexible technical workforce training should be given and it should be checked before the process of manufacturing starts. So the smart manufacturing factories facilitates the creation of interconnected supply chains. So the smart factories plays an important roles which are where the manufacturers can seamlessly collaborate with suppliers and customers, and they can improve the coordination and intervention management, inventory management, and responsive to the market demands. So due to the demands, the smart factories can change quickly, and they make it a new product which are the customer needs and the production environment both can be make it easy, and more demanded products can be manufactured as quick as possible. So the benefits of smart manufacturing includes which increased productivity, which reduced cost, improved product quality, enhanced safety, and better sustainability. It has a potential to revolutionize traditional manufacturing process, driving innovation and competitiveness in the global marketplace. So today, the smart manufacturing, the objective is to increase the productivity and reduce the cost. Apart from that, the product it should be a high quality and reliable product. So here we introduce a concept what we call by augmented reality in smart factories. That is the key role where the quality control comes into the picture under the augmented reality, which has been making a significant progress in the last few years, which become mature enough to be used in the industrial scenario. The augmented reality systems have to be proposed to support the quality control procedures. Most of them only present information to workers, but not to track or validate the process in real time being, which is only used to guide to these smart factories, which are captured through cameras. And these cameras are to be monitored and to be checked whether there is any shift taken place in the smart factories. The objective is to provide a dynamic support and decrease the mental workload needed to complete the procedure, as well as the number of errors to be reduced. Not only that, it also used to facilitating the procedure executed by the untrained workers which are employed, or the changing scenario of the human population. The smart factories are very much useful in the manufacturing environment, where the quality control plays a key role. So design methodology in sampling plan comes under this 2x2 table, which is called by non-Bayesian and Bayesian approach, and risk-based and economically based. So the work designed here is a risk-based non-Bayesian approach, which was considered by Hammaker in 1960. And there are many authors who are already worked in the reliability levels, which are called by Epstein has contributed. It has introduced the reliability sampling plan. Hammaker, Sobel and et al., Gupta and Grohl, Gupta 1962, Dodge Roaming, Duncan, Schilling, Kantham Rosaiya, Balakrishnan, Gupta and Kundu, Su, Marshall Ulkin, myself and my students, research scholar Sivakumar, all have worked many things on the reliability development. So when we talk about the reliability concept, automatically sensoring comes into the picture. Consider a situation where we are testing n non-repairable units taken randomly from a population. We are investigating the population to determine if the failure rate is acceptable or not. The typical test scenario, we have a fixed time t to run the units to see if they survive or it fail. The data obtained are called sensor of type 1 data. So type 1 sensoring and type 2 sensoring, both sensorings are involved in reliability test. So here, whenever we involve the type 1 sensoring, during the t hours of test, we observe R failures, where R can be any number between 0 to n, the items which have been tested. The exact failure times are noted, that is called by T1, T2, etc., TR, and there are n minus R units are survived the entire t hours test without the entire test failing, process taken place. Here we have to note one point. T is fixed in advance, the time is fixed in advance, and the failure of an item is random in nature. There we introduce the probability, that is the random variable comes, since we don't know how many failures will occur until the test is run, and also that we assume the exact times of failure are recorded when there are failures occurs. So we are not sure at what time the failure may take place, which are random in nature. This type of sensor is called a right sensor data, since the time of failure is to the right larger than the t. So if it's larger than the t, then we call by the left tail sensor can be introduced. So when come to the type 2 sensoring, we observe T1, T2, etc., TR, where R is specified in advance, where the number of failures to be noted. The test ends at time T. The time T, we note that the TR, the fixed advanced failures are noted, that is T equal to TR, and N minus R units have survived. So again, we assume it is possible to observe the exact time of failure for failed units or to be noted. For example, you have an item to be tested, that is 100 units of item to be tested, and to decide you want to see at least half of them fail. You fix that 50% of the items will be failed, so R is equal to 50, but the time T is unknown until the 50th item will failure occurs. This is called sensor of type 2 data. But apart from this type 1 and type 2, there are situation arises. Sometimes exact times of failures are not known exactly. Only an interval of time in which the failure occurred is recorded. So this kind of data, what we deal with, called by readout data, or we call by interval data, that is interval sensoring, can be taught. So under these situations, we can talk about the sensoring in the reliability scenario. So here I introduce, this is a research work taken by my research scholar. We are working on that. Here we introduce a distribution called by exponential Poisson distribution. So the two-parameter exponential Poisson distribution was introduced by Su in 2007. This distribution is obtained by compounding the combination of the zero truncated Poisson distribution and exponential. According to Barreto and Souza and Silva, 2015, pointed out that the exponential Poisson distribution is a good alternative to the gamma distribution. This distribution can be used in modeling lifetime data, reliability and time intervals of successive natural data sets. To obtain the lifetime of the products is to set, we can fix the lower confidence limits towards the mean life or median life and percentile life. The life test can be tested for the corresponding proposed distribution. Here, the waiting time for the Poisson distribution is the exponential distribution with the parameter lambda. Poisson models states the number of arrivals per unit of time. Let's say the probability of k arrivals unit of time, that is P of k, is modeled by Poisson, and probability of k plus 1, that is probability of k plus 1, does exponential distribution model on the waiting time. So here we introduce the two-parameter distribution of f of x comma theta, and this distribution is exponential Poisson distribution, where we can test the median life, mean life, or your percentage life. So for the median function, the exponential distribution is given as such. So in system reliability, we introduce the concept of order statistics. The order statistics are random variable that satisfies x1 less than or equal to x2 less than or equal to xn. So here the following are some statistics that are easily defined in terms of in order statistics. So generally, the order statistics, the sample range or talks about the range of the largest minus smallest value, which is the distance between the two values, which is a measure of the dispersion in which the sample should reflect the dispersion of the population. So here, x1, x2, etc. into the order statistics of random sample of the items which are continuous population with the CDF and PDF for the corresponding probability distribution is given here. So Prashant and Seduraman has said that the order statistics from heterogeneous population with proportional hazard function for IID case and non-IID case has been introduced, where here we talk about the system reliability, where the intelligent quality control systems, we talk about the order statistics. So smart raw materials be detected by machines without necessarily having to be verified items as specified as given in the order statistics. The machine fitted with sensors will be able to differentiate between the quality of input items, that is the smart raw materials, which are in to be tested in the right manner, and to detect the defects, if possible, rework or discarded altogether. I think this was formerly done by human beings in the traditional manufacturing setup, where the machines are doing. That is what we talk about the intelligent quality control systems. Here, it combines data collection analysis and decision-making capabilities to improve products or service quality, and also reduce defects and enhance customer satisfaction. So the main point we want to know is that the data what pertaining to study. So based on the analyzed data insights, the systems can provide sort of decision support to quality control personnel or operators by recommending the corrective actions through the augmented reality techniques, what I already explained in the previous slides, which are adjustments to process parameter or initiating alerts for potential quality issues. So the benefit of the intelligent quality control system includes its improved efficiency, reduce defects and waste, enhance the quality control by better compliance with quality standards, and increased customer satisfaction, what the need for going with the IQACS systems. So whenever we talk about designing a sampling plan, the sampling plan can be involved. Either there are many sampling plans available in the literature. One can go through the literature of sampling plan. You can see the n number of sampling plans. Depends upon the situation of the study. The sampling plan varies. So here I introduce a sampling plan for the testing of the exponential Poisson distribution. So there's a significant level of test of the lot acceptance is given by 1 minus P star, where P star is the consumer's confidence level. Using this approach, the smallest positive integer n, that is n equal to r into g, the proposed plan, what we call by group sampling plan, is obtained with the assumption that the lot size is large enough to use the appropriate binomial distribution for the success and failure of an item. So L of P1 is given summation y is equal to 0 to c, RGCI is given this less than or equal to 1 minus P star, where P1 is the failure probability corresponding consumer risk underlining the corresponding distributions, which is given by the L of P. And the group sampling plan can be tested through the following steps. Step 1, fix the parameters GEP distribution of alpha and lambda and fix the termination ratio. Step 2, obtain the p values in terms of the given values of t by beta naught. And determine the smallest positive integer g by applying the conditions what we given by L of P less than or equal to 1 minus P star. Specify the appropriate consumer confidence level, that is 0.75, 0.9095, 99. The confidence levels are fixed when the acceptance numbers ranges from 0 to 4, with the assumptions that the lot size is large enough to need the binomial distribution to find the success or failure of item, which is deal with the truncated life test plan using a search procedure through the computer program. One can use MATLAB or R programming or Python programming, or one can use Excel for doing the search procedure, and you can evaluate the minimum group size for the R is equal to 2, which are given in the table. Step 4 talks about the OC values for the given incoming product called T, which are given by the L of P, where P is the cumulative distribution function in terms of the incoming quality, such that D is defined as beta by beta naught. And the step 5 talks about the ratio to be calculated, and the values are given, fixed values are given in step 5. Step 6 talks about the minimum ratio obtained from the inequality, and we obtain n equal to r into g and the acceptance number c. One can see the minimum mean ratio, which can assure the producer risk will not be more than 0.05 for the proposed plan. For the fixed specified consumers confidence level, 0.75, 0.90, etc. are exhibited. So here we are designing the acceptable reliability level, rejectable relative level, limiting relativity level for the designing of the reliability sampling plan, for the group system sampling plan, for the defective rate to detect the supplier's process of the acceptable levels and rejectable levels, and limiting reliability levels are to be derived by a suitable OC curve, which comes in the next slides. Here, we can provide an optimal sample size to save the cost and time of the experiment. The quality statistics follows the median lifetime. So here we can test the mean life, a median life, a percentile life. I talk about the median lifetime here. According to the PAN parameter is developed the minimum number of groups for the specified consumers' confidence determined with the suitable OC curve for the exponential Poisson distributions can be given. Here, the PAN parameters can be obtained by the two inequalities should be satisfied with L of P1 is greater than or equal to 1 minus alpha and L of P2 is less than beta. So here we can able to design the PAN parameters what we decided about the previous slides. ARL, LRL, and IRL can be defined with the corresponding sample size can be determined, and the producer risk based on the corresponding OC curve can be elaborated. This is the OC curve for the proposed FAN for the fraction defectives, fraction defective of items with the corresponding probability of acceptance. The fraction defectives of items were given. Suppose that the lifetime of products follows the exponential Poisson distribution. It is desired to design the group acceptance sampling plan to test the actual mean lifetime, which is greater than 1,000 hours, with the test terminated at 800 hours, and 2 items on each tester is allowed for the failure with 2, and the lead ratio is given as 0.8, and when C is equal to 2, we can obtain P and L of P like this, and the corresponding OC curves are given here. Here I give an example for the real life example. Today's world is completely surrounded by modern technologies and advanced manufacturing, smart manufacturing. Without technology advancements, no one can survive in the current situations. So that is a scenario what we are having. Today, the drones are currently widely used for many purposes. Even in agriculture, we are utilizing for fertilizer, distribution of fertilizer, like that. Many examples we can say for the drones, which are in demand in the technological products with their use of growing in the exponential rate. So a drone, also known as an unnamed aerial vehicle, is an aircraft that operates with a human pilot on board. Drones can remotely controlled by human operators or autonomously operated using pre-programmed flights planned and abroad based on the sensors. Here, drones have a wide range of application across various industries, including aerial photography, videography, surveying, mapping, agriculture, infrastructure, inspection, search, rescue operations, environmental monitoring, package delivery, and military operations, etc., etc. In all these areas where drones are widely used. So the exponential process is used to describe the increase in the drone production, and Poisson process is used to describe the probability of manufacturing defects. Therefore, it is ensured that this production process is carried out using an exponential Poisson process. Coming to the conclusion, in this study, we have proposed a group of some sampling plan for the median life test when the lifetime of the product follows an exponential Poisson distribution. Since the distribution has shown be a useful model in the area of smart manufacturing and ability studies, to ensure that the life testing of product exceeds a specified standard, acceptance sampling plan based on mean life can be used. In such case, sampling plan has been developed based on mean life or median lifetime. The proposed distribution when the life test is truncated at a predetermined time to optimize the plan parameter, we can develop a sampling plan. So these are the few references, and that comes to the end of my talk. So if there is any questions, I'm very happy to share with the audience. So this is the ideology what I gave for the the present research scholars who are interested to work on it can talk about this kind of applications in your real world scenario. So now it is open for any questions or discussions from the listeners. Any questions? Any research scholars are there? Okay, if there is no more question, we move to the next speaker. So the next speaker is Dr. S. Jayalakshmi. She working as an assistant professor in Department of Statistics, Bardya University. She have more than 10 years of teaching and research experience, and she has guided more than 3 candidates, and presently she guiding 4 candidates for research, and also she guided many MPhil scholars under her research in quality control research area. She also interested in doing research in biostatistics, and she published many research articles in leading national and international journals. So now I request Dr. S. Jayalakshmi to share his research papers and to discuss her research article for 25 minutes and 5 minutes for discussion. Now I hand over the session to Dr. S. Jayalakshmi. Jayalakshmi, are you there? Jayalakshmi? We also have other 2 more speakers. One is Dr. Alagiri Sami from Periyar University. Professor Alagiri Sami, are you there?
Yes, sir. Yes, I'm here.
Shall we start now?
Yes.
Before that, I will confirm once again with Jayalakshmi. If she is
Okay,
not
okay.
responding, we can proceed with Alagiri Sami.
Okay.
Dr. Jayalakshmi? There is no response from Dr. Jayalakshmi. So we can move to the next resource person. The next resource person is Dr. Alagiri Sami. He is an assistant professor, the Department of Statistics, Periyar University, Salem. Sir has a vast experience in teaching and research, more than 15 years of teaching and research experience in colleges and universities. And Sir is guiding more than 5 research students under his guideship. And he published many research articles in leading national and international journals. And Sir is one of the important person in Periyar University, Department of Statistics, and a guru researcher. So Sir is accepted our invitation and came over here to present his research topics in this forum.
Hello.
So I request Dr. Alagiri Sami.
Hello, sir. Hello, sir.
Madam?
Sir, it's audible, sir?
Yes, madam.
Yes, sir.
Madam, kindly wait for a few minutes. I think Alagiri Sami is presenting now.
Okay, sir. Okay, sir. Okay, sir. Thank you, sir.
Okay.
Now,
Alagiri Sami, you can share your screen. Alagiri Sami, are you audible? So, like you can start share your screen. Dr. Alagirisamy. Alagirisamy is audible.
Hello.
It's audible.
It's audible.
Yes, sir, your slide is not visible, sir.
Okay, sir. Wait a minute.
Sir, have you opened the PowerPoint?
Is it visible? Where is it, sir?
Sir, kindly open the PPT.
Yes, sir. It's open.
Select the PPT. Select the PPT to your visible. Don't display your screen. So PPT select பண்ணுங்க சார். உங்களுக்கு அது தெரியணும்.
Sir, it's visible, sir.
For us it is not visible, sir.
Sir, Kavirashu sir.
Yes.
Sir, if there is some problem in Alagirisamy,
Okay.
so please send the presentation slide into the organizing committee, sir. They will
Okay.
presenting, sir.
Yeah, I got it. I can ask him to send to you. Okay.
Okay, I will send you.
Kindly share your email ID in the.
Nigil Chandra is here. Nigil Chandra.
Satish Kumar, I will send to Satish Kumar, sir.
Okay. Nigil Chandra.
You already sent Alagirisamy, sir.
Nigil Chandra is present
I
here.
will send you.
Yeah.
Nigil Chandra, Alagirisamy, Professor Alagirisamy send his presentation to you.
Okay.
Okay.
Yes. Okay.
Okay.
Have you sent to Satish sir? Alagirisamy, sir?
Yes, sir. I have sent to Satish Kumar, sir.
You already sent.
No, just now I sent it.
Okay. They will share.
Nigil Chandra, are you received the mail, Nigil Chandra? Nigil Chandra.
Kavir sir.
I'll check.
Okay. You please share it.
Alagiri sir,
Yes, hello.
have you sent the file, sir?
I have sent the file.
Okay.
Kavirs sir.
Yes, madam. Solling, madam.
Sir, it's audible, sir.
Yes, audible, madam.
Okay, sir.
So you want? I think I called you, ma'am. I think you were left the meeting.
Yes, sir. Yes, sir. Yes,
There is
sir.
some internet connection problem is there. I think so.
Yes, sir. Yes, sir.
So next you can present, ma'am.
Yes, sir.
Okay. May I present my paper? Kavirs sir?
Yes, it's audible, sir.
Okay, okay, sir. So good
The
morning
screen
to
is
all.
not visible, sir.
Hello.
I think the screen is not visible.
The screen is visible, sir.
Visible, sir. Screen is visible.
Okay. For me, it's not visible. I don't know why.
So good morning to all. Is audible? My voice is audible.
It's audible, doctor.
Good morning to all. And all present here. I am Alagiri Swami, working as assistant professor in the Department of Statistics, Periyar University, Salem. I'm going to present my research topic, comparison of Arimo model and the Facebook Prokifit model. And also, I would like to thank the organizing committee to acknowledgement present my paper in this conference. Especially, I would like to thank Satish Kumar sir. Thank you, Satish Kumar sir. So now I'm going to present my research topic. So just I have to take two regression model, that is called Arima model and Facebook Prokifit model. This model actually uses predictive analytics techniques. It's a common research topic nowadays. Recent development in this area have allowed organization to obtain meaningful information and make critical decision based on forecasting results. Especially in forecasting in modern technology, we use only for Arima model, and lot of forecasting models are available. Just I have to choose only for two model, Arima and Facebook Prokifit model. So Arima model have two different time series models are contained. One is called Arima and one is Sarima. There are two models in Arima models. So this study aims to investigate the performance of comparison of Prokifit and Arima models. So just I have to use root mean square error used to evaluate the performance of proposed model. The proposed model is to found outperform for both Prokifit standalone and Arima models. Next slide, please. The main objective of my study is, my main aim of my study is to compare the Prokifit and Arima model. This is my main aim of the research. The main objective of my research is, the main objective of the study is to build different time series models, especially for Arima model and Prokifit model, inspect their results models will use ARIMA model and Facebook Prokifit models. This is my main objective of the study. Next, please. Next slide. Methodology. I have used the methodology. The data collected from data.government website. The sampling techniques are purposive sampling. So this is a sampling technique. So I have used two models, ARIMA model and Facebook Prokifit model. ARIMA stands for, actually ARIMA is a model which is used for predicting future trends on time series data. It is a model that forms a regression analysis. So in this ARIMA model, AR stands for auto-regression. So auto-regression means model that shows a changing variable that regress on its own lagged or period values. That is called AR. So in this, I means I is nothing but integrated. So integrated means differencing of raw observation to allow for the time series to become a stationary. Sometimes the data may be non-stationary. If it is non-stationary, just we converted into stationary one. So if it is a data is non-stationary, just we apply ADF test, augmented decupular test. So many tests are available if data is non-stationary. If it is stationary, then only we can apply for time series model. Next, moving average. In ARIMA, MA stands for moving average. MA means dependency between observation and residual error from a moving average model. Next slide, please. Prokifit model is totally the different model. Actually, this is the latest forecasting technique. So the Box Benkinson actually developed ARIMA model in 1980. So the Prokifit model, the 20th century developed the Prokifit model, Facebook Prokifit model. The Prokifit means that the Prokifit is a procedure for forecasting time series data based on additive model. So in time series, there are two models, additive and multiplicative model. Especially the Prokifit model is used for additive one. So the additive model where non-linear trends fit with yearly. So why we go to additive model means the additive model we can easily apply for non-linear trends. Non-linear trends means suppose the data sometimes may be non-linear. So non-linear data. So with yearly, weekly and daily seasonality plus holiday effects. Holiday effects mean suppose the data are not available some holiday times. So that's why especially used this model, Prokifit model. It works best with the time series that have strong seasonal effects and several seasons of historical data. So Prokifit is robust to missing data and shift in the trend, and it typically handles outliers well. So that's why the Prokifit model, just I have to compare the Prokifit model to ARIMA model. Next slides, please. The ARIMA model have one more type of ARIMA model, which is seasonal. Suppose just you collect the data may be seasonal, sometimes weekly data or monthly data. It may be seasonal wise, just you apply ARIMA model. So ARIMA model is one of the ARIMA. So the seasonal ARIMA is an extension of ARIMA that explicitly support univariate time series data with a seasonal component. It has three new hyperparameters, especially autoregression, AR, and differentiating I and moving average MA for the seasonal component of the series, as well as additional parameter of the period of seasonality. Especially the seasonal ARIMA we can apply only for if a seasonality exists to a data, you can apply for seasonal ARIMA model. Then next slides. There are four seasonal elements that are not part of in ARIMA that must be configured. They are in ARIMA model we cannot compare the PDQ, but in seasonal model we have to compare PDQ. The P means seasonal autoregressive order, D means seasonal difference, and Q means seasonal moving average order. So M means the number of time steps for single seasonal period is called small m. Next slides, please. So this is actually I have to analyze the data. Just I have to take a data from government data.in. The secondary data is collected. So Tamil Nadu rainfall data from 2000 to 2007. This is a monthly data. Just I have to put in Python, machine learning. Just I have to develop modeling, coding for Python package for Sarima and Prokifit and Arima model. This is a coding for Arima model and Sarima model. Next slides, please. Next slides, please. These are the output of the Python packages. The model. Next slides, please. So the data, the Tamil Nadu rainfall data, just I have to calculate the seasonal effects of the model, seasonal decompose. If you collect any type of data, first decompose the model, then only we can find the correct model. That's why we use the decompose the data. Next one. This is a sequence plot. Next one. This is a auto arima function. The auto arima function automatically in machine language calculate the parameters of AIC and BIC parameters. AIC and BIC is a Bayesian criterion, and the augmented criterion is calculated the particular parameter, particular model parameters. So next one, please. Next slides, please. These are the outputs of my model. Then just I have to compare, just I have to forecast Tamil Nadu rainfall data. Just we have to compare the Arima model. This is a sequence plot for the forecasting data 2007 to 2007 January to December data. This is an example only. Based on this example, we can predict the future values. Next slides, please. Next two slides, please. So please wait before the previous slides, please. So just I have to compare RMSE value for the Arima model and Sarima model and Prokifit model. So RMSE is nothing but it is a parameter to evaluate the model. Root means square. So in this Arima model, 72.24. Next two slides, please. This is a Prokifit model coding. Next slides. These are the prediction. Next one. These are the prediction, forecasting the future values using Prokifit model. Next slides. These are the output of the Prokifit model. The Prokifit model root mean square error is 56. Next one, please. These are the sequence are just I have to compare the Arima and Sarima and also Prokifit model. Next slides, please. These are the two predictions, Arima prediction and Prokifit prediction. Next slides, please. So, based on the research, the conclusion was to get the basic understanding of time series forecasting models such as Arima, seasonal Arima, and Prokifit. From the experiment, we can see that Sarimax model forecasting has a better accuracy than Prokifit model forecasting. So the best model is Sarimax model to compare Prokifit, Facebook Prokifit model. The RMSE for the Sarimax model was around 8%, while Prokifit model had RMSE of 11.4%. So that's why the Sarimax model is the best model to compare Prokifit Facebook model. Thank you. One and all. If you have any doubt in this model, please ask. Thank you, sir.
Thank you, Dr. Alagiri, for your presentation. So now the forum is open for one or two questions to be get clarified.
Good morning.
Good morning, sir.
Good morning, sir.
Can you specify the profit model? What is the specification?
The specification is just to sometimes maybe the data may be seasonal components. Suppose our data may be occur time seasonal components, sir.
No, there is a specific model specification. Can you say what it is? Because I have not seen that. That is why I am asking.
So model specification, just we have to compare the
And proceed your talk.
Now my screen is visible, sir.
yeah.
Madam, is visible now.
Yes, sir. Yes, sir.
If possible, make it big screen.
Sir,
Full screen. If
yes,
possible, if you make it full screen, is more better for visibility.
no, sir.
Slideshow mode. You can put it in slideshow mode.
What, sir? Satish, sir?
Yeah, you can put it in slideshow mode. Slideshow.
Yeah, slide share.
Yeah.
Kindly make it slide share.
Yeah, slide.
Open the file, ma'am.
Yes, sir. Yes, sir.
We will guide us. We'll guide you.
Share it once again. Yeah.
So now it's okay.
Yes, ma'am. You go to.
It is okay.
Okay.
Okay, sir.
Yes.
Now
Sir.
you can click
Okay,
on the
sir.
second. Sorry. Okay.
Yes, sir. Very good morning to all present here. First of all, I would like to thank to organizing committee for giving this wonderful opportunity to present my article in the 8th International Webinar on Recent Trend in Statistical Theory and Application 2023. Now I am going to talk about reliability acceptance sampling plan based on truncated light test using modified Keyes exponential distribution. Now we are going to see the content in the presentation. First of all, introduction, acceptance sampling plan, reliability acceptance sampling plan, truncated light test, review of literature, modified Keyes exponential distribution, operating procedure for single and double sampling plan, numerical illustration, conclusion. The basic concepts of the quality control. Quality control is the system in manufacturing of the maintaining standard. Dr. Walter Schuchard, a researcher of Bell Telephone Laboratories, is called the father of quality control analysis. He developed the concept of statistical quality control. It refers to the use of statistical methods in the monitoring and maintaining of the quality of the product and services. It is a term used to describe the set of statistical techniques employed by the quality professionals for evaluating the quality. Here's statistical quality control. In the global world, statistical quality control is a great important. This is considered necessary to ascertain the visible operating characteristics value of the proposed plan. Inspection of the various manufacturing product is considered essential for ensuring the trust of the item with regards to its lifetime. There are two main fields in statistical quality control: product control, that is acceptance sampling, and the process control. This paper is considered with a product control, which aims in assuring a certain prescribed quality level of the skipped or accepted lot. Generally, 100% inspection is neither possible nor economically sensible. Therefore, product control is preferred by means of statistical procedure. Usually, in acceptance sampling, there are only two decisions admitted with respect to the lot in questions, which are called acceptance and rejections. with different models of performance, of course. The statistical procedure cannot be as good as 100% inspection, and it should improve with increasing the sample size in the limiting case that each item of the population is sampled. The statistical procedure should always lead to the same decision as taken in the case of full information. Clearly, statistical procedure being not able to guarantee particularly that lost demand should be applied only in the extreme case that there is a no better procedure available. The process and product control are two key concepts of statistical quality control that are used in monitor and improve the quality of the product or service. The goal of the process control is to detect and correct variations in the process so that the process remains in statistical control and produces product or service that meet the established quality criteria. The goal of the product control is to detect and correct defects or non-conforming in the product so that the product meet the established quality standards and consumers. Then we go for the acceptance sampling plan. The main purpose of the acceptance sampling plan is to ensure that the lifetime of the product is according to the desired standard of the consumer or not. In case the life test shows that the mean life of the product is above the desired standard, the submitted lot is accepted. Otherwise, the same is required. Acceptance sampling is a statistical measure used in quality control. It allows a company to determine the quality of the batch of product by selecting the specified number for testing. Then acceptance sampling is a statistical technique used to inspect the quality of batch of product. It involves comparing the number of defective pieces and the predefined acceptance number to accept or reject the batch. The advantage of acceptance sampling plan is that it provides a strict inspection of the assembled product before it can be sent for the consumer's use according to the desired standard. When the confident limit of the mean life is established, it becomes the easier decision as to whether the submitted lot may be accepted or rejected. And therefore, the important note that whatever the type of sampling plans may be produced, the decision is made concerning the disposition of the lot based on the information obtained from this sample. In general, the three approaches could be considered when receiving a lot. No inspection, then 100% of inspection, then sampling inspection. Sampling inspection, various types are there, like a single sampling plan, double sampling plan, multiple sampling plan, etc. For single sampling plan, here single sampling plan, first a single sampling plan. A single sampling plan is scheme in which decision to accept or reject an inspection lot is based on the inspection of the single sample. First, to draw a sample of size small n from the lot of sample size capital N received from the suppliers or final assembly. Then inspect each and every unit of the sample and count the number of defective units D. In D less than or equal to C, then accept a lot. D greater than or equal to C, then reject the lot. Here double sampling plan. Here double sampling plan is the aim of double sampling plan is to reduce the average sample size and still have the same producer and consumer risk point. The double sampling plan consists of N1, N2 is sample size, and C1, C2 is the acceptance number, and D1, D2 is the rejection number. Then we go for the reliability concept. Then reliability is defined as the probability that a product, system, or service will perform its intent function inadequately for a specified period of time or will operate in a defined environment without failure. The most important components of this definition must be clearly understood to fully know how reliability in the product or service is established. probability, the likelihood of mission success, intended functions, for example, to light, cut, rotate, or heat, then satisfactory perform according to the specification with an acceptable degrees of compliance. Specific period of time, minutes, days, month, or number of cycles. Then reliability theory is one of the prominent research area of the statistical science, which play key role in assessing the failure times and a prediction of life of human facilities such as modern electronic computers, laptop, smartphone, air conditioner, television, etc. The reliable equipment treated as a dependable one. When a statement is made to the effect that a particular equipment is reliable, an acceptance sampling plan under which sampling inspection is performed by conducting live test upon the sampled product may be termed as reliability sampling plans. The lifetime of the product is the main characteristic of interest sampling plan designed for testing the acceptability of product. Then we go for the truncated live test. The technique behind the acceptance sampling plan first start by describing the minimum sample size required to maintain the specific mean life when the life test time is stopped at the predetermined time. These particular kind of experiment are called truncated live test. So truncated live test used to save the time and cost of the inspection. The following is the sampling strategy based on the truncated live test. The unit are descriptable or degraded after the live test. Several distributions reasonably well model the product life. It is most likely taking into account the consumer risk, benefits, and the small number of units needed to test. As a result, we employed the distribution with the minimum sample size. Review of literature for reliability concept and acceptance sampling plan. For Epstein, 1954 has developed the truncated live test in exponential case. Then Cameron, 1952 has constructed and computing the operating characteristics of single sampling plan. Then Gupta and Kroll had developed the gamma distribution in acceptance sampling plan based on truncated live test. Gautam and Rosaya had developed the acceptance sampling plan based on truncated live test using logistic distribution. Then Gautam et al. Had developed the acceptance sampling plan based on truncated live test log logistic model. Then Pratibha Veerakumari, Kavyadas, and myself also developed a reliability concept. Then double sampling plan. The double sampling plan, Duncan, 1986, had described the concept of double sampling plan in book of Quality Control and Industrial Statistics. Then Aslam and Jund has developed the double sampling plan for generalized log logistic distribution with a shape parameter. And Rowe has developed the double sampling plan based on truncated live test for Marshall-Auckland extended exponential distribution. Then Ramasamy and Anburajan. Then Tirupati, Shaha, Satish Kumar sir also developed the reliability concept in double sampling plan. Then here using modified keys exponential distribution. Here modified keys family distribution is a special case of keys distribution. An extended model has considered an exponential distribution as baseline for the modified keys family and generate two parameter modified keys exponential distribution which has several desirable properties. The modified keys exponential distribution has a very flexible probability density function. It can be positive skewed, negative skewed, and symmetric, and can allow for the greater flexibility of the trials. It is capable of modeling monotonically decreasing, increasing, and bathtub hazard rate. Moreover, it has the closed from cumulative density function and very easy to handle, which makes the distribution is candidate to use in different field. Then modified Keyes exponential distribution, cumulative distribution function, then here f of x that is equal to 1 minus of e power minus e power lambda x minus 1, then a. The probability density function of modified Keyes exponential distribution is f of x that is equal to a into lambda e power lambda ax 1 minus e power minus lambda x whole to the power of a minus 1 e power minus e power lambda x minus 1 a, where a is a shape parameter and lambda is the scale parameter. The quantile function is given below. Then percentile estimator. Then Q, the percentile function of the any distribution is given below. Then probability of t less than or equal to tq, that is equal to q. Then tq calculating for this equation 1 divided by lambda, then logarithm of 1 plus, then minus logarithm of 1 minus p whole to the power 1 minus 1 divided by a. Then replacing the scale parameter lambda using this equation, then we get the cumulative density function for exponentiated generalized Richard distribution is f of x that is equal to 1 minus e power lambda q s delta q minus 1 into a. Then we go for the single sampling plan procedure under truncated live test. The sampling plan can be implemented as follows. First, we select the set of small n product randomly from the submitted lot of size capital N. Then conduct the live test to the selected item considered based on time t as the test terminated time. Observe the number of failed item d. Terminate the live test if either at time t or d greater than c before reaching the time t, whichever is earlier. Accept the lot if d less than or equal to c at the time t. Reject the lot if greater than c, either at the time t or earlier. Then we calculate for minimum sample size. Here minimum sample size binomial distribution can be applied to large lot in the situation. Here sample size n, acceptance number c, then specified time t divided by tq. Define our methodological approach of the sampling plan. Using these equations, sum of I equal to 0 to c, ncx p power I 1 minus p power n minus I less than or equal to 1 minus p star, where p equal to f of function of t then delta is the probability failure during the time t given the specified percentile of the lifetime t q naught and dependent on delta naught that is equal to t by tq naught. Operating characteristics function. The operating characteristic function for the sampling plan n comma c comma t by tq is the probability acceptance a lot. It is given by this equation. Then probability function for t by tq, then 1 divided by dq. Here dq that is equal to tq by tq naught. Then we go for producer risk ratio. The producer risk alpha is the probability of rejecting a lot when tq greater than tq naught. The given producer risk alpha, p as a function of dq should be simulated satisfying the condition given by the Cameron 1952 as this equation where alpha equal to 0.05. Then we go for a double sampling plan procedure under truncated live test. Then the operating procedure of the proposed plan characterized by the acceptance double sampling plan is N1 C1 for N1 N2 for sample size, C1, C2 for acceptance number, then specified time T divided by TQ as follows. The first step is select the first random sample of size small n from the lot and put them on the test for the time T0 and the counter number of defective D1 and compare it with the acceptance number C1. Then step 2, if D1 less than or equal to C1, accept the lot. If D1 greater than or equal to C2, reject the lot. If D1 greater than C2 is obtained before the time T0, terminate the test and reject the lot. Then step 4, C1 less than or equal to D1 less than or equal to C2, take a second sample of size N2 from the remaining lot and put them on the test for time T0 and the counter number of non-conformities D2. Then minimum sample size. The lot sizes are efficiently large. Success and failure occurs often. The following as binomial distribution. This problem focuses on finding the minimum sample size of N1 and N2 using known values of P star, the acceptance number C1 and C2 and the specified time TQ. Here using this equation L of P. Then operating characteristic function. The operating characteristics curve between the probability of acceptance and the specified lifetime for the given acceptance number and the sample size. The probability of acceptance is given below for double sampling plan. Then producer risk ratio for double sampling plan. Considering the producer risk is the probability of rejecting the lot when TQ greater than TQ naught, we will ensure the producer risk less than or equal to 5% using this equation. Then numerical illustration for both single and double sampling plan. Assume that the air cooler is subjected to the lifetime examination. The inspector is selecting and modified Keyes exponential distribution for the specific inspection lifetime product. The modified Keyes exponential distribution has three shape parameters that are used to fix the air cooler machine at A equal to 3. So first numerical illustration for single sampling plan. The investigator wants to run the experiment for 2500 hours, but the tester to true percentile lifetime T equal to 1200 hours. C equal to 2, so acceptance number 2, then alpha equal to 5%, beta equal to 0.10, then psi equal to 0.3881. Is computed from the equation, get under the percentile estimator, the minimum sample size is small n equal to 9. The probability of acceptance is given by n, c, t by tq naught. Here 25th percentile using, so 0.25. So that is equal to n is 9, then acceptance number is 2, then specified time is 1.7. With P star equal to 0.95 under the modified Keyes exponential distribution. It reveals that if the true 25th percentile is almost equal to the essential 25th percentile T by TQ naught, here 0.25, that is equal to 1.7. The producer risk nearly 0.9144. The producer risk is almost nearly equal to 0. Whenever the actual 25th percentile is greater than or equal to 1.85 times the specified 25th percentile. Here dq, that is equal to tq divided by tq naught, that is equal to dq. So calculating for 1.1, 1.65, 1.9, 2.8, 3, 4, 5. Then corresponding the probability of acceptance L of P, that is equal to 0.0856, 0.8872, 0.9661, 0.991, 0.9996, then 0.999, almost 0.9999. Then the operating characteristics curve, the specified time corresponding probability of acceptance is given below for single sampling plan. Then numerical illustration for double sampling plan. The investigator wants to run the experiment for the same 2500 hours, but the tested to true percentile lifetime t equal to 1200 hours. Here C1 equal to 0. For double scientific C1 and C2 is the acceptance number. So C1 equal to 0, then C2 equal to 2, then alpha equal to 0.05, then beta equal to 0.10, then psi equal to 0.3881 is computed from the equation get under the percentile estimator. Minimum sample size is n1 equal to 5 and n2 equal to 8. The inspector conducting the lifetime test within the time limit 1200 hours. Inspector was taken a decision or as follows. First one, if D1 less than or equal to 1, then accept the lot. If D1 less than or equal to 2, then reject the lot. If D1 equal to 1, then go to randomly select the second sample, N2. If D2 less than or equal to 1, then accept the lot, and if D2 greater than or equal to 2, reject the lot. The probability of acceptance is given by the sample size N1 and N2, then acceptance number C1 and C2, then specified time using 25th percentile, then T by TQ naught. So N1 is 5, N2 is 8, then acceptance number C1 equal to 0, then C2 equal to 2, then DQ equal to 1.7 with the probability of acceptance 0.95 under the modified Keyes exponential distribution. Here using for operating characteristics function for DQ and corresponding probability of acceptance. The specified lifetime corresponding probability of acceptance. It remains that if the actual lifetime of 25th percentile near approximately predetermined lifetime 25th percentile T 0.25 divided by TQ naught 0.25, that is equal to 1.7. The producer risk near 0.9429. So the producer risk can be approximately to be 0. The true life 25th percentile is greater than or equal to 1.9 times the specified 25th percentile. Then we go for the conclusion. In this paper mainly focusing the producer risk and also meet the consumer expectations. Truncated life test helps to minimize the inspection time and cost. In this paper provides the minimum sample size required to decide whether to accept or reject a lot based on its specified 25th percentile follow modified Keyes exponential distribution. Assuming that the minimum sample size, we can use the tables to calculate the acceptance number C for accepting or rejecting the lot for the given probability of acceptance. For single sampling plan, the probability of acceptance is characterized by NC and specified time T by TQ. Here 9 for sample size, 2 for acceptance number, then specified time for 1.7 with probability of acceptance 0.95 under modified Keyes exponential distribution. In double sampling plan, the probability of acceptance is given N1, N2 for sample size, C1, C2 for acceptance number, T by TQ naught. Here 5,8, then acceptance 0,2, then specified time 1.7 with the probability of 0.95 under modified Keyes exponential distribution. The table's values are used for suitable applications of the product. The single and double sampling plan are flexible. So it is strongly recommended that the industrial can use the proposed plan for the testing of electronic product. Thank you. These are my references. Sir?
Yes, madam. Thank you very much, Dr. Jayalakshmi. Now the forum is open for 1 or 2 questions. Those who are interested can
Right. See, you made a claim that this Keyes exponential distribution
Yes, sir.
can be used for negative skewed and positive skewed normal symmetric distributions. Which is the parameter that is controlling it?
Sir?
Which is the parameter that tells about it?
So lambda and A.
My question, I repeat it.
Yes, sir.
It is the Keyes exponential distribution. You claimed that it accounts for both negative skew and positive skew as well as symmetric distributions. Which is the parameter that accounts for that? It's a curiosity that I am asking, that's all.
Okay, sir. Okay, sir. So the modified Keyes exponential distribution using two parameters, sir, A and lambda. A for shape parameter, lambda for scale parameter.
Yes, madam, you're talking about positive and negative, right?
Yes,
That
sir.
is what sir is asking. In positive and negative, how this skewed distribution can be connected. Suppose in case of symmetric distribution is there, how it may be connected? That is what sir is asking.
So generally, Keyes exponential distribution is using for positive, negative, symmetric, sir. Then we converted modified Keyes distribution.
Okay, right. It's all right. Also, you made a claim that the tails are also can be of varying types. Why
Yes,
I am
sir.
asking is,
Yes, sir.
I want to compare it with certain other distributions. That's all.
Okay. Okay, sir. Okay, sir.
Okay, it's okay, right, fine. I will
Thank
work
you,
out
sir.
for myself.
Okay, sir. Thank you, sir. Okay, if there is no more question, so we thank the speaker, Dr. Jayalakshmi, for the nice
Thank you.
presentation
Thank
of
you, sir.
the reliability acceptance sampling plan and the modified Keyes exponential distribution. So on behalf of the organizer, I thank Dr. Jayalakshmi for your valuable time with us. Thank you.
Thank you, sir. Thank you, sir.
So next we have the last speaker of this session, Dr. Parimla.
Yes, sir. I'm online.
Okay. So now we have the next speaker, Dr. Parimla. She is working as assistant professor in a Hindu college, Chennai, and she has more than 10 years of teaching experience, and she has a good exposure in statistical theory and concepts. So now she's going to present her research work, the latest research work, what we are going to share with us. So on behalf of the organizing committee, I welcome Parimla and to share your screen and present your research contribution. I'm handing over to Parimla.
Yes. Yes, sir. I'm online. Yes. I welcome. Very good morning to one and all present here. Am I audible, sir?
It's audible, ma. Kindly share your screen.
Yes. Is it visible, the screen?
No, not yet.
How is it visible?
No, not visible for me. You go
Just
to
a
the,
minute.
no, just now it's presenting. Yeah,
Yes.
yeah. Now it's visible. Can you make it a bigger screen?
Yes.
Yeah.
Is it now okay?
Now, okay, you can proceed.
Yes. Very good morning to one and all present here. Myself, Parimla, from DRBCC Hindu College. I welcome one and all for this presentation. For the 8th International Webinar on Recent Trends in Statistical Theory and Applications. I am presenting under the guidance of Dr. V. Kaviyar, sir. This insight, this conference promises to be an exciting event with an experts renowned around the world presenting their latest research in the field of statistical theory and applications. We gather here today and we are reminded of the impact of statistical analysis, which is very incredible to our world. That is, we have started from predicting elections to tracking disease outbreak, and statistical methods have been an indispensable tool for making decisions in various fields. We would like to explore the statistical theory and applications and how examine these developments have driven progress across industries. My topic is today designing and planning of quick switching, Bayesian repetitive group sampling system and a gamma zip distribution using minimum angle method. These are the various review of literature which I've referenced. Dodge in the year 1967 and Rombosky, Mox, Roth, Soundarajan, Armanayagam in the year 1990, Govindrajan in 1991, Govindrajan Kurlaman in the year 1992, Suresh and Jayalakshmi, Suresh and Kaviyarasu, respectively in the years 2006 and 2012, Sheng and Fan in the year 1992, Lee and 1997, and Suresh and Lata. Lee's contribution is concept of predictive distribution for sampling information through Bayesian methodology. There are other contributions. Dodge, they have developed sampling inspection tables for lot by lot inspection for attributes. Cameron, they have given tables for single sampling plan of various values of producers and consumers risk and a Poisson method. Halt, changes in the optimal sampling plan, so that if one knows prior distribution, the results are approximated to sampling plan. Again, on gamma zip, these are the various Lambert in the year 1992, Naya, Yang, Sim and Lim, Maklan, P, Yuma and Ramya, Srinivas Rao, Rao and Aslam, Kaviyarasan and Sivakumar in various years from 1992 to 2019, they have contributed to gamma zip. And repetitive group sampling contributions are from Sherman in the year 1965, Soundarajan and Ramya in the year 1984, Balamurli and in the year 2005, Suresh and Kaviyarasu from the year 2008, Lee in the year 2015, Falha and Nezad in the year 2017, Perez Gonzalez in the year 2020. Now, how are you going to master statistical quality control? That is from descriptive statistics to acceptance sampling. Statistical quality control is basically a methodology to monitor and control the quality of product and services. Under statistical quality control, we have categories with respect to descriptive statistics. Here we are talking about quality characteristics and relationship with an example. Say you can take mean and standard deviation. Under statistical process control, we extend the use of descriptive statistics to monitor the quality of product and process, state of control and amount of variation. And acceptance sampling is the third category under statistical quality control. Now, what actually we do in acceptance sampling is we just check whether it complies with the standards. When it complies with the standards, we accept. When do we accept? When the defective pieces are less than your acceptance number. Non-compliance with standards, we reject when defective pieces are greater than acceptance number. Now, with respect to quality, we in acceptance sampling, we look into the quality aspect. Here we have two distinct meanings which has to be differentiated. One is quality of design. Say, for example, you take blade. The purpose will be the same, but it differs in sharpness, corrosiveness, and your price. When it comes to quality of conformance, the ability of production process to maintain a specified quality of the design in the long run. How are this quality of measurements made with respect to quality? One is variable, another one is attributes. Here we are talking about directly measurable, that is thickness, length, temperature, tensile strength, and here it refers to producing continuous data. And with respect to attributes, we talk about cracks, breakages, assembly defects, air bubbles, that is producing discrete data. Now, data science and quality, statistical quality control. Because data science, we are dealing with data, and in quality control, we are bothered about quality. So this concept can be extended for use. Say like it is a practical extraction and application of patterns from recorded observation, and we also get knowledge about it. Now, how are we going to introduce data science? Because it is a practice of extracting insights from large and complex data, we have advanced analytical techniques. But how does this statistical process fit into this picture? That is by monitoring and controlling. Here we make ensure that process that they are operating And with the combination of data science with particle control, we can not only identify areas of improvement, but also controlling. Now, data science, we say it is an interdisciplinary subject as it deals with extraction, analysis, interpretation of data to solve complex problems. Here, it incorporates the techniques of statistics, mathematics, computer science, and have a specific domain knowledge. The goal of data science is to uncover insights and patterns that can be used to make informed decisions. There are key concepts and techniques used in data science like predictive analytics and data mining, machine learning, processing. They are used to extract meaningful information from the data sets, and you can build models to predict the future outcomes. This has been used in various industries. Now, statistical process control. Here we are talking about quality control method, which uses statistical analysis to monitor and control a process. It involves collecting the data on the process and analyzing it on to identify any trends or patterns that may indicate a problem. By detecting the problems early, it allows for corrective action to be taken in the process for defective products or services. There are several key concepts and techniques in process controls like process control charts, process capability analysis, or statistical process analysis. Or you can go in for control charts, which are graphical representation of data, and it is for identifying the trends and patterns. Process capability analysis is used to determine whether the process is capable of producing the products or services within specific tolerances. Here, finally, statistical methods to analyze the data and identify the patterns may indicate a problem. Now, how data science and statistical process work together. How they work, they are complementary tools and they work together to improve the quality control and optimize the process. Here now, combining data analysis with rigorous process control, organizations can gain a deeper knowledge or understanding of the observations and informed decision. So while, for example, you can identify the patterns with respect to data science in a production data, which may not be apparent through traditional process method, it can lead to an insight for targeting the process improvement and better quality control. On the other hand, we can provide a framework for monitoring and controlling process in real time and by maintaining the level of quality and consistency. What are the challenges and limitations that we come across? One of the biggest challenges when using data science and SPT together, you have to ensure the data is accurate and reliable. Data quality issues you may come across, the data may be missing or it may be incorrect, and you may have incorrect analysis and you may have flawed conclusions. Additionally, it is difficult to integrate data from different sources, which can further complicate the process. This becomes a challenge now. This challenge is ensuring that models, algorithms are appropriate for SPC application. And we also have to make sure that models that work well for one application may not be suitable for other. It may be a little difficult, and the models are most appropriate without extensive testing and validation. Now there's a challenge of interpreting and communicating the results of data, which is non-technical, and the stakeholders who may not have a deep understanding. What is its implication? Now, what is that? As data science has explored the world and statistical process control, how they work together will be to optimize your process and also to control. Now that we have seen it is of late, the data science is a powerful tool for analyzing large amount of data, identifying the patterns, trends. This will be process control for monitoring and control process for ensuring consistent quality. Now, by combining these two approaches, it helps the organization to have a deeper understanding of the process and make sure how better decisions they can take and how to improve on them. They also can identify what potential problems are before they occur and also take proactive measures to prevent defects and reduce waste. This can lead to cost saving and improved customer satisfaction. Now we are moving to quick switching system. Here helps the plan. We have taken repetitive group sampling plan. You can manipulate tables, analyze with using operating characteristic curves. Here we are identifying the pattern, runs the system. To the main objective is to based on gamma zip distribution as such as two plan parameters. These plans are studied under smart manufacturing situation here as the inflation of 0 or more. Here using Bayesian statistics here because it's a powerful tool and an approach in the field of statistical theory. Unlike traditional methods, Bayesian it allows to incorporate the prior knowledge and uncertainty into our models. That means we make more accurate predictions and better understanding that generate our data. One of the key benefits of is to we can handle complex data with parameters. Introduction to gamma zip. Because of the technical advancement, the production process are well designed in such cases that occurrence of defects becomes a rare one. So we'll have to make an alternate study. So here this study is to investigate the factors involved in the development of sampling plans which has a prior history about the manufacture. Zero inflated models provide frequent zero valued observation when production units are monitored during your inspection process. This is the operating characteristic curve function. The OC curve. OC curves are for a sampling plan for producers risk and consumers risk. Inspection procedure. Minimum angle method. Norman Bush in the year 1953 used a different technique to describe the OC curve. This method involves comparison of OC curve against a portion of ideal OC curve. Here we are talking about the length joining the acceptable quality level and probability of acceptance. He has mentioned that consumer risk can be minimized by making the ideal OC curve. Peach and literature in the year 1946, they used predetermined points, say like P1 1 minus alpha and P2 beta on the OC curve to determine the obtain the operating ratio and corresponding unity value, say NP, with an ideal condition to minimize the consumer risk. This is the minimum angle method procedure. Here we are talking about the practical performance of the sampling pen, which is revealed by operating characteristic curve. It involves comparison of OC curve to that of an ideal curve. Tangent of the angle method, line joining the points AQL and 1 minus alpha, LQL and beta. Here we are taking the points P1 equal to AQL and P2 equal to LQL. By one can get a discriminating plan with a minimum angle, and the tangent of angle made between the lines AP and AC is given by tan theta equal to BC by AC. Tan theta is NP2 minus NP1 by P of P1 minus P of P2. The smaller the value of tan theta, closer is the angle approaching 0. The chord approaching AB and AC is the ideal condition. This criterion minimizes the consumers and producers risk and favors the plans evolved by the criterion. Now, various operations, various challenges we have faced. How we going to achieve reliable, accurate predictions? What are the data science approaches to quality control? We have derived challenges by inspecting product quality control method. We can take an example for quick switching Bayesian repetitive group sampling 3 with a maximum of 5% producers risk and maximum of 10% consumers risk with quality limits and also minimum angle to be calculated. Then we assume that the manufactured quality follows gamma zip distribution For example, if manufacturer wants to determine the design parameters for given values, they say P2 equal to 0.19 and P2 0.01, S equal to 110. Here we can obtain variation representative to something involving minimum angle, which is calculated as follows. P2 by P1 is 19 and your tabulated value corresponding to this acceptance numbers. We have U1 0, U2 3, V1 0, V2 1. From the table, we have calculated NP1 and NP2, and we get the N as 30, N equal to 32, and respect to corresponding as alpha equal to 0.05 and beta 0.10. Tan theta is given, and therefore the minimum angle is 11 point. Therefore, proposed plan. This is a table indicating minimum tangent angle N theta, alpha, beta, S, omega, nu in degrees, theta in degrees, and your optimal parameters is 61, 5, 02 with minimum angle. So here in designing plan system associated levels, concerning the producer and consumer, the sampling system is useful in the area of testing and safety destructive areas. The general firm work studied with makes the OC curve approaching to ideal form by minimizing the tangent angle joining the points. It provides an alarm for sense for the quality control towards lot sentencing, and the disk exists under this plan. It is mainly related to obtain an optimal plan parameters in any manufacturing industries for inspection procedure. The unity value approach has been used to obtain optimum value of the tangent for specific values of NP1 and NP2 by keeping the producer's risk at 5% and consumer's risk at 1%. This is a table value which has been shown. Table 2, this is table 3, table 4, and this conclusion. In the sampling system, the product life follows two plan parameters, namely normal and Titan, and minimal sample size needed, and it guarantees a particular product, and the associated producers' risks are obtained. Here we are application of data is presented. These are the various references I have made, bibliography. And that is, thank you one and all. That's my presentation. I thank Kavir sir for giving me an opportunity to present here. Thank you one and all.
Thank you, Parimla. So the forum is open for discussions or any questions or clarifications. One or two. Okay, Parimla, you said about gamma zip distribution, right?
Yes.
What is the need for studying gamma and zip together?
Gamma zip, we have frequent zeros. Any manufacturing industries, we have. You may come across that there are no. There is no defects. You may go for zero defects. In such cases, we'll have to go for gamma zip.
So actually, you have to collect the data related to this for gamma and zip environment. And you can give an example. You said about yarn industry somewhere and how these can be collected for your QSS, right? So,
yes.
So you have to try to get the real-time data related to that, and if you have made comparison, that will be more practical oriented, it will be useful for the young people also. Okay.
Okay, I'll plan another to do it.
Okay, thank you, Dr. Parimla. If there is no more questions, we thank Dr. Parimla. So you can stop sharing.
Thank you. I thank even the organizers, Dr. Satish Kumar, for his support.
Okay.
Thank you.
Okay, thank you. So the conclusion. So actually, we have planned 4 speakers. and the four speakers are all given their respective topics. They have delivered their talk. So on behalf of the organizing committee, I like to thank all the four speakers. Specifically, I like to thank Dr. Alagiri Swami from Periyar University, Dr. Jayalakshmi from Bhadyar University, Dr. Parimala from Chennai, have sparing their valuable time with us and given their talk on the topic what they have already allotted. So, on behalf of the organizing committee, I once again thank all the three speakers, and also I thank Dr. Satish Kumar sir for their wonderful arrangement for the National Statistics Day 2023. So we have we all joined here and discussed about the importance of statistics and what are the recent developments and applications in statistics are emerging in different parts of the country, and given their talks on this forum. So on behalf of the members who presented in my topic, I thank Satish Kumar sir for giving an opportunity for all of us to share our research ideas in this forum. So, not but not least, I also thank all the participants who joined here for their patience listening. Now it's time to hand over to the organizers.
Thank you. So
Yeah.
thank you, Kaviraj sir, for chairing this
Thank you.
session.
Thank you very
On
much.
behalf of the organizing committee, I express my sincere gratitude to you, sir, and all the other participants present here.
Okay, thank you very much, Riaz. Thank you very much.
Sadish sir. Sadish sir.
Satish sir is there, or he is in the next another meeting?
Okay, some technical problem.
Okay.
That is why he is not
Convey my
responding.
regards to Satish sir. Okay.
Okay. Thank you, sir. Next session will start, I think, at 12 p.m.
Hello, Dr. Satish, I am ready here. Hello, Satish sir.
Sir,
Hello.
our next
I am ready.
session is at 12 o'clock. So
Okay.
we'll wait for a couple of minutes and then we'll resume.
I am ready.
Good morning, Joe sir.
Good morning, Rias. റിയാസ് സാറേ, നമ്മുടെ ചെയർമാൻ വന്നില്ലെന്ന് തോന്നുന്നു. ചെയർമാനെ ഒന്ന് വിളിച്ചാൽ.
ഞാൻ ഒന്ന് വിളിക്കട്ടെ സാറേ ചെയർമാൻ, ഒരു മിനിറ്റ്.
ഷിൻഡെ സാർ ഐ ആം റെഡി.
ഓക്കെ, ഞാൻ ഒരു മിനിറ്റ് സാറേ ഒന്ന് വിളിക്കട്ടെ.
ആയിക്കോട്ടെ, താങ്ക് യു.
Joe sir, I cannot connect with him, sir. Joe sir?
അല്ല ഇപ്പൊ പറഞ്ഞിരിക്കുന്നത് ഷിൻഡെ അല്ലേ, പ്രൊഫസർ ഷിൻഡെ?
Now he is here. Shinde sir? Okay, he is joined. So welcome dear Professor Shinde sir. Sir, you are...
Warm greetings to all.
Sir, you are
Priya
muted.
sir, may I take over?
Okay, Swapna, please introduce our chair. Anjana,
Yes,
you are
of
introducing. Okay.
Thank you. Warm greetings to all. The technical session 33 of WSTA 2023, which will be chaired by Dr. Ramakrishna Lahu Shinde. Dr. Shinde is the head to the Department of Statistics at Kavitri Bahanabai Chowdhury, North Maharashtra University, India, who has over 3 decades of teaching experience and specializes in probability theory and the reliability of systems, among others. He has several research publications to his credit, including the articles, a new probability-based multivariate process capability index published in the International Journal of Quality Engineering and Technology, and Undernutrition Among Indian Men, a study based on NFHS3 published in the American Journal of Men's Health. On behalf of the organizing committee of WSTA 23, I hereby extend a warm welcome to you, Dr. Shinde, and cordially invite you to chair the session. Over to you, sir.
Thank you. So, good afternoon to everybody. This session has two speakers. In this session, we have 2 speakers. First one is Professor K.K. Jose. He is currently Honorary Director, School of Mathematics, Statistics and Data Analytics at MG University, Patan. He served for more than 30 years state of Kerala and other states of India as a principal, professor and head Department of Statistics, teacher in statistics, researcher, excellent administrator. He got awards for administration also. His research area is statistical modeling, stochastic processes, distribution theory, time series modeling, sampling theory, reliability analysis, multivariate analysis, quality control, biostatistics related areas. 150 papers, more than 150 papers he has published and 25. Delivered many industry talks and in India and abroad. Particularly, he has organized many programs. More importantly, more than 100 quizzes for popularizing statistics all over the Kerala state and country. Overall, Professor Jose is excellent teacher, researcher and administrator. And I will call him as a resourceful personality in the field of statistics from Kerala as well as in this country of India. I would like to invite him to deliver his talk on generalized Harris family of distributions. Okay, Professor Jose, you will get around.
Okay, I am here, sir. Okay. Thank you. So, Professor, thank you, Professor Shinde, for your introduction. And I'm very much grateful to Professor Sadish Kumar for organizing this WSTA online program. And as part of the National Statistics Day celebrations. So before starting this, my talk, I pay my tributes to Professor T.S.K. Muthad, who was the professor and head of the Department of Statistics of the University of Kerala, who had passed away very recently during June itself. So, and also I pay my tributes to my professors, former professors, especially Professor R.N. Pillai. So now I will be sharing my slides. I hope it is visible. Okay. Now it is visible?
Yes.
Okay. So the top.
Yes.
Yeah, it is visible, brother. It is visible.
Okay,
Yeah.
okay. So I can proceed. So my topic of discussion is actually generalized Harris family of distributions and theory and applications. And as far as generalized family of distributions is concerned, adding new parameters for extending classical distributions in order to obtain more flexible new families of distributions has been investigated by several others in recent years. In many applied areas such as lifetime analysis, financial modeling, insurance, etc., there is clear need for extended forms of classical distributions. That is, new generalized families of distributions which are more flexible to model real data sets in these areas, since the data can present high degree of skewness, kurtosis, etc. And the present paper focuses on the class of distributions called Harris extended family of distributions, introduced by Ali and Ben-Gor in 2011. And then recently myself, Albin and Jos, my students, Sophia et al., 2021-22 have introduced and studied different Harris extended distributions and their applications. These authors proposed an interesting method by adding parameters to a baseline distribution yielding the so-called Harris extended or HE family of distributions. And this family actually includes the baseline distribution as a basic exemplar and gives more flexibility to some distributions for modeling various types of distributions. It's not coming, some problem. Okay. So now we will be coming to the Harris PGF. So it is actually defined in terms of a probability generating function given by phi s theta k equal to theta s raised to k divided by 1 minus theta bar s raised to k whole raised to 1 by k, where theta bar is nothing but 1 minus theta, where theta lies between 0 and 1. And here, when k is a positive integer, it can be put forward as a result examining a simple discrete branching process. So it has got some connections in the context of discrete branching process also. When k equal to 1, we have the probability generating function of the geometric distribution. Now, coming to Harris extended family, so the survival function is given, some survival function f is given. The Harris family of survival functions is given by hx theta. So that is equal to theta into f bar x whole raised to k divided by 1 minus theta bar into f bar x whole raised to k, the whole raised to 1 by k, where f bar x, that is the survival function of a baseline distribution. So certainly this f bar x also lies between 0 and 1. So this is actually just substitution in the Harris generating function itself. So this can be considered as a generalization of the Marshall-Röntgen family of distributions. So when k equal to 1, this actually reduces to the Marshall-Röntgen family of distributions. And Sandhya et al. 2008 proposed Harris family of discrete distributions. Then Alice et al. 2003-2005 considered Marshall-Röntgen families. Then Geethani 2005 discussed about Marshall-Röntgen extended Pareto distribution and so on. Jagumar and Thomas 2008 discussed a generalization of Marshall-Röntgen scheme using gamma, and they have applied it to Berg type of distributions. Nadaraja et al. 2012 introduced a new family of lifetime models called models. Then Sarlish 2001 discussed about this type of distributions. Then Gupta and Kundu, Sarlish et al. All consider different types of Harris extended distributions. And Harris extended probability distributions, or Harris extended family, is having a closed form expression for the probability density function also, that is given by Gx equal to theta raised to 1 by k into fx, where fx divided by 1 minus theta bar into f bar x whole raised to k, the whole raised to k plus 1 by k. So here the failure rate function also has a closed form expression given by hazard rate function, that is Hx equal to Rfx divided by 1 minus theta bar into f bar x raised to k. So this actually makes this model very convenient to use. So we are having closed form expressions in the case of probability density functions as well as hazard rate functions. And now we will be coming to, so here this Rfx actually denotes the failure rate function of the baseline distribution. So Rfx is the hazard rate function of the baseline distribution. When k equal to 1, the above equation actually reduces to the Marshall-Rutkin family of distributions introduced in 1997, the various extensions. And regarding Harris-Extended distributions, so we can have some algebraic equation that is actually given by Barreto and Sousa et al. 2013. So they give they discuss various mathematical properties of Marshall-Rutkin family of distributions and an algebraic expansion also in the form of gx equal to fx into summation I equal to 0 to infinity wfx wi f bar x whole raised to k into I. So that expansion is also possible, polynomial expansion. Then we will be coming to the PDF also. PDF is also for theta greater than 1. So we have gx equal to fx into sigma nu I into f bar x raised to ki. So that way we can obtain the PDF, and it has got say 2 different expressions for 0 less than theta less than 1 and theta greater than 1. And Bartsidis and Lamonde 2014 have conducted an extensive study on this Harris-Extended family of distributions. The Harris-Extended family of distributions can also be constructed as proportional failure rate model. So from a modified Marshall-Rutkin model. So we initially generate a new class of distributions with survival function, some given by some f1 bar x equal to f naught bar x whole raised to k. That is actually the proportional model. So which is a proportional failure rate model of initial one. So next we apply the Marshall-Rutkin transformation. Then we will be getting g bar x equal to theta f1 bar x by 1 minus theta bar into f1 bar x, where f1 bar x is nothing but f0 bar x whole raised to k. So this actually gives you the proportional failure rate interpretation, so from the context of reliability theory. So as far as this Harris-Extended family as well as Marshall-Rutkin family is concerned. So when k equal to 1, we are having the Marshall-Rutkin extended family. So therefore the Harris-Extended class of distributions is a proportional failure rate model for reliability theory context. Now we can have we can generate the obtain the expression for the qth quantile also. Xq is equal to g inverse of this, and that actually helps us to generate random variables from this Harris-Extended family in the very general sense. For particular distributions, we will be having special situations. Then the moments also can be obtained. Moments of the Harris-Extended distribution exist for exactly the same order as in the baseline distribution. And that also we have expressions. The moment generative function is given here. Then using that you can obtain the moments. And regarding Marshall-Rutkin family was extensively studied by my team, Jos and his research scholars in recent papers. Tahir and Nadaraja in 2015 paper. So they have quoted all these papers. Actually, they have referred to more than 40 papers published by my group. And these are actually the papers. And finally, they have come to, so they have commented on our works also. And it is very appreciating that the contributors have expanded the horizon of application of efficient statistical modeling. And in this regard, the acknowledgement and appreciation goes to Professor Jones, N. Balakrishna, Costa Sagros, Felix Mamoye, Kalam Lee, then Jamesh Gupta, Arjun Kumar Gupta, Debasis Kundu, Gitani, myself, and so on. So that is an appreciation to our works by international statisticians like Professor Cordera and so on, Brazilian statisticians. Yours 2011 discussed on Marshall-Rutkin family of distributions and their applications in reliability theory, time series modeling, stress strength analysis, and so on. We have developed auto-recursive minification processes, max-min processes, etc., having different structural forms also. various researchers have applied the models in industrial reliability contexts for obtaining optimal acceptance sampling numbers for conducting the study. Now we will be coming to the Harris extended variable distribution. So here actually we are substituting the survival function of the variable distribution. So F bar x, the new model, the Harris extended variable model is having the survival function as F bar x equal to theta into e raised to minus k into lambda x raised to beta, whole divided by 1 minus theta bar into e raised to minus k into lambda x raised to beta, the whole raised to 1 by k. The PDF can be obtained easily, and the reliability function is Rx equal to beta lambda raised to beta x raised to beta minus 1 divided by 1 minus theta bar into e raised to minus k lambda x raised to beta. So there is closed form expression for the PDF as well as the survival function. And we have applied we have considered the special cases, the shape, properties, etc. have been considered. Then the quantile function is also obtained, and the failure rate function in particular has been studied in detail. Let Rx be the failure rate function of the new Harris extended variable distribution. Then for beta less than or equal to 1 and 0 less than theta less than or equal to 1, this Rx is decreasing over the support 0 to infinity, and it has got decreasing failure rate function in that range. For beta greater than or equal to 1, theta greater than 1, Rx is increasing in 0 to infinity, and it has got IFR property. And for beta greater than 1 and 0 less than theta less than or equal to 1, such that this delta beta theta is equal to this one, Rx is increasing. Otherwise, Rx is increasing, decreasing, and increasing. Something like then for beta less than 1 and theta greater than or equal to 1, this Rx is decreasing. Otherwise, it is decreasing, increasing, and decreasing. So different shapes we are having in that context in the case of variable. As in the case of variable, we are having different contexts. So here in the case of Harris extended Lomax distribution, so we are having the survival function in this form, and the PDF is given. Then the reliability function, the hazard rate function is also given. And there also we are having the quantile function, and there also we can have different properties. Then the failure rate function of the Harris extended Lomax distribution is considered. So for theta 0 less than theta less than or equal to 1, this Rx is decreasing. And for theta plus theta bar k gamma greater than or equal to 0, Rx is decreasing, and so on. So different properties are there. Unique model, then property also is there. Then we have considered Harris extended linear exponential distribution, which is a generalization of the exponential distribution, and this actually gives to linear failure rate function, and that is why the particular distribution is called linear failure rate distribution. And in that case, we have considered the Harris extended version, and there also we have the reliability function, the hazard rate function, and the PDF having different shapes. So there also we can develop the qth quantile. Then we have considered the Harris extended Gumbert's distribution with the baseline distribution as the Gumbert's distribution. There also we have all these expressions. Then Harris extended Pareto distribution is also developed, and the hazard rate function, PDF, survival function, etc. are obtained. Then the quantile function is also given. Harris extended Fresher distribution is also considered. There also all these functions are developed. Then Harris extended Berk-12 distribution. So there we have considered the particular case. Then the probability density function is given. The hazard function is given. And when k equal to 1, we are having the Marshall-Rutkin-Berk-12 distribution. And the graph is the hazard rate function is given. This is the PDF. The PDF is given. The hazard rate function is given. Then the quantile function is obtained. And the Harris extended Berk order statistics and record values are considered in detail. So we are having a random sample x1, etc. xn. Then the order statistics are considered h1 and x2 and etc. xn. Then the survival function is given. The CDF of the minimum order statistic x1n is given by this expression. Then the maximum order statistic xnn is having the PDF in this form. The probability density function of the ith order statistic is obtained. Then we are considering the record values. So actually record values were introduced by Chandler 1952, and the theory of record values and its distributional properties are studied in detail by Agasanulla, Rakka, Balakrishnan and Agasanulla, Saran and Singh, Krishna et al. And Krishna is my student. And we have, so here is the definition of the upper record value. So let exponential sector xn be a sequence of independent and identically distributed random variables. Let yj equal to maximum of exponential sector xn for j greater than or equal to 1. Then xj is called an upper record if yj is greater than yj minus 1. So similarly, you can consider the minimum record value also. So let xu1, xu2 sector xu1 be the end record statistics from a population with the cumulative distribution function fx and probability density function. Then the probability density of the density function of the end record value can be obtained as far as this Harris extended family. We can obtain general expression for that. Now we are considering the inference, that is actually estimation of the parameters. So we have, in particular, we have considered the Harris extended Berg type 12 distribution, and we have taken the sample. Then we have considered the log likelihood function is considered, likelihood of the sample. Then the log likelihood is considered, and we have obtained the normal equations, but the normal equations are not giving any closed form expressions. So we can use the NLM software in R to obtain the estimates, and that is how we have obtained the estimates. So Gupta et al. Introduced exponentiated exponential distribution. That also we have considered that f bar x is 1 minus e raised to minus lambda x whole raised to alpha. So this is actually something which was studied in detail by Kundu et al. Also. And g bar x is in this expression, and the PDF is given. The hazard rate function we can obtain. Then different forms are there. Then the quantiles are there. So here the failure rate function or the hazard rate function is having this general expression, and quantiles and order statistics are considered. Then here are the distributions of the maximum order statistic and the minimum order statistic. Then the probability density function of the ith order statistic is obtained. Then we have proceeded. Then the likelihood function is obtained, the log likelihood is obtained. Then we have obtained the normal equations. Here also the normal equations cannot be solved very easily. We will be using R software and the NLM package. In particular, here we consider the application of, so here we are using two different data sets. The first data set is used to compare the Harris extended Berg type 12 with the Berg type 12 distribution, and the second data is used to compare Harris extended exponentiated exponential distribution with exponentiated exponential distribution. And for that, for comparison purposes, we will be using the AIC archaic information criterion, BIC Kolmogorov statistic, etc. Then here is the data. The data is taken from Cholukin and Stephens 2001, and the data is actually regarding exceedance of flood peaks. So of the Wheaton River near, so that is in Canada. So the data consists of 72 exceedances for years from 1958 to 1984. And the observations are here, and we have applied the models, and we have compared the goodness of it. And what we have obtained is, for the Harris extended Berg 12 model, the AIC value is 618.85, BIC is 627.96, and the Kolmogorov similar statistic is 0.51. Whereas for the ordinary Berg 12 distribution, we are having very higher values, 1180.7, 1189.8, and Kolmogorov similar statistic is 0.85. So in all these cases, so we are having the optimal situation in the case of Harris extended Berg 12 distribution. And the second data, that is second data set, is from Lawless 2003, and the data is on failure times for a sample of 15 electronic components in an accelerated life testing experiment. and we have obtained the maximum likelihood estimates, and we have fitted the model, and the goodness of it is also compared here. For the Harris extended exponential model, the IIC value is 505, BIC is 508, and the Kolmogorov-Smirnov value is only 0.7056. Whereas for exponentiated or extended exponential distribution, the Akai information AIC value is 1,482, somewhat 3 times the value. So 1,485, then Kolmogorov-Smirnov statistic is 0.89. So showing that the model is more appropriate than the usual models. Now we are considering the stress strength reliability analysis also. Here in stress strength analysis, we are considering the reliability value, so which is actually R equal to probability that X less than Y, where X is actually the stress and Y is the strength. When Y is the strength, when the strength exceeds the stress, certainly the system can work. Otherwise, the system will collapse actually. So this measure of reliability is widely used in engineering problems actually. So it may be noted that R has more interest than just a reliability measure. So it actually can be used, it is used by mechanical engineers in the development of various machines actually. So in spacecraft modeling, etc., it has got more importance. So here, as far as probability X less than Y is concerned, or that is actually probability Y greater than X. So you are making conditioning and you are obtaining the expression. In this case, you can obtain the expression as alpha by alpha minus 1 square into minus of log alpha plus alpha minus 1, and where alpha is alpha 2 by alpha 1. So this alpha 2 and alpha 1 are the parameters associated with the two distributions, Marshall-Rudkin pressure distribution, etc. So we have obtained the estimate, and we can proceed with that. Then reliability test plans. So in statistical quality control, acceptance sampling plan is concerned, and their reliability test plans are having more importance. So Kandam et al. 2001, Srinivasa Rao et al. 2009, etc. considered various or developed various reliability test plans. Myself, my students also have developed Jose and Krishna and various others. Jose and Demia 2015 also developed a Marshall-Rudkin Rayleigh distribution and applied it to reliability test planning and acceptance sampling. And the test may be terminated before the time t is reached when the already observed number of failures exceeds c. So the minimum number, suppose you are having the minimum acceptance number, then that is regarded as an optimal situation. So certainly usually sampling. So in industrial context, it is a costly affair. So we need to take sampling plans which are having very small, very comparatively small acceptance number. So that is, we are interested in obtaining the smallest sample size necessary to achieve, say, our objectives of strength and other things, alpha, beta, and then OC function, etc. So acceptance numbers you can obtain using binomial approximation or Poisson approximation. In many cases, we use in the finite sample situations, we will be using binomial approximations when the proportion, the probability is actually close to 0.5. So in not very, very small. So when the probability is very, very small, so we'll be using the Poisson approximation. So here are the acceptance sampling numbers with respect to different values. The C values you will be getting, then the acceptance numbers are in the tables. So that is actually for the Marshall-Rudkin Rayleigh distribution that is given. Then this table, so this is actually the Poisson approximation. Then we are having the producer's risk. All these things are considered. Then the producer's risk is the probability of rejection of the lot. Then the consumer's risk is also considered. Usually producer's risk is given more importance in industrial context. So for a specified value of the producer's risk, say 0.05, one may be interested in knowing what value of sigma will ensure a producer's risk less than or equal to 0.05 for a given sampling scheme. And for that, you can make use of another method is actually to make use of the binomial approximation, and then you can obtain the table, and the values are given here. And so we have seen that these values are comparatively smaller. In the relative test plan using polynomial and Poisson approximation, the minimum sample sizes are less as compared to Krishna and Joss, Ristic, and so on. So the new plans, we conclude that the new test plan is preferable than the older ones. Then we are considering what are the minification process, that is applications in time series modeling. So we are considering different structural forms, xn equal to epsilon n with the probability p minimum of xn minus 1 with epsilon n with the probability 1 minus p. And there also we have developed the model. Then another model is actually xn equal to xn minus 1, the previous value with the probability p1. The epsilon n is having some significant role with the probability p2. Then minimum of xn minus 1 epsilon n with probability 1 minus p1 minus p2. Then in that case also this model can be applied. Then another form, that is maximum, minimum, and the process value. Maximum xn is equal to maximum of xn minus 1 epsilon n with the probability p1, minimum of xn minus 1 epsilon n with the probability p2, and xn minus 1 with the probability 1 minus p1 minus p2. So one more generalization we have considered, that is called the max-min process. So where you are having all the four components, that is xn is equal to maximum of xn minus 1 epsilon n with the probability p1, minimum of xn minus 1 epsilon n with the probability p2, epsilon n with the probability p3, xn minus 1 with the probability 1 minus p1 minus p2 minus p3. So where 0 less than p1, p2, p3, all less than 1. So all these p1, p2, p3 are the probability values. They are lying between 0 and 1. But p1 plus p2 plus p3 is equal to, is less than 1. p1 plus p2 plus p3 is less than 1. And sequence epsilon is a sequence of independent and identically distributed random variables independently distributed of xn. And then the process is stationary, Markovian with the Marshall-Rutkin distribution as marginal. So this fourth one, 4.1 is a generalization of all the three other models. And in all these cases, we can make use of this type of model. So we can have applications of this model in various contexts, not only in biostatistics. I have just mentioned biostatistical context. So the above model can describe the responses to treatment of a patient suffering from BP or the blood pressure or systolic measure in a normal situation. So xn is the same as xn minus 1. Otherwise, so suppose we are an acute patient. So if it just bring a cup of tea, then certainly the innovation will be coming. So some such situations. So then innovation is also important. In some cases like VP, we have to keep the minimum as well as maximum also. So it cannot exceed. Then you will be having hypertension. When it is minimum, you will be having low tension. So such problems will be there. So such models are useful in economics also, economics and hydrological context. In economics also, when the financial situation is concerned, when the inflation is very high, it is certainly it is not good. When the inflation level is very low, so there may not be any movement at all in the market. So that way, so this maximum is important, minimum is important. When some catastrophes happens, when some problems, some wars occurs in some adjacent countries, certainly the stock market will be plunging down. So such situations are there. Then in the case of dam level also, so we have to keep a minimum level. So the maximum level also we cannot exceed. So during 2018 in Kerala, we observed that. So when there was heavy rains, so actually all the dams were full, but that actually caused heavy damage in the whole state actually. So in many places that we are observing during these years, in Chennai, in Mumbai, etc., this type of rains are usual nowadays. So even so, in such situations, in the case of aeroplanes and submarines also, maximum models are needed actually to model. So they will prevent explosion as well as implosion. Very recently, we have heard about the Titanic, the Titan submarine. So our scientists, many scientists say it was explosion. Some others say it was implosion. So implosion means the minimum level. So it actually crunched. Then explosion means it is exceeding something. So one of these things have happened. So in all such situations, so we have to make use of appropriate models. And I think we hope that this type of models are proper for modeling such situations. So, these are our references. Albin and Joss, 2021 in reliability theory and applications. Albin and Joss, 2020 in International Journal of Statistics and Reliability Engineering, and so on. The Sally and Berkoff paper appeared in Sankhya 2011. Sankhya be a new family of distributions based on probability generating functions, and so on. Balakrishnan and Agasuna, Barreto, Chandler, and so on. These are the different papers. Krishna, Joss, and Ristic in statistical theory and applications. Then this is the Marshall-Wilkin paper which appeared in Biometrica 1997, and so on. Nadaraja and Jagumar and Ristic, and so on. Sophia Thomas, Lisha Moll and Joss. So these are actually some recent papers. In 2023, we have a paper on discrete Harris extended variable distribution and applications, and that was applied to model COVID data, and that was actually very useful. And that appeared in statistics and applications, and so on. So then Tahir and Nararaja's paper, which was on G families, that was a review paper on G families, which appeared in the Brazilian Journal of Statistics. Thank you all. Thank you, sir.
Thank you.
Any questions? Any questions?
Very nice presentation. Professor Josh has made very nice presentation on various family of distribution and their applications in the areas like biostatistics, control, and other areas. If audience has any question or query, one can ask quickly. If no question, let us thank to Professor Josh for this nice presentation.
Thank you, Professor Shinde and Professor Sadish Kumar. Thank you all. Thank you all.
Thank you, sir. Thank you, Professor. Thank you, sir.
Thank you.
Thank you so much.
Thank you. I will close my stop my share. So next is Jagumar. Okay, I have
Professor
stop share.
Jayakumar, Professor Head, he is working as Professor Head, Department of Statistics, University of Calicut. He has got more than 30 years of experience in the area of teaching and research. He worked for PhD under the guidance of well-known professor from Kerala, Professor R.M. Pillai, University of Kerala. He has done a very good research and received national, international fellowships and awards. Research area for Professor Jayakumar are distribution theory, time series and forecasting, probability theory mainly. He has published more than 100 research articles on his credit in reputed journals of statistics and related areas. More than 10 students have obtained PhD. He served as the General Secretary and President of Kerala Statistical Association in recent years. I would like to invite him for his talk on the discrete linkage, exponential and variable models. So, dear Professor Jayakumar, you may start with.
Thank you, Professor Shinde. Okay. Thank you, Professor Shinde, for the nice introduction, and thanks to Professor Sadish Kumar for inviting me. And my topic of today's discussion presentation is on discrete linear, exponential, and variable families of distributions, and these distributions arise as the distributions of random minima. Let me share my presentation. Is the screen visible?
Yes.
Yes, yes, it's visible. It's fine.
Okay.
It is fine.
Thank you. Thank you. And the topic of today's discussion is on discrete linear, exponential, and variable models. And before going into the details, we know that the discrete linear distribution, it is in fact a distribution which is related with the discrete stable, and discrete linear exponential is in fact, it is not a discrete distribution, it is a continuous distribution, and it is a generalization of the classical exponential distribution. So we are introducing two classes of models which are in fact generalizations of the well-known exponential and variable models. And I will now go through the work that we have done. So that is a family of distributions is generated using truncated discrete linear distribution is studied here in the presentation. And this family is a rich family which includes a number of well-known families of distributions such as the Marshall-Olkin extended family of distributions, family of generated distributions generated through truncated negative binomial, family of distributions generated through truncated DML, etc. So, and as a particular case of this family, we will look for the generalization of the well-known exponential and variable distributions, namely discrete linear exponential and discrete linear variable distribution. And this is in fact a work which has already appeared in Communications in Statistics, Theory and Methods in the year 2022, I think. And various properties of the distributions are explored along with its estimation and real data applications. And before going into the details of this class of distributions, let me look for how this class of distributions has in fact arose, and in fact it arose as the distribution of the random minimum. And for explaining that, I will look for give a brief introduction of compounding of distributions. So Tahir and Cordo in 2016 considered inferred that by adding an extra parameter to an existing family of distributions, it is very common in distribution theory, and often introducing the extra parameter gives more flexibility to the class of distribution functions, and it may be very useful for data analysis purposes. And considering this in the last 2 decades, two major generalization approaches were adopted and practiced. And those 2 approaches have received much attention in recent years. And the approaches are the developing generalized classes of distributions and the generalizing the distribution using compounding approach. Now, let me look for the compounding approach. This approach deals with the compounding of discrete models. Namely, you may be able to compound the random variables using the geometric law or the negative binomial or discrete Pythagorean or Poisson logarithmic binomial power series, etc. with the continuous lifetime models. So you may be able to take the distribution of a random sums of random variables where the sum that you are assuming to be a discrete random variable. So which may follow as a geometric or negative binomial or DML or Poisson distribution, as the case may be. So here we are looking for the case where we are replacing the sum by minimum or maximum. And the basic idea of compounding models of families is that the lifetime of a system with n components and positive continuous variables yi can be denoted by the non-negative random variable y equal to minimum of y1, y2, etc. yn, or z equal to maximum y1, y2, etc. yn, based on whether the components in the series are, it may be either in series or it may be in parallel structure. So when the components are in series or parallel structure, it will lead to the distribution, the random variables corresponding to the minimum of a random number of random variables or the maximum of a random number of random variables. And if you consider y as the minimum of y1, y2, etc., yn, then you can see that the unconditional CDF of y, by conditioning on the integer value random variable n, you may get it as an equation number 1. And similarly, if we take the random maximum, then the unconditional distribution of the random variable z, which is your maximum, by conditioning on n, will leads to your equation number 2, where in the case of 1, the survival function plays a crucial role, whereas in 2, we have the distribution function replaces the row. And if I may look for a certain generalization of it, suppose we may consider a system that is made up of n components, and that the ith component is made of zi components working in series. So you have a system made up of n components, and that the ith component in that is made up of zi components working in series, and let xij denote the failure of the jth component in the ith parallel component. So then if this is the setup that you are looking at, then the failure of the system or the system that you may be able to represent by x equal to max min xij, j equal to 1 to zi, and I takes the values 1 to n. Or you may be able to write it as max yi, I going from 1 to n, where your yi is nothing but it is the minimum, random minimum. So this is in fact the system that you have, that I have already explained, that a system of parallel and series components. So we may be able to, now we are looking for the life distribution of this setup. So before going into this, let me review some of the works that have already appeared in the literature. So one fundamental work is the one that I have already mentioned by Marshall and Rolkin in a paper which appeared in Biometrica, where he has considered, they were considered x1, x2, etc. as a sequence of IID random variables with a survival function of bar x, and n is a geometric random variable which is independent of xi, and they have considered the random minimum, which is given by equation 3, and if g bar denoted as the survival function of your un random variable, which is the random minimum, then g bar of x is nothing but it is given in this equation. That is your alpha f bar x by 1 minus alpha bar f bar x. And that is the case when you are assuming that your random variable alpha has a geometric PMF with, of course, your parameter alpha, which lies in 0, 1. And if you have your alpha is greater than 1, then you may be able to consider again n as a geometric random variable with the alpha replaced by 1 by alpha. And then you may be able to consider the performance of the system based on the random variable Vn, which is nothing but it is the random maximum. Okay, if x1, x2, etc. is sequence of random variables with a distribution function in the family 4, and if n has geometric distribution 1, 2, etc., then you can see that in both your random minimum and the random maximum, under the assumption that your n is geometric, both will belong to the same family. Or in other ways, you may be able to see that it will possess what is known as the stability property. That is the geometric extreme stability property. That is in fact the one of the desirable property, and that is why the work of Marshall and Rolkin has received very much attention, and a number of results have appeared based on that distribution. Now, so that happens when your n is nothing but n is geometry. For example, if I may replace n by Poisson distribution, you can see that stability property may not possess that. So, or in other ways, you can see that your Poisson is not, if you are taking the random minimum, then the extreme with respect to the distribution, the extreme is not, or in other words, it is not, the Poisson is not extreme stable. Some examples of the families generated by Marshall-Wilkins scheme are in the very paper they have introduced Marshall-Wilkins exponential, and also they have studied Marshall-Wilkins variable, then Marshall-Wilkins Pareto by Alice and Deuce, Marshall-Wilkins logistic, Marshall-Wilkins Lomax distribution by Gittini et al. In a paper which appeared in Communication Statistics 2007, Marshall-Wilkins Gamma by Ristic et al., Marshall-Wilkins Power Logistic, Power Log Normal Distribution by Gu. Then the next is another that is independently of the work of Marshall and Wilkins. Adamidis and Lucas 1998 in a paper which appeared in Statistics and Probability Letters in 1998 considers a similar problem, and they have considered the distribution of the random minimum by replacing your xi n is geometric and xi has exponential distribution. And you can see that as you expect, you can see that both the results will lead to the same family of distributions, and the Marshall-Wilkins exponential family studied by Adamidis and Lucas has the PDF given in 5. And you can see that this is in fact a generalization of your classical exponential law, in the sense that whenever the parameter alpha is 0, it will reduce to the exponential random variable. So in fact, it is in fact the alpha that will regulate the changes, the departure from exponentiality. And you can see that will the parameter alpha in fact also regulates the skewness of the distribution also. That is in fact one of the reasons why this Marshall-Wilkins family has received much attention. In another paper in KUS in 2007, in a paper which appeared in Computation Statistics and Data Analysis, where he has considered again the distribution of the random minimum, where the random variable n is replaced by not by the geometric random variable but by a zero truncated Poisson random variable, which has the PMF given in that equation, and the resulting random Poisson random minimum, where the minimum is subject to the Poisson random variable and the component random variable is exponential, then the corresponding random minimum has the survival function given in g bar x equal to e raised minus lambda fx minus this. It is not in the, it is by fx, and whenever you replace your fx by exponential, you will get that. Right? A number of families are distributed, the distributions are studied in the literature by considering zero truncated Poisson distribution by simply substituting appropriate effects in place in the expression for G bar x. In this expression for G bar x. Or then these are some of the examples that are studied. That is exponential Poisson by KUS, and another one is generalized exponential Poisson by Barato Soso and Kribari Neto in a paper 2009 in Statistics and Probabilities. Exponentiated Weibull Poisson in a paper by Mahamoudi and Sepadar in Mathematics and Computation Simulation. Exponential Poisson distribution by Ristic and Nadaraja in Journal of Statistical Computation Simulation. Inverse Weibull power series family in a paper in the, and so on. A lot of work has done by considering the n as nothing but it is the truncated Poisson distribution. And another work that has appeared in the literature is by replacing n by the logarithmic series distribution. And the base work in this direction is a work by Tamsabi and Resai which appeared in Computation Statistics and Data Analysis in the year 2008. And you can see that in this situation, when you are replacing your n by logarithmic series distribution in the random minima series, you will get the resulting survival function as log 1 minus alpha f bar x by log alpha. So that is what you are getting here. And some other works that are generalizations that appeared in the literature are by Jaykumar and Thomas in a paper which appeared in statistical papers, where they have proposed a generalization of the Marx-Shloker family by replacing by taking the power of the survey function, that is alpha f bar x by 1 minus alpha bar x raised to gamma. And whenever your gamma is equal to 1, you know that it is nothing but your exponential. It is simply the Marshall-Rhodkin scheme. So it is in fact a generalization of the Marshall-Rhodkin scheme, and you can see that this construction also possesses the stability property. So that is in fact the one of the attractions of this work. And based on this work also, a number of distributions are developed in the literature. Another case that was studied in the literature is Chakandi and Ganjali in 2009 in a paper which again appeared in Computational Statistics and Data Analysis, where they have replaced the random variable n by a zero truncated negative random variable. Okay. And the resulting random variable un as the PMF, which is given by g bar x is equal to 1 minus alpha fx to the power n minus 1 minus alpha raised to n by 1 minus alpha to the power n. And the case by replacing n by negative binomial was studied by Jaykumar, Nadaraja, myself, and Ristic in a paper which appeared in the Journal of Statistical Computation Simulation. Okay. Where we have considered the distribution of the random minimum, where n is nothing but it is the truncated negative minimum. And the corresponding survival function is given by g bar x here. And based on that, a number of works have been developed. That is, one is exponential truncated negative binomial distribution. Another one is negative binomial Marshall-Rhodkin Rayleigh distribution. And uniform truncated negative binomial distribution. Another one is Weibull truncated negative binomial distribution, generalized exponential truncated negative binomial distribution. So, and another family of distributions that in fact incorporates, that is where we have taken the distribution of the random minimum considered here is the discrete mythographer family of distributions, which in fact a work which was introduced by myself and Professor Pillai, my research guide, in very early in the 1995, in a paper which appeared in Statistics and Probability Letters, where the discrete mythographer family arose in fact as a generalization of the classical geometry distribution. So that this is in fact the mathematical origin of the discrete mythographer distribution. So you have let us consider a sequence of independent Bernoulli trials in which the kth trial has the probability of success A by k, where 0 less than a less than or equal to 1 and k equal to 1, etc. So what does it mean? It means that in the first trial, the probability of success, you are assuming you have a sequence of independent Bernoulli trials. The first trial, the probability of success is A. Second trial, it is A by 2. Third trial, it is A by 3. Fourth trial, it is A by 4, and so on. So, or in other words, the probability of success varies with respect to the trial number. Whereas, in the usual case, in the development of the theory of binomial, geometry, negative binomial, etc., we assume constant probability throughout trials. Whereas here we have considered a slight departure from the constant assumption of constant probability of success. And if that is the case, let us consider capital N as an integer value random variable, which in fact counts the trial number in which the first success occurs. So the counting variable n, it in fact counts the trial number in which the first success occurs. And if you identify if you calculate the probability that the n is equal to r, then you will get it is equal to -1 to the power r minus 1, a minus 1, etc. a minus r plus 1 by r factorial. And the PGF of the random variable capital N is given by G, that is this. And that random variable later on known in the literature as the severe random variable, because the severe has in fact considered this GZ function while he was studying about the properties of hypergeometric series, hypergeometric functions, in a paper which appeared in Annals of Institute of Statistical Mathematics in the year 1979. That's right. Now, let us consider x1, x2, etc., xn be ideal random variables as n with PGF, which I have already mentioned. That is 1 minus 1 minus z to the power a. And let me take my x naught is 0 and n be a geometric random variable with the parameter alpha. Then the generating function of the random sum. The generating function of the random sum leads to equation 7. And you can see that it is known in the literature as discrete rectangular flare. And whenever c equal to 1 and your a equal to 1, you can see that it is nothing but you are simply the geometric PGF. So, or in other words, the DML alpha C, DML AC random variable, where DML 11 will corresponds to the simple geometric case. So, or in other words, I can tell that my DML alpha C is in fact a generalization of the classical geometric distribution. Now I may consider the distribution arising from the random minimum, where the random number is subjected to the DML distribution, where the DML the new random variable, it has the PGF. It is constructed in such a way that you are in fact removing the case your x is equal to 0, and if you are truncating at x equal to 0, what you will get is your random variable y, which has the PM of probability that y equal to x is probability that x is equal to x by 1 minus p naught, and the corresponding PGF is given that is the expression for hx. And in hx, if you are replacing your s by the generative function variable s by f bar x, it is nothing but the situation where you are representing the PGF of the random minimum. So that's right. That is nothing but it is. So that is the case that you are getting here. So, or in other words, we will get G bar x is equal to a whole simplification. We will get G bar x is equal to 1 minus f raised to ax by 1 plus c f raised to ax, which we will call now as the families of distributions generated through DML, truncated DML, with the baseline distribution as fx. And a lot of properties of this family has there. So some study has one. These are some of the studies. So you can see study based on uniform is appeared in 2016, based on exponential by Ristic and Kundu in 2015 in Veteran. Weeble by Vidram, Almatsas and Nekoho in 2015 in communication and statistics, additive Weeble by myself and Sangaran, and so on. And now I will come to the topic of today's discussion, that is nothing but it is on discrete linear distribution. Christopher Schreiber studied the discrete analog of the positive linear distribution with the Laplace transform phi lambda equal to 1 by 1 plus lambda to the power a whole to the power theta, where a is restricted on the interval 0 to 1, theta greater than 0, and lambda greater than 0. So that is the situation. And you can say that this your phi lambda is nothing but it is a generalization of the exponential distribution in the sense that whenever your a equal to 1 and theta equal to 1, it will correspond to the simple exponential case. And whenever your a equal to 1 and theta takes any theta is greater than 0, you can see that it is a generalization of it is nothing but it is the distribution. So this in fact it is a class which contains your exponential gamma and so on. And so this in the being it is positive, it was introduced in the literature by Professor Pillai in a paper in 1990, which appeared in the Annals of Institute of Statistical Mathematics, which he named the distribution as the Mitthoff distribution because of the connection between this function and this distribution and the well-known Mitthoff function, which was introduced by Mitthoff in the year 1903. So now our aim is to consider the discrete version of this positive linear graph. If I am considering the discrete version of a positive linear graph, one of the possibilities is that I may be able to replace my lambda by 1 minus s. And that is known in the literature as what we will call it as the alternating PGF. If you are looking for the alternative PGF, now what is the resulting class? That is in fact 1 by 1 plus c into, in general you can write c into 1 minus s to the power a whole to the power theta for 0 less than theta less than infinity. And it is in fact in the limiting case when theta is infinity, it is nothing but it is a stable distribution, discrete stable. That is e raised to minus c into 1 minus s raised to the power a is known in the literature as the discrete stable, which was in fact introduced in a study by Stuttel and Manhan in a paper in the year 1979, which appeared in the journal Annals of Probability. So it was in that journal they have considered a discrete version of the stable, and you can see that all stable distributions are absolutely connected. That's well known. But a discrete version was introduced by Stuttel and Manhan by redefining the concept of stability, and the corresponding law has the PGF, which is given by e raised to minus c into 1 minus s to the power a. And you can see that whenever a equal to 1, what we are getting? Whenever a equal to 1, we will get the symbol Poisson PGF. So, or in other ways, your discrete stable law, you may be able to consider as a generalization of the Poisson law. And a lot of interpretation on that are already appeared in the literature. And now, if I am looking for the distribution generated by the DML, discrete linear family, so I may have to truncate it. So this is the case, and if I am looking for the HFS, then I will get this family, and if I replace my S by F bar X, I will get the distribution of the random minimum, and that is in fact given by my HFF bar X. Or in general, I may be able to write it as some G bar X. So I will get the family as G bar X is equal to 1 plus C to the power theta minus 1 plus c f raised to a x to the power theta by this one, where c and a are in fact arising from by DML or in fact the discrete linear cases. So you have c and a from there and theta from your discrete linear, or in other words, you can see that you have the discrete linear family is in fact a 3-parameter family which contains your a, theta and c, and whenever your c is 1, it will in fact belongs to the DML distribution. And whenever your a and theta and c are 1, it is nothing but it is simply your geometry PDF. geometric PM. So that the discrete linear family is in fact a very large family which contains these exponential, this geometric, and its different variants. And in equation 12, that is the equation 12 is nothing but it is the families of distributions generated through the discrete linear. And in 12, when theta equal to 1 and a not equal to 1, we obtain the survival function of truncated DML distribution. And when a equal to 1 and theta not equal to 1, we obtain the survival function of truncated negative binomial distribution, which is already studied in a paper which appeared in, I have already told the Journal of Statistical Simulation Computation. And whenever a equal to 1 and theta equal to 1, it will reduce to the well-known Marshall family. So the corresponding distribution.
Dear Professor, we have 4 to 5 minutes more.
I will conclude it.
Yeah.
Okay, sir. The corresponding relative distribution function of 12 is given by this one. And you can see that whenever I replace my fx by some certain distribution, so that is in fact the discrete linear generator family of distributions. And now I will look for the discrete linear exponential distribution by replacing my fx by fx in equation 13 by the exponential distribution. If I may replace my fx in equation 13 by the exponential distribution, I will get the discrete linear exponential. And whenever I replace my fx by in equation 13 by the Weibel pair distribution CDF, I will get the discrete linear Weibel family. So that is how the construction we have in fact looked into it. So these are the density functions of the family, and this is the general family. General family, you may be able to look for the hazard rate function. One may be able to, in fact, simulate it. So as a practitioner, one may be always interested in how we can generate the random samples from the distribution, having the CDF GX, and that you may be able to generate using your equation number 16. And these are the ways of simulation. So another method to simulate the random variable through random minimization or maximization, you can use this algorithm. So you generate a random variable n using truncated linear distribution with the given parameters a, theta, and c. So that is the first step. And then you have input the values of a, theta, and c. Then generate the random variable, discrete random variable, and having truncated discrete linear distribution that you can easily do. Then you may simulate x1, x2, etc., xn, where xi's are IID with the distribution function f. That it may be either in the discrete linear case, it is linear exponential model. The xi's are exponential. If it is discrete linear Weibel model, xi's are Weibel. So you can generalize it. Then you find the maximum of that generated random variable. So that will give a single observation on you. So you deliver it. Then you repeat this process, and that will give rise to the whole sample. Okay, by repeating the step 2, you will get the random sample, which has the discrete linear family of distributions. And now I come to my topic, that is the truncated discrete linear exponential. And in that case, if I may replace by fx by exponential, I have this is the distribution function, and these are the properties. And if you look at the structure of the graph, you can see that apart from exponential, a variety of shapes that you are getting. It may include a gamma type shape, vert type shape, and so on. So that is in fact the advantage of this compounding mechanism. And if you look for the shape of the PDF, you can look for the logarithm of the density function, and you can see that whenever if you are restricting your alpha in the interval 0, 1 and A in the 0, 1, you can see that the DLE, the discrete linear exponential, it is a discrete period. It decreases from infinity to 0, and these are the other possibilities. So that you have the other possibility. In the second case, you have whenever say alpha in 0 to 1 and A greater than 1, you can see that you will get that there is a single mode and so on. And whenever theta equal to 1, our distribution reduced to the Marshall-Olkin generalized exponential distribution by Stick and Kundu in 2015. And whenever A equal to 1, it will reduce us to the exponential truncated negative binomial studied by Raja. And whenever A and theta equal to 1, it will reduce to Marshall-Olkin exponential studied by Marshall and Olkin in the biometrica paper. And whenever your A equal to 1, theta equal to 1, and alpha equal to 2, it is simply the half-logistic distribution with the scale parameter lambda. So, or in other words, it is a very rich family of distributions. And when alpha tends to 1, the discrete linear exponential theta alpha lambda A reduces to the generalized exponential distribution that was in fact introduced by Gupta and Kundu in Australian and New Zealand general statistics. So you may get a number of distributions as special cases, and these are the hazard rate of the general family, and you can see that the hazard rate possesses various shapes, which is in fact a desirable property when one is modeling the lifetime data sets. And you can see that the parameters, that is your A1, theta 1, alpha 1, these are identifiable. You may be able to prove the identifiability of the distribution, and we have already proved the one. We have proved the identifiability. We can look at the other properties of the distributions, and I'm not going into this one. If one is interested in the estimation part, then you can see that the likelihood equation you may be able to derive, and you can prove the existence. We have already proved the existence and the uniqueness of the MLEs. You can see that under certain conditions, the MLEs are unique. And these are the simulation of the family, and you may be able to develop the time series models based on that. And this is in fact a real data application where we have considered a data visited by Bader and Priest. And this data we may be able to model with our distribution, that is DLE distribution, and when you are comparing the p-value, you can see that the DLE is more appropriate as compared to the Marshall-Olkin exponential, generalized Marshall-Olkin exponential targeted negative binomial, Marshall-Olkin generalized exponential, and so on. So all those things. So this in fact gives the application of this distribution, and one may be able to test whether the distribution from varies. That is, if you can see that there is in fact a similarity in the shape of Marshall-Olkin generalized exponential and discrete linear exponential exits, and to identify it, you may be able to test your theta equal to 1 and theta not equal to 1, and you can see that is in fact the test is rejected, and it will in fact test that at a level which is greater than 0.0363, the model DLE is better. So this is the other generalization, and with this, let me show. These are the generalized limit variable distribution, and these are the sum of the first related to this. I am not going into this. So one may be able to follow this and this is in fact by replacing the exponential by the variable distribution. These are the references by Adamides and Lucas, Bader and Price. I have already explained. Chandra on a mixture of probability distribution, Scandinavian general statistics, Christoph and Schreiber, generalized discrete distribution, Girish Babu, and Gupta and Kundu, Jayakumar and Shankaran, discrete linear variable distribution. This was the model that I was in fact mentioning this, which is a paper which appeared in Communication Statistics Simulation Computation. And Jayakumar and Thomas, Kuss paper, Raja Jayakumar and Stick, any family of lifetime models and so on. plain Devmore 1995 or discrete telephone distributions. So thank you all. Thank you very much. Any questions or comments, please? Any questions or comments? It's not audible, sir. Thank you. Thank you very much. Thank you. Thank you. Thank you.
Can you hear me?
Yes, yes, yes.
Okay. In fact, we have a very nice session, in fact, on distribution theory and related thing area by two experts in the area. In fact, Professor K.P. Jose and Professor K.J. Kumar. We are very much grateful to you, professors, for your deliberations in our conference. And we are always grateful to you, professors. Thank you so much. Fantastic works you are doing.
Thank you,
Also,
Professor Shinde. Thank you, Professor Shinde. Thank you very much, sir. Thank you very much, sir.
Also, we wish to extend our gratitude to Professor Shinde on behalf of the organizing committee of WSTA 2023. Professor Shinde, you have nicely managed this session. Thank you so much for chairing this session. Thanks a lot. Thank you.
Thank you.
Now we have a half an hour break for the lunch. Let us please join by 1:50 or 1:53. Well, now it is 1:23, 1:50 or 1:53. Please, Professor Kusubowiski's session. We can, I think, yeah, yeah.
Yes, yes.
In the afternoon, after lunch. Yeah, thank you all. Thank you so much.
Hello, good afternoon, Sadish sir.
Good afternoon, sir. Good afternoon.
Audible ആണല്ലോ അല്ലേ? എൻ്റെ സൗണ്ട് audible ആണല്ലോ?
Audible ആണ്, sir.
Okay.
Okay, sir. Sir, Kusubavisky join ചെയ്തോ?
ഇല്ല, so far not.
We are trying to contact Professor Kusubavisky. I think he has not joined it, isn't it?
So far, I think his name is not seen, but
Satish, I don't see him in the list.
Yeah.
Yeah, I'm not seeing him in the list of attendees here.
Yeah, I have to check where sometimes he will go through. Yeah, some other name because he's not in USA at present. He is in connection with some other. Yeah.
Let's wait for
Hello?
a few minutes. Let's wait for a few minutes.
Yeah, sir. Yeah, person. Yeah. Presently, he is in Poland, so he informed it earlier.
Do you have his WhatsApp number?
Yeah. I'm trying those.
Okay.
But we will not. Don't know whether he take the WhatsApp.
The
mic
should be on. Do you see me?
Okay, Professor. Hello, Professor. Good afternoon.
You can see me, right? And hear me.
Okay. We can see you. And hear you also. And we can hear you.
Technical issues. I'm ready to present if you.
Sangamita?
Yes, sir.
Yeah, that person. You please introduce the chair and
Okay.
do
Sure,
the
sir.
needful for the procedures.
Sure, sir.
Okay, so I'm disconnecting the phone. I'm going to proceed with the presentation then, right?
Yeah, Professor.
A warm welcome to the technical session 34. A warm welcome to the technical session 34 of WSTA 2023, which is chaired by Dr. M. Manoharan, retired senior professor, Department of Statistics, University of Calicut. His research area includes stochastic models in QS, inventory and reliability, phase type distribution, survival analysis, longitudinal analysis, and inferential problems associated with all of these topics, supply chain processes, and official statistics. He has 33 years of teaching experience. He is a life member of International Indian Statistical Association, Indian Society for Probability and Statistics, Indian Statistical Association, and also Kerala Statistical Association. It is an honor to have you here to chair the session, sir. And now, without any further delay, I welcome you on behalf of the whole organizing committee and kindly request you to take over the session. Over to you, sir.
Thank you. Good afternoon, everyone, on this online platform. And I'm extremely glad to have a very distinguished speaker in this session, technical session number 34. Professor Thomas J. Kusubowski, Department of Mathematics and Statistics, University of Nevada, Reno, USA. He's a familiar name in Kerala. He has visited many institutions in Kerala, including our University of Calicut here. And also he has been collaborating with several research scholars in Kerala. He's a very senior professor, published nearly 200 research papers and more than 5,000 citations in the Scholar Google. And his areas of interest is a very vast area, including probability theory, mathematical statistics, stochastic processes, data analysis, distribution theory, applied mathematics and finance, and so on. And today he would be talking on from slash distributions to the generalized convolutions. With the traditional warmth and grace of the state, let me welcome Professor Thomas J. Kusubowski to start his talk. Thank you.
All right. So shall I get started? Thank you so much for your kind introduction. And I'd like to thank the organizers of the meeting for invitation to present at the proceedings here. So I'm very happy to be able to do so. My presentation today will be about an interesting class of distribution. So it's on the boundary of distribution theory, actually, and probability. So as we will see soon from the presentation, actually, let me see if I hopefully be able to get the this presentation on the screen. It will take a little while. Just a second. Do you see my presentation on the screen?
Not yet.
No? Okay, wait a minute. So should I press something on the, let me see, where is this? Just 1 second. On the main website, the conference, is there a button to press to start the presentation? Which button should I press? The one with the arrow present now?
Yeah, the one with the upward arrow, sir.
Okay, I'm clicking there. Your entire screen. Okay, so I press that, and then I go to my screen.
Yeah, now you can take your file. Yeah, thank you.
Yeah, that is fine.
It's fine now.
Can you see?
Yeah, fine.
Okay, so good. Okay, thank you. So, right, so this is a joint research with my wife, Anna Ponorska, and also a colleague from Poland, Marek Arendarczyk, and it has to do with the distribution theory. So we're looking at a class of probability distributions called slash distributions. So we'll be discussing this concept of slash distributions and actually their unexpected relation to a branch of probability theory called generalized convolutions. So on one hand, we're talking about a very applied concept of the distributions. They are very popular generalized type of distributions. They pop up in statistics on many occasions. And on the other hand, this branch of probability, generalized convolution, is highly theoretical and very rarely, if ever, makes a way into statistical studies. So there are very different groups of people that work in these branches of probability and statistics with almost no interaction. And we were very happy to see some connections between those fields. So now those generalized convolutions hopefully will find more applications in statistics. And also the techniques from distribution theory now become relevant to deal with the general concept of generalized convolutions. So let me get started here. We're going to begin this journey with the definition of slash distribution or alpha slash distribution. which is what they generally called. So in this presentation, we're going to restrict exclusively to non-negative random variables, although the slash distributions are defined for any random variable, not necessarily non-negative. So we're looking at the random variable y. Here we'll assume it's non-negative. And we say that it has an alpha slash distribution if the following equation is true. So generally, it is the ratio of x divided by the power of u, where u is standard uniform random variable. So it's just a transformation. It's basically a scaling transformation, or the ratio of two random variables. So there is a relevant random variable x, the uniform random variable raised to the power 1 over alpha, where alpha can be any positive number. And with this procedure, we extend x to another random variable y called alpha slash version of the random variable x. So this probably started back in the 70s with the work of Rogers and Tukey, where they consider the slash normal distribution. I think in the original paper there was no alpha. Alpha was set to 1. It was just x over u. And generally this transformation leads to a distribution that is a heavy tail distribution or power law distribution, and it was used by Tukey in robustness studies. So since then, the concept has taken over, and there are now dozens of different types of slash distributions scattered in the literature. In particular, in the field of linear modeling, this alpha slash transformations is actually applied in multivariate setup, where x may be a multivariate normal random variable. So here we get like a scale mixture of normal distributions, and then it can be used in robustness to check the robustness of some statistical procedures in this setup. So multivariate slash distribution has been defined as well. It has also been extended to discrete type of distributions very recently in 2019, where the definition is slightly different. Slash Gumbel distribution, slash Pareto distribution, and so forth. These are just a couple of different examples of this concept. And when you Google slash distribution, then there will be like multiple, dozens of different papers will come up regarding this concept. So the slash distribution will play a very important role in this presentation, and we will see how this very naturally connects with the other concept of generalized convolutions, and how it helps in this area, because it allows a particular interpretation of convolution probability measures. So let's move on to the next part. So generally, we will start with the following question. So given n random variables, x1, xn, we assume them to be independent and non-negative. They have distributions lambda 1 through lambda n, and alpha is arbitrary value greater than 0. We also have uniform, bunch of uniform random variables that are mutually independent, and they are also independent of those x's. So the question that we ask that is basically, what can we say about the maximum of these slashed versions of the distributions. So we take each one of the x, we divide by the uniform raised to the power, and then we take the maximum of those random variables, and it will turn out that this maximum of the slash versions of x has something to do with what we call generalized convolutions that we'll discuss very shortly. So the notation, this is a standard notation here that represents the maximum of random variables. So in particular, we posed the question as to whether this maximum also have an alpha slash distribution. In other words, when we combine these alpha slash versions of x by taking their maximum, does it follow or not that this maximum is also of the same type? Namely, if there is another x independent of u, such that the maximum of those things has the same distribution as x divided by the power of u, or in other words, whether the maximum is a slash version of some random variable x. And if so, the question arises, what is this distribution of this x, if there is such an x? Or in other words, is it possible to invert the slash transformation, and given the slash distribution, can we actually recover x? So what is particularly interesting here is a connection that may exist between the numerators. So when we posing this question, we're asking, what is the connection between the x on the right-hand side, if any, and the xi's on the left-hand side? Because in the denominators, all these variables u are all standard uniforms, but we're asking about x. What is the connection between these things, if there exists such a connection? And also, does this connection exist for any random variables xi, or do these xi need to be very special? And also, we're gonna discuss going beyond the slash transformation. We can replace this u, but some other random variable, and ask the same question. So if we take the maximum of the variables on the left-hand side, where in the denominator we have IID random variables, is it always the same distribution as one such a ratio, with the same random variable in the denominator and some particular x? So down on the bottom, we basically showing what we're asking, right? So are there any random variables t for which this relation is actually true? So in this presentation, first, we're gonna focus specifically on the slash transformation, where the variable ti is precisely the power of ui. And then at the end, we will discuss some extensions for an arbitrary random variable t. So to get started with this, let's take a look at the structure of this maximum of random variables. So we start with the probability that the maximum of random variable is less or equal than t. That's the cumulative distribution function of the maximum. And because all of these variables under the maximum are independent, then that basically reduces to the product. That's the product of the respective probabilities for each term under the maximum. And then we're asking, is this product equal to the right-hand side, where we replace n probabilities basically by one probability where there is x and u. And we're trying to figure out if that's true, then what is this x and how it's related to the xi. Now, this relation can actually be stated in terms of Fourier transforms here, or the Laplace transforms of this. So, if this equality with the question mark were to be true, then when you work out of what these probabilities are, where the f and fx and fxi denote the distribution of those x's, then it's pretty easy to figure out those probabilities and write integral representation, just because these are mixtures. Basically, we take an x, divide by u. So using the total probability formula, we can pretty much write down this probability in an integral form. So we have one for the right-hand side and one for the left-hand side. And somehow this form, using integral representation, actually can be connected with the concept of the characteristic function for generalized convolution. So the formula under the integral, when we focus on the right-hand side, so this expression sort of, when you think about this expression, it turns out that it has an interpretation as a characteristic function, or actually Laplace transform, but not with respect to general, ordinary convolution, but rather with respect to generalized convolution. So for example, if in this integral we have, if it went from 0 to infinity, and then under the integral we have e to the power negative t times x instead of what we have here, then that would be the Laplace transform of the random variable x. So it turns out that this one is also a Laplace transform or integral transform, but for an operation of probability measure, which is not an addition of random variables. So that's how this connection has been discovered, and the slash distribution actually plays a crucial role in this discovery. So before we get to the concept of generalized convolution, let me discuss a little bit of notation that will appear in this presentation. So we already saw the notation for the maximum of two numbers, a and b. That's just this notation right here on the very top of the screen. There is a similar notation for the minimum. Then when we write x plus, what we mean by that is the positive part of x. So it's a maximum of x and 0, which is equal to x when x is positive and 0 otherwise. And this notation with the maximum extends to more than 2 values, so we can have a maximum of n values, and the similar notation applies to the minimum. Now the equality with the d means equality in distribution, that the two random variables have the same probability distribution. The p plus denotes all the probability measures on the Borel sigma algebra of R plus. R plus is an interval from 0 to infinity. Now we also have this delta x is basically a measure concentrated at the single point. So this measures concentrated at the single value of x play a very important role in the theory of these generalized convolutions. And we also use this scaling operator. So essentially, if we have a random variable x, that is positive random variable, and we have a number A that is also positive, then we can always look at the scaled version of X. So it's just a distribution of A times X. It's a scale family of distribution with the base distribution X. But if we want to describe this in terms of probability measure of X, then we denote the measure of AX by TA of lambda, where lambda is the probability measure connected with X. So this notation with TA for a constant A will be very common on the following slides. All right. So, and also the weak convergence of measures, or for random variables that will be convergence of distribution, is denoted by the symbol on the bottom of the screen. All right. So with this notation, let us take a look at this concept. The concept is somewhat technical. It's been studied in the 60s mainly by several people. So there is work of Bingham and Kingman back then, many decades ago actually, and then there was Polish mathematicians, mainly Urbanik, who was a professor at Wrocław University in Poland, and he sort of developed this whole theory of generalized convolution back in the 60s and 70s and so forth. And it has a niche in probability theory, but it's not a very popular concept, probably because of, it's somewhat disconnected from statistics. So I guess in recent years that this concept has been somewhat revived by the work of people on the bottom of the screen, who they published many papers in recent time devoted to this topic. But again, the applications in statistics were lacking. So as you can see from the definition, this concept satisfies actually five key properties. Probably the first four of them are the key properties that sort of parallel the concept of convolution. So think of the star as an operation of convolution. So when we say, convolution of two measures basically somehow correspond to operation on random variable. And the basic example is addition. So when we have X and Y, independent random variable, and we have the sum of X plus Y, it's essentially equivalent to convolution of their measures, lambda and mu. Now, when we extend the concept to other operations that are different than addition, then it's convenient to define the concept using operation on measures, and rather than operation on random variables, which is actually some of the disadvantages, because in order to proceed with statistical applications, we really want to have a description in terms of random variables. Otherwise, it's somewhat abstract and it's very unclear what this actually means. But anyway, let's go through some of these properties to kind of get used to this idea. So the first one simply says that if I have a convolution of any probability measure, lambda, with the probability measure concentrated at 0, so that's essentially a random variable equal to 0 with probability 1, then this convolution is invariant, is the same as lambda, right? So in terms of regular convolution, it's basically saying that x plus 0 equals x, which is kind of obvious for addition. But we require that this general concept of convolution actually satisfies the same kind of condition, that the convolution of lambda and the 0 concentrated measure doesn't change the distribution. And then equation number 2 has to do with mixture of measures. So you can think of it on the left-hand side, it's a measure corresponding to the random variable that is mu with probability p and some other v with probability 1 minus p. So if you take a random variable that is a mixture in terms of regular convolution and add an independent random variable to this mixture, then it's basically the same thing as if we took a mixture of those two measures, which basically means we take, this guy and convolution with lambda, so this random variable represented by mu, and add that one, and then take a mixture with the other one when we take the convolution of v and lambda. So this is a property that is satisfied by ordinary convolution. And when this theory has been developed, it was required that the same sort of condition be satisfied by the general concept of convolutions. And then the formula number 3 is saying, in terms of ordinary random variable, that if I take x times y plus x times z, it's the same random variable as x times x plus z, which is kind of obvious for regular convolution, and we extend the same concept to the theory of generalized convolution. And then there is a condition involving convergence of measures. So in terms of ordinary convolution, it's basically saying that if the sequence of random variables xn converges to x, then if we add to this xn some other random variable that is independent from the sequence, so xn plus z converges to x plus z, where lambda is the distribution of z. So the same sort of condition is extended to generalized convolution. So basically what I'm saying is that there is this concept that generalizes addition of random variables to another operation of probability measures that satisfies very similar conditions. And it's been studied by probabilitists since the 60s, but it's not very popular in statistics. I haven't seen a single paper in statistics that has anything to do with this concept. So, just a minute, something. Okay. So it should also be said that this generalized convolution actually is typically defined when we read papers from this area. It's typically defined through the convolution of point masses. So in other words, if I have a convolution of two probability measures, lambda 1 and lambda 2, and I want to find the probability of A under those measures, then it turns out that all I have to do is to take a convolution of point masses, delta x and delta y, evaluate the probability of A, and then sort of mix with respect to x and y. So I take a double integral of this guy with respect to the distribution lambda 1 and lambda 2, and that's how we define the convolution of these two measures. And in addition to that, most generalized convolution actually admit the analog of characteristic function, or it would be Laplace transform for positive random variable, which is convenient to work with in the space of this random variables following this generalized convolution. It's a very convenient tool, essentially because of formula number 2 or property number 2, which is a very well-known property of characteristic function or Laplace transform. We often work with this function because of the following property. If I have two independent random variables, x and y, then the characteristic function of the sum is the same as the product of the characteristic functions. So the same exact property holds for generalized convolution. There is this generalized characteristic function where the generalized characteristic function of the convolution of mu and v is precisely a product of characteristic function for the single components. And it also satisfies some other properties which are analogs of the ordinary characteristic function. So here we're looking at some examples of this generalized convolution. So we mentioned already that ordinary convolution would be our main example, where the characteristic function is the Laplace transform for positive random variables, and the convolution of 2-point measures is simply another point measure of the point x plus y. So if I have constant x and constant y, then x plus y is obviously the same thing as x plus y. But then when we move to other generalized convolutions, going beyond addition, then when we combine the point measures, it's not necessarily the sum, and it is not even necessarily a constant. It actually could be a random variable, which is not a constant, even though we take a convolution of 2-point measures. Another example is a maximum. Actually, a maximum of probability of random variables also corresponds to generalized convolution. It satisfies all these properties that we have listed. And in this case, the operation of point measures is the maximum of the two numbers. It corresponds to the maximum of independent random variables. Now, when we go to other examples of generalized convolutions, the interpretation is no longer as simple. So here is a particular case of what we are interested in, because it's very closely connected to slash distribution. So one particular convolution that received quite a bit of attention, especially in recent years, is called Kendall convolution. And for Kendall convolution, the operation of 2-point masses that is shown on the bottom of the screen is actually quite complicated thing. It's not a constant, it's a random variable. It's actually some kind of a mixture. So we take this pi 2 alpha, this pi 2 alpha denotes the Pareto distribution with parameter 2 alpha. And delta 1, that one is a point mass at 1. And we kind of take a combination of the two, which has to do with x and y. And on top of that, we attach like a scaling factor. The maximum x and y is a scaling factor that is attached to this measure. So it's a very, very complex description, and it's just for the point masses. It's totally unclear what is the interpretation for actual random variables in this setup. So this concept has been studied from theoretical point of view, but not much has been known about the actual operation on random variables. What does it mean to take a convolution of two random variables, x and y? Doesn't follow in a simple way from this theoretical description. So, so in fact, we were able to discover such a description with this research. So if we take two random variables x and y, they are independent, non-negative. Then the generalized convolution measure corresponds to this random variable that we call this, using the special notation, x plus y. It's not a regular addition. Actually, there is an interpretation in terms of these random variables, x and y, and it means this. So it's kind of a complex representation of these random variables, where we also have an independent uniform random variable U1 and U2 standard uniform that appear in this mix. So the main connection that I'd like to point out that has led to this advancement is this connection that is now in the middle of the screen. Namely, on one hand, we're looking at the CDF of the slash version of x. So x divided by the power of u less or equal than t actually can be related to the characteristic function of Kendall convolution. So in the theory of Kendall convolution, there is a characteristic function phi x with index alpha, and this characteristic function is very closely connected to this probability. And because of that, and the property of characteristic function, namely that the product of characteristic function corresponds to convolution of probability measures, obviously, once we have that connection, we can see that the product of the characteristic function on the right-hand side is related to the product of the probabilities on the left-hand side. And this product of probabilities on the left-hand side can be related to the probability of the maximum of random variables. So here is basically what I just said. We take the maximum of the x over ui to the power, that is the product of the probabilities. Now it becomes the product of the generalized characteristic function because of this connection, and because of that, we can actually say that this product of characteristic function is also a characteristic function, phi x, and this characteristic function corresponds to Kendall convolution of those x's. So this generally solves this problem and the question that we posed at the beginning, that there is a random variable x whose distribution is a convolution of those n measures, the Kendall convolution. And it follows that we have this equation. So the probability that the maximum is less or equal than t, when this maximum is the maximum of slash random variables, actually corresponds to another slash random variable, where we have x divided by power of u, and that at the same time we actually gave interpretation of what Kendall convolution actually means. All right, so let's take a look at this theorem. So it says that if we have a bunch of random variables x, they are all independent, non-negative, they have measures lambda, and we have a bunch of uniform random variables, standard uniform, independent of those x, then we actually showed that there is a random variable x that satisfies the formula on the bottom. So in other words, the maximum of slash random variables is another slash random variables. And we are able to tell what this x actually is. It has an actual interpretation of convolution of random probability measures, but not the regular convolution. It's not an addition of random variable. It's the Kendall convolution. So with this, we have actually able to give an interpretation of what the Kendall convolution means for random variables. So again, we have an interpretation of the convolution of two random variables. We're looking at this at the screen now. This is a formula for 2. There is a similar formula for n random variables and their Kendall convolution that is a little bit more complicated, but it's still an explicit expression. And there is also a way to write CDF of this Kendall convolution. Actually, it follows some sort of integral representation, which may not be easy to work out. But in fact, there is some explicit equation for this distribution function as well, which can be used in applications. And then lastly, I don't, how much time do we have? Are we near the end of the presentation? Do we?
Yeah, sorry, you're at the end of the presentation time. Yeah.
It's at the end of the presentation.
Yeah, only 1 minute left. Yeah.
Okay, so what I'm going to do is hopefully I made the point across that there is a close connection between slash distribution and generalized convolution. They are interesting examples of this Kendall convolution. All of this can be found in the paper that was recently published. I will show the reference of the paper for anyone who may be interested to read further about this. Let me just skip a little bit through these examples, and I'm going to get to the end of the presentation where we actually have a very similar result for other operation than slash. So in essence, what it's saying is that if I have a random variable t, that this random variable t has a survival function h of u, and this survival function satisfies some properties, some technical properties. So not every random variable satisfies these properties. Some random variable t satisfy the properties and some don't. In particular, u to the power 1 over alpha does satisfy the property and some others do not. But if it does, then it follows, then when I take the maximum of x divided by t, ti, then it actually has the same exact distribution as x over t. So it's a property very similar to the slash distribution. And we can also say what this random variable x is and how it's related to x's. So some examples for which this holds is the case of u to the power 1 over alpha, which is where it's a regular slash version of x. Another example is a power of beta random variable that connects with another type of generalized convolution. Another example is a power of gamma distribution with shape less than 1, again, that has interpretation of this x as a convolution of xi of the Kucharczak type, but also there are values of t for which this property does not hold for every x. An example would be Frechet distribution of t, or a finite distribution, discrete distribution of t with finite support. For that distribution, we also don't have x that satisfy this condition. And generally, the characterization of for what values of t this is always true is a general question to which there is no answer. So this is like an open problem where one would characterize the class of distribution of t. What are all the distribution of t for which this equation is true for every xi? For every xi, there is an x for which this is true. And the question being, what is the class of distribution t for which this is true? So for now, we know some distributions for which it's true. We know others for which this is not true, but we're not able to tell what is the totality of distributions that satisfy the condition. So that would be then the end of this presentation. There are some references on the screen. The paper up on top is the main paper on which this discussion is based. So you can find more details about what I presented today. And there's some other papers listed, some of them recent, some of them older, where one can read about generalized convolutions. All right, so let me stop here. I'm sorry if I used extra time. I apologize for technical issues.
Thank you, Professor Kuzminski, for your wonderful presentation on a very highly rigorous topic, but put it in very simple terms. I think one speaker has one audience person has already raised his hand. Banu K.S. Any question? Banu K.S. Are there any questions? We have don't have much time, but take at least one. Yeah.
Yeah, I don't hear anything. So anyway, yeah,
Okay.
thank you very much.
Okay. Let me ask one clarification, Professor Kusubowski. You have you were talking about the closure result of alpha slash distributions, closure of maximum. Does it
That's correct.
Does it find application in reliability and other areas wherein maximum is of interest, like parallel systems and those things? Is there any work in reliability connected with reliability?
As far as I know, the applications of this closure property, I'm not aware of that anyone has worked on this using the fact that it's actually closed under taking the maximum. But I think that because of that, that would be important application in this field, and somehow it also because of the close connection with the Kendall convolutions, and the Kendall convolution has this very strange interpretation in terms of random variables. Something to do with Pareto distribution, something to do with point mass distribution, something to do with maximum and minimum. So this, because of the complexity of the interpretation, it may be slow progress to get this Kendall distribution into statistical applications, but actually, because of the closure of slash distribution, so if you take the maximum, it has the same kind of distribution, and you can actually tell what the random variable is, this x, in the slash interpretation, that this x is a convolution of those xi, then this may have some implications in application, I think.
Okay, thank you. Thank you. Let us. I think we don't have much time left, so let us thank the speaker for his wonderful talk in the conventional way, giving that. Thank you. And
thank you so much.
Over to Dr. Satish. Yeah, please.
Yeah, Professor, it was a very informative talk. Thank you so much, Professor Kusubowski, for your deliberations through this international conference. And it's very, very informative, and also it's very much useful to the young researchers in the area. We are grateful to you, Professor. Once again, thanking you, Professor. Also, we wish to thank Professor Manoharan for chairing the session in a very nice way. In fact, there several have questions with regard to the presentation, probably for clarifications. They can contact Professor via email or other media. Let us conclude the session with once again thanking you, Professor Kusubowski. Thank you all. Thank you, Professor Manoharan.
Thank you again.
Thank you. Thank you. Yeah. Have a nice time. Yeah, thank you.
Now let us move to the next session, because we have a little bit late by 5 minutes, I think so. Vishwadhar, please introduce the chair. I hope Professor Sebastian has already there in the group to chair the session.
Yes, I am here.
Yeah. Vishwadhar, please chair and help the chair to run the next session in a very smooth way.
Okay.
Sure.
Okay, so thank you, Professor,
Welcome,
for giving the opportunity.
Excuse me, today?
Shall we start now? Are you hearing me?
Yeah. Please introduce
Yes,
yourself.
yes. So,
Welcome, everyone.
this session consists of 3 talks. One by Dr. T.D.P. and Manish Goyal, and the other one is Rodas Bharadwaj. I think all the speakers are present here.
Yes, sir.
So shall we start the first talk by Dr. D.P.? She will be talking
Yes, sir.
on study on dimensionality reduction technique in FORSD model. Am I correct?
Sir.
Or FORSD
Yes,
model?
yes, sir.
Sir,
So,
I will, Dr. Sebastian. Hello.
Pardon, Mr. Haidlal, are you talking anything?
Yes, sir. I would like to introduce you to the session chair.
Oh, I see. Okay, sure.
Okay. So, welcome everyone. Welcome again to this wonderful international webinar on recent trends in statistical theory and applications 2023. Myself, Vishwadev H, and I am here to introduce Dr. Sebastian George, sir, to chair the session. Dr. Sebastian George is the Associate Professor, Head of Department, and Campus Director of Kannur University.
Please correct us, Sebastian George.
Yes, sir. Dr. Sebastian George. And he was Associate Professor of Statistics at St. Thomas College, Pala. He is now the Associate Professor of Statistics, Department of Statistical Sciences at Kannur University from 2020 onwards. He is also an adjunct faculty of Department of Biostatistics at the Christian Medical College, Vellore. Also, he is the Pranab Sen Distinguished Visiting Professor at Department of Biostatistics, University of North Carolina. His areas of specialization are in probability theory, multivariate statistical methods, statistical inference, Bayesian inference, harmonic regression models in epidemiology. Personally, it's a great pleasure for me to introduce Dr. Sebastian George, since we both are from Avelikra and we both are chess players as well. So it's a great pleasure and privilege for me to introduce Dr. Sebastian George on behalf of our WSTA 2023. And I hereby invite Dr. Sebastian George to chair the session. Over to you, sir.
Thank you, Dr. Haidlal, for your nice words about me. Now I will introduce the first speaker, Dr. T.D.P. She is working as Associate Professor in the Department of Freshman Engineering, Gitanjali College of Engineering and Technology, Hyderabad. And she has a number of publications. And I request you to present this your work here, please.
Okay.
Dr.
Sir.
T.P., you have 25 minutes presentation and
Okay,
5
sir.
minutes for very perfect. Okay.
Okay, sir. Thank you. Thank you very much, sir. Is my PPTs visible, sir?
Yes.
Thank you, sir. So today my lecture on study on dimensionality reduction techniques in FORSD model, first order response surface design model. And coming to the contents of this lecture, first a brief introduction to the response surface design, and in that we have first and second order response surface design models and the necessity for the reduction of the model and the review on reduction of response surface design models and a few methods that were discussed here to reduce the dimensionality in the first order response surface design model with some illustrations. And coming to the introduction part, what is this response surface design and how it will be? There are V factors, x1, x2, so on up to xv. Each has S levels for experimentation. Let
you denote the response at the uth combination. Let the design matrix be defined as D is equals to XU1, comma XU2, comma so on up to XUV, where each XUI be the level of the ith factor in the uth treatment combination. The study of functional relationship between the factor combination to the response is defined as expected value of yu is equals to functional of xu1, xu2, so on up to xuv. So the design matrix representation, which is said to be a response surface study, and the designs that are used to fit this response surface called as response surface design, and the model fitting is called as response surface design model. And in response surface design, there are two models. First one is first order response surface design model. Simply we can call as FORSD model. The model representation is similar in the way of linear regression. That is, let us define y is equals to x beta plus epsilon be the first order response surface design model in V factors, where the response y variable is having y1, y2, so on up to yn be the vector of observations. XU represents the design matrix, which consists of 1, comma, XU1, XU2, so on up to XUV, which represents the uth row of the design matrix X of order n cross V. And beta represents beta naught, beta 1, beta 2, so on up to beta V be the vector of parameters which are involved in the model, and epsilon 1, epsilon 2, so on up to epsilon n be the vector of random errors. So here we are assuming this error follows normal distribution with mean 0 and variance sigma square I. And here the model in the generalized form is expressed as y is equals to x beta plus epsilon, and the first order we are going to represent this one as y is equals to beta naught plus beta 1 x1 plus beta 2 x2, so on up to beta v xv plus epsilon. So this represents the first order response surface design model. And to estimate betas, the parameters, we use here the least square estimate, which is defined as beta hat equals to x prime x whole inverse into x prime y. Then the estimated response at uth design point is defined as yu is equals to x into x prime x whole inverse into x prime y. And the variance covariance matrix of the response is given by variance of yu hat is equals to x prime x whole inverse into sigma square. And here the moment matrix, which is defined as x prime x for the first order response surface design model, is like this. So the first row, first column represents the total number of observations in the design matrix. Then the remaining part all represents the summation of xui, xuv, like this, so on up to. So we are going to represent this in matrix, which we are going to call as moment matrix. The notation is x prime x. And the variance of the predicted response at the uth point is defined as variance of yu hat is equals to variance of beta naught hat plus summation x square into variance of beta I hat plus double summation xii into xij into covariance of beta I hat, comma beta j hat. And continuation to the first order response surface design, as if you see the moment matrix x prime x is this matrix, and when we are imposing the restrictions on this moment matrix, then the matrix is reduced to this one, that is x prime x is equals to n, and the cross products will become 0, and off diagonal elements will become the elements of n and n lambda 2i. So here we are imposing the restrictions on the moment matrix, which reaches to the orthogonality. such as summation xui, summation the cross products of the design values will be equals to 0. And also let us define summation x square is equals to n lambda 2. Then the variance covariance of matrix x prime x can be reduced to this simplified form in the first order response surface design model. So hence the variance of the predicted response at a particular design point is defined as variance of yu hat, which is defined as variance of beta naught hat plus variance of beta I hat. So previously, if you see the moment matrix, which consists of rows and columns, and when you impose the conditions, imposing the restrictions towards the moment matrix, which reaches to the orthogonality, then it gives us a simplified form. Then coming to the second order response surface design model, so which is defined as y is equals to x beta plus epsilon, and y is the response variable, consists of vector of observations, and xu represents the design matrix, which consists of the first column takes 1 and the second part represents all the individual observations from the design matrix, and the second part represents the square of the observations and then the cross products. So this is the matrix that you are going to represent in the design matrix, and beta represents the beta naught, and beta 1 to beta v will be the individual, beta 1 1 beta 2 2 beta vv represents the square, and beta 1 2 beta 1 3 like this if you represent, then will represent it as cross products with the vector of parameters in the second order response surface design model. And here also epsilon follows a normal distribution with the parameters mean 0 and variance sigma square, so which consists of vector of random numbers. Then the second order model is defined as yu is equals to beta naught plus beta I into summation xui plus beta double I into summation xui square plus the cross product terms and epsilon. Then here also we are going to use the least square estimate to estimate the beta, that is parameters. Same formula, x prime x whole inverse into x prime y. Then the estimated response at a particular design point is defined as yu hat is equals to beta naught hat plus beta I hat into xui plus beta double I hat into xui square plus beta ij hat into summation xui into xuj. Then the variance covariance matrix of beta hat is given as variance of beta hat is equals to x prime x whole inverse into sigma square. So here in the second order response surface design model, the moment matrix x prime x is this one. So where I, ij, ijk, ijkl and all these are terms which are related to the sum of xui, xuj, xuk, xul over the n design points. So here the evaluation of the variance of estimated response in case of a second order response surface design model which is not in a simplified form because of its moment matrix inverse x prime x whole inverse. So here we are imposing restrictions on the moment matrix towards reaching to the orthogonality. So here we are imposing the conditions on the moment matrix, that is all odd power summations becomes zeros and summation x square become n lambda 2, x power 4 represents c n lambda 4, and the cross product square terms will become n lambda 4. Then the moment matrix is reduced to a simplified form like this. Then the inverse of this moment matrix is reduced to this matrix, where delta represents lambda 4 into c plus v minus 1 minus v into lambda 2 square. So obviously delta value also will be greater than 0, just like variance, and individual observations, variance of beta naught, variance of beta I hat, variance of beta ij hat, and the covariance of betas. So all these are represented in terms of the simplified form. Then the remaining few terms will be vanish due to this covariance in nature. Continuation to the above slide. Here we are going to extend this for the simplified version of the moment matrix in the second order response surface design model. So the variance of estimated response will become this equation. So this is the simplified version which results in the variance of the response estimated surface. But here my interest is on only first order response surface design model. So how you are going to reduce the size of the model and what is the necessity to reduce the size of the model? Here, when the number of factors increases, for example, if you say the number of factors are greater than 10, then the number of relationships between the combinations of factors and response also increases. As a result, the difficulty level of the analysis of the model also increases and it will be relatively inaccurate in higher dimensions. So with the increase of the number of factors, the size of the data set increases and the difficulty level of the model also increases. So which leads to the problem of dimensionality. Hence, the size of the data or the model cannot be reduced directly because it affects the model and analysis of the data sets. So reduction in response surface design model. If the number of factors or factor combinations is more, then only few measured which are of interest or important to study, then eliminate the insignificant factor combinations which are not affecting much the response. So that is the loss of information due to the elimination of factors should be as minimum as possible. So high dimensional data sets makes many mathematical challenges in fitting and give rise to new theoretical developments, so which reduces the time, cost, effort, and complexity by reducing its dimension. Most of the literature available on the reduction of dimensionality is related to reduction of size of the multiple regression models. Coming to the literature review on reduction of dimensionality, particularly in the multiple linear regression models, there are several researchers made attempts on the reduction of dimensionality of the data and on data models. Most of the research work done on the reduction of the dimensionality, which is related to the multiple linear regression models. So these are the various researchers or authors made attempts on the reduction either directly or indirectly. And particularly coming to the review on response surface design model, very few articles are found on the reduction of response surface model. Some of them are Kaufman, Homa and Saltelli, Chan, Venter, Vignox and Scott, McKay, Redis, Lace, and Steele. These people or these researchers made an attempt on the reduction of dimensionality in response surface model for a particular data related to engineering applications by using the general linear regression approach. But here we made an attempt to review in detail about some of the general reduction of dimensionality methods, for example, principal component analysis, factor analysis, multidimensional scaling, Bayes discriminant classification, and other methods like Sobol in 1993, McKay in 1995, Saltelli and Chan in 2000, Amin and Bhattacharya in 2014, and me and my supervisor Bhattacharya Garu in 2015 and 2018, we made to reduce the variables under the response surface design model particularly in the first order response surface design. For example, if you take the method under Sobal in 1993, he developed sensitivity indices to reduce the size of the model based on the variance of the estimated response. So this is the methodology that is under Sobal. So first, we need to consider the model in the form of a linear regression model, that is y is equals to x beta plus epsilon, which is similar for the first order response surface design model. Then estimate the variance of the response and also estimate the variances of each components di in the model. Then evaluate the ratios of individual component variance to the total variance. That is, so these are the S represents Sobal. S naught is equals to d1 by dj, S1 is equals to di by dj, and S2 is equals to dij by dj. So like this, so on. Eliminate the component whose Si values are insignificant. And coming to the...
Dr. GT, I think you are not moving your slides.
I'm not moving, sir.
Okay, okay, it's okay.
It is okay. Now it is in McKay, 1995. Is it okay, sir, now? So, McKay method. Consider an observed sample of information containing the response variable and its associated independent variables, that is the design matrix. And here we are assuming the linear relationship as linear only. Then evaluate the correlation between the response variable y to the independent variables and identify the insignificant correlation variables which can be eliminated with a little loss of information. So generally this McKay method is based on correlation between the response as well as the number of independent variables. Here, as we all know that the correlation coefficient indicates the strength and direction of a relationship between the two random variables x and y, and also it is having a capable of to estimate the main effect contribution of each factor of the output variance. For example, if you go for there are 15 observations, like 15 design points and 7 independent variables, and y represents the response variable and all xi represents the independent variables. And here constructed the correlation matrix with respect to response as well as the independent variables. Then these are the correlation between the response and independent variables is 0.092, 0.222, 0.316, like this up to so on up to 0.276. So these are the correlations between the response as well as the independent factors. Now, to reduce the dimensionality, whichever are insignificant in the model, that you can delete. For example, if you observe the correlation between the response variable and the first variable, and the response variable and fifth variable, that is 0.092 and this one, which are tested and found to be insignificant, means the strength of this correlation is very low. Hence, we are eliminating these two variables from the model. Hence, the model is reduced to only 4.
Dr. DP, your slides are not visible. It's not moving.
Not moving, sir?
Yeah, you are not moving.
Is it okay now, sir?
Now, yeah. The time is almost over.
Okay, sir. I'll be finishing, sir.
3 minutes more. Yeah.
Okay, fine, sir. Thank you. So here we are reducing the variables for x1 and xy because the strength of the correlation is very low for those two variables. And the next one is Salterly and Chan in 2000. So here also we are taking the linear regression model and we are estimating the standardized regression coefficient. Based on this, one can able to reduce the dimensionality. So I'm directly going to the illustration. I'm taking the same example with 7 variables. Out of 7 variables, how many variables that we can able to include in the model based on the regression coefficient that we can able to. Suppose if beta 1 and beta 5 are very, these two values are very low or very small, hence we can able to delete those variables x1 and x5, then we can able to include the other remaining variables in the model. So out of 7, if you take 2, so only 5 variables will be included in the model. So like this, one can able to reduce the model. And in 2014, Amin and Bhattacharya has attempted an attempt to derive the variance component indices through Sobal. So they have find the Sobal indices S0, Si, Sij and SAA. Based on these indices, we can able to reduce the model in first order response surface design model. So here I have taken the problem here with 18 design points and 3 independent variables. So when you able to calculate the Sobal indices for each variable, whichever the beta Sobal indices are very low, then we can remove those variables so that we can able to reduce the model. In 2015, Deepthi and Bhattacharya has invented the nested estimated procedure to find the reducing the number of variables in the first order response surface design model, and this is the methodology. Here instead of reading the steps, I can able to show the flowchart of this. First we are going to take the response, the collecting the information and finding the correlation between response and the factor, and we are going to able to construct the base nested model through general ordinary least square procedure, then estimate the model, then evaluate these residuals, check whether the parameters are significant or not by testing it. If it is no, then we are going to arrange the final model as the reduced model. So this is the factor, this is the problem that I have taken. It consists of 16 design points and 5 independent variables with response. Here we have evaluated the nested model and tested it. So these are all significant, so that we are including x2, x1, x3, and for the x4 variable it is insignificant, so we can able to remove this from the model. So here it is, the nested reduced model will having only 3 variables out of 5 variables. So better if you observe the R square value for the full model and for the reduced model will be almost nearly same. So for the full model I got 0.963 and for the reduced model I got 0.962. So with a little loss of information that you can observe. And coming to the another method which comes under Bayesian approach method in 2018. So here we taken y response variable and the regression y is equals to a plus bx. Then the methodology I'm going here. So how to reduce the first order response surface design model based on the likelihood function which is defined as y comma beta comma sigma square. And here the distribution parameters with respect to beta as well as sigma square. Beta follows a normal, and whereas sigma square beta follows multivariate normal distribution with the beta hat and x prime x whole inverse, and whereas the sigma square posterior distribution follows inverse gamma distribution. Then here through Bayesian we have taken the same example which I define in the nested approach. Using R package, we evaluated all 32 possible linear combinations. From this collected the highest posterior probability which corresponds to only 3 variables, x1, x2, x3 out of 5 variables. So generally full model will be in with respect to 5 models, whereas the Bayesian reduced model consists of only 3 variables, that is x1, x2 and x3 with the highest probability as 0.618 and with R square value is 0.962. So approximately all the methods will give the same R square value, near and same. Then I'm concluding. So generally, reduction of dimensionality of the model depends indirectly on the design points. Extending of the existed reduction of dimensionality regression models are not directly applicable to the response surface design model, and whereas variance component indices which are derived by Amin and Bhattacharya for the response surface are not applicable in case of rotatable designs because the simplified version will not be present in the moment matrix. The nested approach avoids the problem of multicollinearity, but it takes a time-consuming process due to estimation of parameters and testing its significance in each step of iteration. And especially for the Bayesian approach, the computation of normalization constant and evaluation of posterior distributions are very crucial steps, but we can overcome this with respect to the R programming. And these are the references. Thank you, sir.
Okay, time for questions from the audience. You can ask 1 or 2 questions, please. Dr. DP, you are deleting the variables whenever your beta coefficients are too small.
Yes, sir. I'm eliminating those variables, sir.
Yeah, eliminating variables. Is it the right procedure? You should consider the standard error of that estimate also. And you need to test whether that quantity is nearer to 0.
Yes.
Because even if your beta coefficient is 0, that depends on the standard error also. So I found that whenever your beta coefficients are very small, immediately you will delete that.
Based on that only,
the
I'm
right
eliminating.
procedure, I think. Yeah, you have to test it.
Okay.
By testing, even if your beta coefficient is small, if your standard error is too small, then there is a possibility for accepting the hypothesis that your beta is 0.
Okay.
Or beta is not 0, kind of thing.
Okay, sir. I'll go through it.
And similarly, you assume that your x prime x, the design matrix is always non-singular.
Yes, sir. Non-singular.
If it is singular, then what you will do?
Because singular means we can't able to move further, no, sir. Because compulsory inverse matrix should exist.
Is there any procedure similar to the ridge regression, or can you use some other kind of inverse?
Okay, I will go through that, sir. If it is singular, I need to check.
So, thank you, Dr. DP, for your wonderful presentation.
Thank you very much.
So we will proceed to the next talk. Our next speaker is Manish Goyal, Assistant Professor in the Institute of Integrated and Honest Studies, Kurukshetra University, Kurukshetra. I think Ms. Goyal is here.
Hello, sir. Good afternoon, sir.
Good afternoon.
Sir, actually, second talk will be mine, Dr. Kimya Tinani.
I see. But the order that's given by Professor.
Yeah, Manish Goyal has been replaced by Manish Goyal.
Is Dr. Bharadwaj here?
No, Manish Goyal has given the talk yesterday.
So,
instead of Kimya Tinani.
Hello, Professor Sadish.
Yeah, there is an interchange between Kimya Tinani and Manish Goyal.
Okay. So, so you can give the talk, no problem. Please start.
Yeah. Thank you so much, sir.
Yeah.
Good afternoon, all. Myself, Dr. Kimya Tinani from Sardar Patel University, Gujarat. First of all, I am very thankful to Professor Satish Kumar, sir, who has given me a chance to share my work. I am sharing my presentation. Is it visible, sir?
Not yet. Now.
Presentation is not so visible. Yeah.
Is it visible, sir, now?
Now it's fine.
Now it is fine.
Yeah. Thank you so much, sir. So the title of my talk is Application of Quality Function Deployment in Higher Education. Now, this is one of the research paper which is related with my research project, which is sponsored by Sardar Patel University. So the title of the talk is Quality Function Deployment. So what is Quality Function Deployment? So basically QFD is one of the total quality management tool which is used in various industries, including higher education, to ensure that customer requirements are translated into appropriate product or service features. So by applying QFD in higher education institutions, can develop programs, courses, or services that better align with the needs and expectation of their students. So this leads to improve educational experiences, enhance student outcomes, and increase overall satisfaction. So basically, this study has been used QFD as a tool for quality improvement of teaching quality and also for the benchmarking to improve their overall quality from higher education institutes of Gujarat. So basically, this study has been based on the primary data collection from which students are considered as the customers and teachers considered as a technical describer from some university of Gujarat. So by group discussion and brainstorming session, we have designed a questionnaire for data collection, and the data will be analyzed using the techniques of QFD in higher education institutes of Gujarat. And on the basis of these feedback, House of Quality will be developed, which highlights the major concerned areas of quality improvement in teaching and also highlights some benchmark where other institutes are more progressive. So total quality management refers to the managing quality, which involves every department to achieve excellence in business with regard to customer satisfaction. So basically, to meet the needs of quality in education, higher education institutes also adopted TQM principle to improve the education quality. So basically, TQM is an approach to management that focuses on achieving continuous improvement in the quality of products, services, and processes within an organization. So TQM in higher education aims to enhance the overall quality of education, improve students' learning outcomes, increase student satisfaction, and build a reputation for excellence. Now, QFD was developed in Japan in 1960 and brought to the US in early 1980. So QFD tool can be used in higher education institution to improve this teaching ecosystem and provide necessary facilities, thus improving student satisfaction. So Akao ETL, that is in 1987, studied QFD usage in Japan in 1986 by Quality Research Section of Japanese Quality Control Association. So QFD is a method of developing quality product services that aims to satisfy consumer and then reciprocate the consumer's demand into the desired results, parallel maintaining the quality throughout the production process. Agarwal and Sharma in 2014 they considered QFD one of the total quality management methods that can be applied for process and design improvement. So basically the characteristics of QFD are formalized way to keep track of all the customers' needs to make such that most of the important needs get special attention, It's a standardized approach to document and keep the track of the customer needs. We can employ technique that keeps the company's focus on what is important to the customer. So ultimately, a planning methodology that organizes relevant information and help companies make better decisions. And the features in the QFDs, we have to form a matrix format which is used for process input, where inputs are customers' requirement, and processing includes deciding priority items, finding out relationship, and comparing with the competitors. So that gives outputs as an action which will improve customer satisfaction. So basically, QFD is a methodology which is based on the development of a sequence of matrices, which is known as a house of quality. So it translates the customer's requirement into engineering characteristics to meet the new product design and helps how an organization will meet those requirements. So basically, it is a type of conceptual map that offers means of interfunctional planning as well as communication during the product or service development process. So this is a layout or structure of house of quality. First area, so here there are total 8 areas. So in first area, we write down the customer's requirement. Second area represents technical requirements, and third area gives relationship matrix between technical requirements and customer requirements. Then in fourth area, we can do comparison with competition, and fifth area will be action notes. Sixth area in which we consider comparison with competitions, and in seventh area we consider target value, and eighth we consider correlation, that is relationship between technical requirements. So this is a description for each area. Like the matrix is formed by first filling in the customer requirement, that is in area 1, which is developed from the analysis of voice of customer. So first of all, we will find what are the requirements of the students. And integration of technology, flexibility in selecting elective courses, hands-on practical session, timely feedback provision, then career counseling and job placement supports. So based on this feedback and students' requirement, I have designed the questionnaire. So first of all, I have collected demographic information. Then for making house of quality, I required what are their priorities. From requirements, priorities, 1 we have considered as a highest priority and 12 we represent lowest priority, because in each category I have divided all the students' requirement into 4 categories. Like first part I have considered as a campus facilities and resources. Then second part I have considered as student support services. Then teaching and learning aspect, academic program and curriculum. So this way I have divided entire students' requirement into 4 different categories. And from each category, I have just asked on 5-point scaling, like whether they are strongly dissatisfied to strongly satisfied. And I have given one column for rank your preferences, that is priority, where from teacher, punctuality of the faculty member.
Dr. Kimya, you
Yes.
have only 5 minutes more.
Yeah. Okay, sir. Thank you. And academic programs and curriculum. So with curriculum, first of thank you, sir.
Yeah, Dr. Kimya, your presentation is over now.
Yes, sir. Thank you, sir.
Okay, thank you.
Yeah.
So now time for questions.
Yes, sir.
I think it is only a presentation of the data that you have collected.
Yes, sir.
You do any analysis?
Yeah, sir. Actually, this method is still no one has done in India. This approach. This is one of the approach which is applied in Six Sigma methodology in DMAC in defined phase. QFD, quality function deployment. So actually, I got this as a research project sponsored by Sardar Patel University, and 4 to 5 months back, I have got this project. So that's why this is 2 years project. So based on this, good work should be done, because in out of country, so much research is done on this topic.
If no question, then let us thank Kimya, Dr. Kimya, for the wonderful presentation.
Thank you so much. Thank you, sir.
Thank you.
Thank you, sir, for giving opportunity.
Yeah. Our next speaker is, I think, there is some change in the Dr. Bharadwaj. Yeah, he's there. Okay. So, yeah, please, Dr. Bharadwaj. You have 30 minutes, 25 minutes for presentation. Dr. Bharadwaj, are you hearing me?
Yes. Screen is visible, sir?
Yeah.
Okay.
Please carry on.
Okay, first of all, I'm thankful to Professor Satish Kumar for providing this splendid opportunity and to be the part of this mega event. So thank you, sir. Thank you very much. The topic of my talk is exploring the performance of a cloud-based virtualized computing system. The agenda for this presentation is to introduce basics of cloud computing, to develop conceptual model for a cloud-based computing system, to find analytic solutions of the system model, and to discuss the future dimensions of the study. The entire talk is distributed in following headings. So the first is, what is the virtualization actually? So the single physical machine, say the computer, replaces many other machines performing different tasks on different platforms. So the concept of virtualization is very common in our day-to-day life. So the question arises, what virtualization is actually? So in the virtualization process, what we do, we try to replace various physical machines with a single machine. In other words, you can say a single machine can perform the function of various machines. So this is the technology that allow for the creation of virtual versions of, sometimes for the computer hardwares, sometimes for the operating system, sometimes for the storage devices, and also it can be used for the virtualization versions of the networks. So it enables the consolidation of multiple virtual resources on a single physical resource such as a server, and provide the ability to run multiple operating systems and applications independently on the same hardware. So what are the basic requirements for the virtualization? This is quite important to know what are the basic necessities to set up a virtual environment. Three key components to set up a virtual environment are the host machine, the guest machine, and the virtual machine monitor. They have different functions to perform in the virtual environment. The first is the host machine. This is basically the machine which is on our side as a developer of the virtualized environment. Then what we try to do, we have to develop the guest machines so that we can replace the physical machines. So it is the virtual environment that behave like the computer within a computer, but actually use software to run programs and applications. So the third one is how to achieve or how to develop the guest machines within a machine. So that task can be performed with the help of another software, that is the virtual machine monitor. Sometimes it is also called as hypervisor. So it is also a software that make virtualization possible by creating a virtual environment to run, create and manage the virtual machines. Actually, the functionalities of the virtual machine monitors range from creation of virtual machines to the management of the virtual machines, how they performs, what type of softwares, programming they required, and what type of functionality we should assign to different virtual machines, whether the functionalities will be dependent or they may be independent. Some basic examples of these hypervisors are the VMware, vSphere, Microsoft Hyper-V, and KVM. The kernel-based virtual machine is also the example of virtual machine monitor that is generally used by the people who prefer to use the open source softwares. Now the cloud computing environment, the CCE. So the cloud computing refers to basically the delivery of computing services. They may include, as I told earlier, that storage, the databases, the networking, software, or analytics over the internet. So the internet is also required for the cloud-based computing environment. So it is the platform that enable user to access and utilize these computing services remotely without the need of local infrastructure or the hardware. Cloud computing environments are used for a variety of purposes. They may include the web hosting, the hosting of websites and different other types of applications. Cloud computing environments are used. Another is the data storage and backup system. They sometimes also use the concepts of cloud computing. They avail the cloud computing environment to provide security to the data. The big data also for the processing and analytics of the big data, the cloud computing environments are required. Development and testing of different types of software also require sometimes the cloud computing environments to deal with the huge, the raised cost of testing. While testing or developing different types of software, they may require the alternative can be there. Either you use different physical machines to run a single software for its testing. So that involves huge amount of money. Another is you have a single machine and you create virtual machines within that machine and you run your the software and you can test the functionality of the software developed. So this require again the cloud computing environment. So generally they offer benefits such as cost saving, scalability, accessibility, and reduced maintenance overhead compared to traditional on-premise infrastructure. Example of popular cloud-based provider include Amazon Web Services, Microsoft Azure. Desktop is also very famous cloud-based computing system. The Google Cloud Platform is also used, offering different types of services to the users. This is the illustrative design for this cloud-based computing environment system. In this figure, it shows that we have, the two systems. First is active system. Another is taken as the backup system to provide the reliability. Here in the active system, the things representing this system, they are the virtual machine monitor in the lower S that generate the virtual machines. These are designated by VM1 and VM2. They may have different or same operating systems. And then with the help of these generated virtual machines, different types of applications can be performed. The two hosts are there, host 1 and host 2, and they can have either the shared storage network or they have different storage networks. So this is just for the illustration purpose. So, once we set up the virtual environment, then the effect of aging is also there. Though it is strange to, think about the aging of the softwares, but it includes the memory leakage. Some problems are there like the memory leakage, storage space fragmentations, crash, hang failure, data corruption, etc. These types of problems generally we face, and we, refer these problems as the aging of the system. So the aging cannot be prevented, but we can understand the causes and try to mitigate these effects. So one of the way to deal with such type of aging effects is the software resignations. It is one such technique that is used generally to deal with software aging. It occasionally stop running software, cleans its internal state and restart it. So this is used to increase the aging time of the system. It is proved cost effective and time effective method to delay the failure of a system. Some related studies carried out that use the concept of cloud-based computing environments are in the Khajehi in 2014. They discussed, the cloud computing system. Another is Shukumar 2020 discussed the role of virtualization and its significant impact on enhancing network performance to satisfy the requirements of customers. Causes of aging and its impact on the system had been studied by various researchers. Among these, some are cited here. Machita in 2012, they investigated the bug-related issues that occur, and the aging they defined in terms of the occurrence of the bugs in the system. Mohan and Reddy, in 2014, they established aging trends in the server virtualized system that suffer from performance degradation due to resource shrinkage. Abdullah in 2017 explored the concept of software aging and discussed various maintenance techniques to counter the aging effect of these softwares in the virtualized environment. To deal with software aging, different strategies had been discussed in the past studies. Among these, some are in 1995, Hank proposed a technique to deal with the aging effect of the software, and that technique is the rejuvenation technique. Trivedi in 2000 discussed stochastic modeling to evaluate the effectiveness of the proactive fault
Dr. Bharadwaj.
Yes, sir. Yes,
are you moving your slides? It is you are showing just the 5th slide, I think. You have a number of slides in your presentation.
Actually, from my eyes, I am moving the slide, sir. I am on the 12th slide right now.
Oh, I see.
Yes.
I don't know whether the audience are.
So should I rejoin?
Dr. Sadish.
Should I proceed or rejoin, sir?
You proceed, no problem. But I'm seeing only your 5th slide.
What happens?
Are you seeing the slide?
Yeah. Now what is visualization? Virtualization.
What is visualization? Yeah, that is only the 5th slide. Now it is 12th.
Now it is.
I think you are not moving the slide.
Now, okay. Is it okay now, sir?
Okay, proceed.
Okay, to deal with the software aging, different researchers, they have carried out their work, as I cited some of them. In 1905, Hang, they discussed the concept of rejuvenation. Trivedi in 2000 discussed the optimal time for the rejuvenation. In 2017, Umesh discussed again the resolution technique to enhance availability and performance of the cloud computing system, as well as application software that runs on a virtual environment. In 2021, Arjo discussed a methodology to deal with the software aging issues and discussed again the resolution policies to achieve better system availability. So from all these studies, one common technique that emerged to deal with the aging effect is the resolution technique. Different types of redundant systems are also extensively studied in the literature. Among these, some are cited here. Bhardwaj in 2017 analyzed a redundant system in which standby is subject to failure after specified amount of time. Roy and Gupta in 2020 studied coherent system with 2-unit cold standby system to optimize the reliability of the system. J in 2021 obtained reliability index for a cold standby repairable system using supplementary variable techniques. Now, using this concept of virtualization, we tried to develop a conceptual model for here. In this model, we consider a system that consists of two hosts. One host is operating in active state and the other host is backup host, which is in passive state, or you can say in the cold standby state. There is the single repairman, the maintenance engineer, who is present in the system and cannot fail while performing its duty. That is assumed here. All the virtual machine monitor resolutions and repairs are assumed perfect. There is a perfect network connection between both the hosts. Instant migration is considered because if you want to achieve the task of resolutions of the VMM, then the virtual machines need to be migrated from one host to the another host. Therefore, the instant migration is considered here. The failure of shared memory is considered only at the initial operating state. All the random variables included in the study, they are statistically independent and they are supposed to follow the general distributions initially. And for the simulation purpose, a particular distribution is considered for all these random variables. In this virtualized system, some random failures occurs while they may occur while either migrating the virtual machines or when the VMM goes into failure probable zone after passing some time. So similarly, the failure of shared memory and direct failure of VMM are also random in nature. In other words, we can say number of resolutions of virtual machine monitors are calculated using same argument. Again, using the Laplace transformation, the equations are solved mathematically and the expression is obtained. Finally, the profit incurred to the system model is also different types of cost are assumed: cost for repairing the shared memory, cost for resolution of the virtual machine monitors, and the revenue per unit uptime of the system is considered hypothetically, and then the expression for profit is derived. In the last, a simulation study is carried out, assuming all the random variables following the probability distribution, the exponential distribution. Just to represent these theoretical results numerically, the simulation study is carried out. The expressions for transition probabilities are obtained.
Now also your slide is not moving. I am seeing only, yeah. And now it is correct actually, yeah.
Actually, sir, when I put these in the full screen mode, then there may be some problem.
Okay.
Yes. So these are the expressions. After considering these distributions, we obtain these expressions. This is the discussion on the result, different parameters, and how we obtain the trends. These trends are shown here graphically. The mean time to system failure that varies with the different parameters. The values are here shown in the legends. This is the trend for the availability, and this is the trend for the profit. Availability and profit, they shows the similar trends. and the findings are highlighted here. It is shown here that the mean time to system failure, it increased with the increase in the rate of resolution of the virtual machine monitors and decrease with increasing the failure rate of the virtual machine monitor. That is quite obvious results. So these obvious results are obtained here. Similarly, the availability and the profit, they increases with the resolution rate of the virtual machine monitors, and they decreases with the failure of virtual machine monitor, as well as with the failure of the shared memory. So these are represented through these graphs, which I already have discussed. So these are some of the references that are cited in this study. And the future of this virtualization lies in the potential of this concept. The agility, the fragility, and the flexibility of virtualization put forward these concepts, on the forward stage, and various types of, the applications can be performed. And in the future time, we'll see various applications and, almost all.
Dr. Bharadwaj, I am not so good in this area.
Sir.
So I am also not asking too many questions to trouble you. Anyway, it was a good presentation. Thank you very much.
Actually, what we are enjoying right now is possible because of this concept of virtualization.
Okay.
we are meeting virtually, sir.
Okay. Professor Sadish.
Yes.
I think we are going to end this session.
Okay.
On behalf of the organization, I congratulate all. Thank you all for the three presentations. They could finish it in time.
Okay, sir. Thank you.
Thank you, sir.
Thank you. Can you hear me? Thank you, Professor Sebastian John, for chairing this session. And let us give a big clap to all the speakers of this session, Dr. Deepti, Dr. Tinani, and Dr. Bharadwaj. In fact, we have there is some time. Professor Rajagopal is here, the group, Cindy, to chair the next section. Okay, Professor?
Yes, thank you. How are you, Dr. Suresh?
Welcome, Professor.
Nice to see you and greet you for the occasion.
Thank you, Professor.
Thank you, sir.
Thank you. Thank you, Tinani. Thank you. Okay. Okay. Let us give. I hope now the time is 6:20. 5 minutes is there. No problem. We can introduce the chair and thereafter move to the session. Krishnaveni?
Yes, sir.
Yeah, please introduce the chair and help the chair to run the session in a very smooth way. I hope that Professor Prabir Kumar Das and Professor Shivasamy are there in the group. In the next speakers, Professor Das is here. I can see you. What about Professor Shivasamy? Whether he joined or not, I don't know.
Yeah, good afternoon. This is Professor Pravid Das.
Yeah, Professor. Yeah, okay, Professor. Okay, Krishnaveni, please introduce the chair.
Okay, sir. Warm greetings to all. We are moving on to the technical session 36 of WSTA 2023, which will be chaired by Professor Rajagopal AS. Dr. Rajagopal is the professor and head of the Statistical Quality Control and Operations Research Unit of the Indian Statistical Institute in the Coimbatore region, Tamil Nadu, which is headquartered in Kolkata, India. He is a trainer and a coach on Six Sigma Black Belt of the SQC and OR unit and a consultant to various industries like textiles, automobiles, healthcare, aerospace, and environmental science in India, Australia, North and South America. Dr. Rajagopal is also the lead auditor for quality, health and safety, environment, and social accountability of the National Accreditation Board for Hospitals. With great pleasure and honor, I cordially invite you, Professor Rajagopal, sir, to chair this session. Oh, you, sir.
Happy evening, and
Welcome, boss.
thanks for the introduction that is remembered and recalled what I had written some years back. And 36th session, I am so happy that despite my travel, I am now in another near Madurai from Varanasi. I want to tell that about more than 70 eminent people have come and addressed. And it is something, a great effort by Dr. Satish and his team. And university people have given full support to him to involve globally eminent people inaugurated by Dr. Prakash Rao. I am now on the Sunday evening. This is talking about theory and practice, the statistical trends. The institute is one place where both sides of the coins are practiced. And Dr. C.R. Rao and in the gold, it has value. When it is used, it gets a lot of results. Here we have two speakers, Dr. Prabir Das from Calcutta, and his research in e-commerce using multivariate analysis is in fact a very interesting one, because I had done some work on retail analysis, and the way that he will put forth how it is used, it will be very interesting, because of two reasons. This multivariate analysis in e-commerce is done in many ways. Market basket analysis, customer segmentation analysis, demand preferences. These are all some important area where e-commerce is done. Even the website, how it is presented should not irritate. There are variants, they do analysis between various websites of A/B testing, predictive analysis, and also create variants in the website itself, splitting click-through, how it works. There are conversion rate, how many click can become a conversion, and sometimes it's become a bounce rate. All these are very important in. After COVID, I find that all have learned how to work on virtual. Everywhere now, virtual conferences are happening. Even if there are possibility of coming physically, they prefer virtual. So the e-commerce in the multivariate analysis will not only help in analytical side, it is economic improvement of the country. At the time of G20, when we want to increase our exports, this accessibility of digital world will be very useful. In this, more than computer people, actually the decision makers are statisticians who can actually help how to outreach to customer. I invite Dr. Pradeep put his view on e-commerce and his research work. It will also help me to understand how it will be help in my domain of applications also. Can I invite Dr. Prabir Das and take your time, as we have up to 4:30. I think we started 5 minutes before. I welcome you, sir.
Yes, thank you very much.
To this session. Please, the audience
let me share the. Just give me a few seconds. Let me share this. Share. Yeah. Are you able to see the PPT? Let me make it full screen.
No. Yeah. It is.
Yes.
Yeah, it is fine. Yeah.
Yes.
Yeah, thank you, sir. Thank you very much. And I thank the organizer for giving me this opportunity to present our work. Before I start the presentation on these multivariate techniques in e-commerce sellers ratings, let me tell a few words about my institute. I am working at Indian Institute of Foreign Trade. We have 4 campuses: New Delhi, Kolkata, Kakinada, and Gift City, Ahmedabad. Currently, I am based at Kolkata campus. However, we need to go to any campus for teaching assignments as well as research work. The genesis of this work is the government e-marketplace. They approached me to develop a rating model for their sellers. There are 12,000 plus sellers. They have there are registered sellers of different sizes in the government e-marketplace, popularly known as GEM, which is responsible for providing the public procurement in the country for all government departments and government offices. They do make their purchases from government e-marketplace. So what they wanted, that let there be a model using which we can rate the sellers, the 5-star rating that you see, that we always see on the e-commerce platform, how we can derive that based on an objective method. That was their objective, and their then CEO and chairman, Mr. Talin Kumar, who is also my co-author now in this paper, which we have published, and another paper we are communicating, wanted that it must be systems and ratings are being used in this format. They collect consumers' review feedback score through a reputation system, mostly black box, we do not know. We can see only the ratings. In the literature, I'm not giving the complete details of that here. There are other models where people use consumers. In addition, in some studies, we also found that people do use platform-based function reporter. So consumers review, product attributes, and platform-based function reporter, when we are using, we can give a picture of ratings. Now, when we started this work for this government e-marketplace, through theory, we learned that adverse selection and moral hazards are the 2 important aspects of this rating system, as well as the public procurement aspects. Now, what is adverse selection? Adverse selection happens when we try to select the seller. That means at the stage of selecting the sellers before placing the order, there could be adverse selection due to information asymmetry. And what is moral hazards? Moral hazards happen after selecting the seller and placing the order. Maybe the seller is not capable of handling the order, the quantum of order that we have placed, or the quality that he has mentioned in the website, perhaps he is not able to deliver the same same quality goods or services. So there is a moral hazard. We get what we are supposed to get. Hence, what is required based on the academic literature review as theory, what is required that there has to be a rating system which is transparent, inclusive, efficient, effective, robust, and accurate. Now, it was really a tough call. Then what we did, that we identified certain variables which quantify some metrics. For example, we need to quantify delivery, reliability, quality. And this we found that can be quantified from the transaction level variables. And also using the feedback variables, user and buyer. Now, for some systems, user feedback and buyer feedback both are taken, and in some system, both are synonymous and only one feedback is taken from the buyer. Now, where it is B2B system, that means business to business, particularly when government department is purchasing from the GEM, the user and buyer are two different entities. Hence, it is required that we take both user feedback as well as buyer feedback. However, in B2C category of e-commerce, business to consumer, we may have only the user feedback, and user and buyer could be the same entity. Now, we have this kind of variables. Now, how we quantify this? Now, I'm coming to that in the next few seconds. In addition, there was another requirement, and this restriction was imposed by the platform, that look, when you develop this model and identify these metrics, make sure that all the sellers are getting equal treatment, in the sense that larger sellers must not get benefit out of the model the way you develop the model, and smaller sellers must not be in a disadvantaged position. Also, a startup must have equal level playing field with the very renowned or reputed large brands of sellers. So when this coverage aspect was done, we have excluded, they had a variable called coverage, where if a particular seller is covering large extent of geographical area in the country, they used to get higher score, and those who used to cover less area, they used to get lesser score. So we have excluded this coverage variable, that if we include this coverage variable, then we are having some differential treatment to the sellers based on their size or geographical extent. So let us exclude that. Now the question is how to determine the weights for these different variables, or the 5 variables that we have. Now for that we will be using principal component analysis, though predominantly principal component analysis is used for reducing the number of variables to less number of components. However, we have used it here for determining the weights. We have also used canonical correlation to find or test the correlation between two sets of variables. Now, do we really require transaction level variables and feedback variables, or transaction level variables and one feedback variable, maybe user, or another feedback variable, say buyer? This question we have addressed using canonical correlation. Then, as we do not have any target variable here or dependent variable here, and all the 5 variables are impacting the seller's ratings, we used k-means clustering and t-SNE, t-distributed stochastic neighbor embedding technique to validate our findings. I will come to that later. Now let us quickly explain how we have quantified the variables. Now delivery variable has been quantified using this structure where score 5 is assigned to delivery if it is within schedule, and 4, 3, 2, 1, and 0 as per this table. And this is obtained from the transaction level variable and from the platform's database. In all platform, all the sellers sign an agreement, and as per that agreement, they need to go to their business. And these variables are derived part from that agreement document and part from the requirement of the public procurement theory. Second variable that we have quantified is reliability, which is based on something called acceptance ratio. And acceptance ratio is eta. Eta is the acceptance ratio, which is defined as 1 minus number of orders cancelled divided by number of orders placed. So if number of orders placed is say 5 and number of order cancelled is 0, that means his acceptance ratio is 100%. So he will get the highest point. However, if number of order placed is 5 and all the 5 orders are cancelled subsequently, so it is 0 and his value for this variable would be 0. This is how it has been defined. Next is quality. Zeta is based on rejection ratio, and here this rejection is with respect to the buyer. So after getting the product ordered by the buyer, if he finds that it was not as per the description given in the platform, then he or she can refund that, or then if that number is that ratio we have defined QR by QO, that means quantity rejected by quantity ordered. So accordingly, we find this rejection ratio, and we have defined in this way that if rejection ratio is say 0%, he gets 5, and if it is more, then he gets less score. So these are the 3 variables which we quantified using the transaction level variables. And then we also collected buyer's feedback and users' feedback. And this buyer's feedback and users' feedback, here our assumption is that whatever we could not quantify using those 3 variables, perhaps we are able to quantify using the buyer's feedback and users' feedback. So we have 2 more variables, X4 and X5, buyers and users' feedback. Now we use the apply principal component analysis on these 5 variables, and whatever weights we get for each principal component, and where we find that which one is highly loaded on a particular observed variables, that has been assigned as weight of that particular variable. And this is the standard practice in the literature, in the among the academic fraternity, when they are using principal component analysis for determining the weights. So, and subsequent rating computation. So we found this W1, W2, W3, W4, and W5, these 5 values. And based on this rating model, which is a linear combination of these 5 variables and their respective weights, we can compute the rating for each seller. Now, once we compute this rating for each seller, the point is that we don't have any, it's not a supervised algorithm that we have a target and we have split into analysis sample and test sample, and we can verify everything using the analysis sample, whatever we have done on the test sample. But here we cannot do that validation. So what we did alternatively, we computed or placed we grouped the sellers based on this PCA, based on this k-means algorithm, and found that how many groups we are getting. Now, when we use the PCA and then we applied T-SNE visualization, now this T-stochastic neighbor embedding is another dimension reduction technique where it does that if the sellers are having some grouping on the 5-dimensional space, and then if we transform that from 5 dimension to lower dimension, say 2 dimension, then this T-SNE algorithm is such that it can retain that groupings, and this is very interesting. And T-SNE is actually can retain, and there are several studies in different areas, and it has been found that yes, T-SNE can retain when we transform from higher dimensions to lower dimensions. So when we see that this T-SNE visualization based on PCA and also T-SNE visualization based on k-means, whether a particular seller is having the same group or not, we developed a two-way table. Now, before we use that two-way table, this is how we define the 5-star rating, that 0 to 1 is assigned 1, and greater than 4 and less than equal to 5 is assigned 5-star ratings. Then we have developed this particular I hope I am within time, so I will be able to finish.
You have time.
Another 2-3 minutes. Another 2-3 minutes, I'll be able to finish.
You have time. You can take another minutes.
Okay, thank you.
You have to say.
Okay. So now what we are doing here we are having this classification based on k-means star ratings and classification based on PCA star ratings. Now we find that in this particular sample that we have considered, all the sellers are falling either 5-star category, 4-star category, or 3-star category. Now, a seller who is falling in the 5-star category based on PCA-based star ratings and k-means-based star rating. So there are 36 such sellers. And then PCA-based star rating 5-star, but 4-star in k-means 0, and 1 3-star rating, that is only 1. Similarly, PCA-based star rating 4 and k-means star rating 5, there is only 1, and PCA-based star rating 4 and k-means star rating also 4, there are 4 sellers. So in this way, when we compute this to this matrix, then what we find that 2 types of things are emerging. One is bingo accuracy, another is one away accuracy. Now, if we consider only bingo accuracy, that means whoever is in the PCA-based star ratings, whatever class it is falling, and whatever is in the k-means based star rating, wherever it is falling, that is around more than 95%. So, and if we also add one away accuracy, that means in one classification, say it is 5, but another classification it is 4. And similarly, or maybe one classification it is 4, star rating 4, and another classification is star rating 3. So then also it is one away accuracy. So if we add that, then it becomes more than 98% accurate, this particular computation. Now, we also propose a generalization to it, that not only 2-dimensional metrics, we can have multi-dimensional, as we have different unsupervised algorithm. say self-organizing map, DB scan, and so on. So if we use more and more algorithms, and if we generalize it, and then we see the performance, then if the accuracy tends to the higher side, then perhaps we can reasonably be sure that the model that we have developed is giving a true picture of the seller's intrinsic worth. So what are the applications of this rating? Sir has already mentioned that in the introductory comments, that there are several applications of multivariate techniques, in fact, in e-commerce, including market basket analysis and other techniques. But this is a very specific, and it is based on the practical requirement of a particular platform that we have developed it. So rating scores and 5-star rating system, which is very prevalent in majority of the e-commerce sites, where we can obtain and quantify the reputation of sellers. It can be used as a filtering criteria by the fintech firm for sanctioning the working capital loan requirement of the sellers. So, and in fact, there is a product developed by GEM, known as GEM Sahai, where on a real-time basis, they shared the data with their partner fintech companies, and they sanction the loan within a very short period, because all other documents they are having through the platform. And once they get the ratings, so based on these ratings, their decision making can be expedited, and the whole process can be made end-to-end digital process, and it can expand the business, generate more employment, and protecting the buyer's interest, as well as expand the business of the sellers. Well, there are the use case is the government e-marketplace, and GEM Sahai is another one. Maybe more inclusive e-com ecosystem we can have with this. It can be replicable, and it is in fact replicable with minor changes is required for some other platforms, particularly B2C. I was talking to higher officials in the Walmart, Flipkart Walmart, where he found that yes, it could be even applied to B2C, maybe with minor modification. And then ONDC platform also, it could be applied. And maybe, in fact, we have presented this in the G20 seminar, part of University Connect program, where we propose that perhaps this could be replicated by other nations as well. Thank you. That's all from my side.
Thank you, Professor Dr. Robert Das, for highlighting the need for principal component analysis, and came in clusters, particularly in the business applications. It is very, very important that I happen to do some analysis using principal components. It was very difficult to make understand even the journalist, because they used to do the descriptive analysis. This sort of dimensional reduction and principal component factor analysis and score-based discriminant analysis are becoming more and more important in pharmaceutical trials, which I did and published in one of the reputed journals for chronic kidney disease. And the product was also installed. It was so much informative that the role of e-commerce, not that digitally people can access it, then the result orientation of getting the turnover and promoting India abroad requires certain analytical decisions. And the way you have put forth key distribution embedded neighborhood string and I will also try to use it. I request if any of the participants online are physically present, if they have any questions to Dr. Prabir Das, please ask. Otherwise, I have a few interactions with him. I leave the platform open to audience to raise questions and interact with Dr. Prabir Das for sparing his Sunday evening time with us. Please ask your questions, please. I think there are no questions. It may be that they can put their hands up and put it in the chat box or contact you by email address. I want to say a few things clarifying with Dr. Prabir Das. This medical tourage in India is gaining importance. Now there are, I did some work on Indian defense e-commerce program, and it was done in how MSME can participate. And as a result, in southern part of India, defense corridor started, and a few Odisha, Coimbatore District Small Industries Association started the defense corridor also and manufacturing wing. I want to ask you about healthcare industry promotions, not product. I'm talking about services. Do you suggest that there are famous service providers in India, especially in cardiology, at quick accessibility and affordability without any waiting time? How to promote this in abroad, particularly developing and developed countries where it is taking a lot of time, waiting time is more? Is there any access in e-commerce platform that medical specialists can register themselves, like Health Plus is there, but any other platform that you suggest? How it is scope going on? The question is how the doctor can sell themselves abroad.
Yes, sir. Should I respond on this?
Please, yes, please.
Sir, the way I understood the problem, in fact, the way we can rate the product space, the service space is little more complicated. Now, in the GEM platform itself, we do have services. They do provide services. Say we can hire the cars, etc. Now, this services data, when we started this work in 2020, there was no adequate data at the time. The first requirement is the data. And with reference to healthcare, let me tell you that the point that you have raised is what is the need of the hour. In fact, there are many platforms, those who are providing medicines, online medicines, and they are also coming into online services, so doctor services. So where we can consult the doctor, and sometimes they are giving a complete package, say for diabetes package, complete diabetes package, that this is how we have to do it, and this is how if you become a member of this particular platform, and in this package, then you get these services, say A, B, C, D. These are the services you are getting. Now the question that you are raising, that how we can scale it, maybe scale it, and we can go beyond the border. That is one aspect, perhaps the way you are raising the question. Another is that how we can probably rate these services. Okay, now if I understood that in that way, now first part is that yes, the
not medicine alone and consultancy. There are a lot of time taking for procedures. For example, hysterectomy procedures, or even cardiac procedures, or even the dialysis procedures, transplant procedures. These procedures, the waiting time abroad is so high, and India would definitely reduce the cost and accessibility. Whether these services can be, and there are very veteran, and I have been working with many of the well celebrated specialists, but I find they are not outreaching the world how this platform can be used for procedures also.
Exactly. So there could be processes, well-defined processes. That is what is the first requirement, that we will define the processes.
Okay.
And then some of the things could be even AI driven. Now, when I say that AI driven, so it has to be not just automation, but it has to be data driven automation, so that the system would be able to make decision based on the data available with it. So when we have similar AI driven processes, perhaps this would be further easy,
Okay.
and a person requiring this service sitting abroad would be able to get majority of the consultation through online, and then he can make his mind that yes, I can now avail the subsequent services which require physical interaction, and can take this particular service.
The GEM is having with any collaborative arrangements with developed countries in Europe or US, or even developing countries like Bangladesh, Korea, or Sri Lanka.
They have received, what I came to know from the CEO, then CEO, that they have received some request, and perhaps that is in the discussion stage to replicate similar thing, because only few countries in the world are having similar platforms. So the way our UPI is getting acceptance in other countries, and GEM is similarly getting acceptance in other countries.
Okay, it's wonderful. I did some work on CRO, the clinical research organizations, but mostly they are abroad. This patient recruitment and volume of patients and varieties of diseases and presenting conditions are more in India than abroad. But most of the trials are happening and funded from abroad. I thought this platform should be more productively used for addressing the sample size and variety of conditions, patients, and the volume of patients. These things can be definitely sold abroad, that they can be collaborated with the GEM platform. I will discuss with you further. Can you share your email address on the chat platform?
Yes, sir. Yes, sir.
I
It's
think
PK Das. Let me share it here itself.
PK Das at
IIFT.edu. I'm writing it here.
Okay.
PK Das @IIFT.edu. Yeah, it is there in call messages.
Okay. PK Das at IIFT.edu. So I am very happy to hear your updated knowledge on this area.
Thank you, sir. In fact, Professor Bimal Roy also went through this, and he appreciated a lot that yes, this kind of study must be done. And in fact, his residence is very near to my home in Calcutta, and we shared the same market from where he also.
Yes, I will discuss with him that I discussed with you in the Cochin University platform, and he will definitely, as a former National Commission for Statistics.
Yeah,
and he will,
he's also in my PhD students doctoral advisory committee, so we always receives his guidance.
very good. I will have some more interactions with you.
Sure, sir.
Some more people in the medical science, and then we'll see how we can start working on first relationship management.
Sure.
And analytical for growth. Now we need a good outreach. That I'll also discuss with Dr. Bimal, and because the most important thing is how do we keep our values on trust and reputation abroad.
Right.
This is one area where we can also brainstorm. Though individually we have a high trust and high reputation, individually with a lot of recognition, but as a country, it is getting varied. For that reason, I wanted that at least a few individuals can use this service of e-commerce and then outreach Indian medical tourism abroad. Nice to interact with you. And not only this, there are some more areas for MSMEs that also I will discuss with you. MSMEs, startups also I will discuss with you, because their knowledge is more into the day-to-day working capital management, but their accessibility in e-platform and web designing is very, very limited. And people like you will be very helpful for them, and we will discuss further. Thank you so much for interacting your time and presenting how dimensional reduction can help. I enjoyed your lecture, and I will keep in touch with you. Thank you,
Sure, sir.
Dr. Prabir Das.
Thank you.
Thank you so much. Let us give a big hand to him and show the hands up in our message box. I have started already. Thank you so much. Dr. Satish sir, the next session is for Dr. Sivaswamy.
Professor Sivaswamy.
Yes.
Whether Professor Sivaswamy has joined by this time? No? Not in the group, is it? He is not responding to our mails, and other media will be contacted him last day also. I don't know whether any problem with him or any network issues, or I don't know.
Okay.
Anyway, we expected him to join by this time.
Okay. Now we have time another 20 minutes, 25 minutes.
Yeah, boss. No, 25 minutes.
36A session going to start. Can I take this opportunity to tell a few words in the platform who are all there? About 18 people are there. Can I tell few words?
Yeah, boss. That's fine. That's great, Professor. Please.
That's what you also made a message to me. See, very important for the statistical research in India. It is well acknowledged abroad because we have the chair in United Nations by Dr. Jaishankar, our Honorable Ministry of External Affairs. So statistics in India is definitely well appreciated than any other research people from the statistics department of universities, and also from the institutions like foreign trade. There are institutions like Entrepreneurial Development Institute. There are institutions like Market Research in Chennai, financial institutions, and commodity trade in Bangalore. I happen to work with all of them, but still the gap between the domain experts and statistical experts are very wide. I need to tell this, that the wide, in the sense that one, they are afraid of any sort of analytical approach. Afraid in the sense their feedback is, it is above their head or above their perceptions. They want to see that statistical people speak their language. Their language is what? Example, I was talking healthcare professionals, I was talking MSME professionals, and I was talking financial professionals. What is their language? Healthcare people, they are very much bothered about what is the aim of the research. They are much confused about the aim. They write too many aims. They write too many objectives. They don't tell the problem statement correctly. When I say they, most of these students upcoming PGs, postgraduates from medical institutions, these statisticians can play a predominant role with them in helping their thesis, that it is taking and accepted in the index journals, Scopus journals, and World Congress. So the statistics department, I find, can work with other departments, which Cochin University is already demonstrating. One department you can work with bioinformatics and biomedical and bioengineering and bioinformatics. These areas, it doesn't matter whether you have their knowledge or not. Today, you can always read in ChatGPT, Google. A lot of platforms are there, and even textbooks are there. You can interact with them. Take that open mind of working with the other domain. This is one thing I will tell for the youngsters, because when we started in ISI, we were put in industries where we don't know anything about that industries. I was put in an industry in Baroda, where I don't know anything about gases there those days. What is petroleum gas? We don't know. So we have to read physical and chemical properties, inflammations, all this. Then it helped me a lot to take further work in Indian Oil. When I was taken as a faculty, it helped me a lot. So first thing I say, speak their language, read their domain. You know what statistics can do. If you read their domain, you can make the aims and objectives properly. They are much confused. They raise questions, but they themselves do not have answers. So aims and objectives is one area where we can tell them clearly. It's a management concept of writing the problem statements. And it is needed for thesis also, for PhD students also in statistics. Second important thing that I would like to, I'll take 10 minutes, then you'll have another 10 minutes for interactions. Second important thing is that most of the domain people understands simple visualizations. Like I will say, they are in a very rudimentary. They don't know what principal component Dr. Pubida stopped. They don't understand what is loading plot, and they don't know where is the origin there in that loading plot. If I show you the loading plot to them, they will understand, they will take much time to understand where is zero, because they always see zero in the left bottom corner. The loading plot is at the center. So they don't know how the loading plot and the aging plot, they are totally ignorant of all this multivariate analysis. How to promote, how to make you tell them in a simple language, in their language. This is very important. That what I am trying to say, their visualization is mostly restricted to bar diagram, line diagram, pie diagram, and percentage analysis. They don't know about even the next analysis variance, and they know p-value very well. Most of the engineers know p-value, but there are a lot of controversies about the p-value and about the sample size also. So I want to say, in the study design, statisticians can make a lot of questions to the people who are conducting clinical trials, who are conducting industrial experiments, who are conducting agricultural trial. I have taken a work in agriculture in a cotton crop. I have just taken, and tomorrow we are going to discuss. I am sharing that it took a lot of time for me, 6 months, to convince the biggest corporate and the United Kingdom collaborators why the cotton imported from abroad, Pima cotton from USA, Nile cotton from Egypt, and even African cotton, it is all having a very good price, and many people are importing into India, paying a heavy, Dr. Prabhudas also knows, paying a heavy imports, and there is a export commitment also, paying extra price. And also lead time is more. They have to store in a godown of not less than 400 by 700 feet, keeping bales and bales of cotton. If it is done in India, how to grow in India? Organic cotton, high stable length, with the lower short fiber content, you need a proper study design. UK government is prepared to help me, and it took 6 months for me to get the support of corporate and then get the support of agricultural associations, even the support of the farmers. To get 4 pieces of land of 400 square feet, I have to talk to them a lot because they want to do what they have been doing. This is what is happening in every domain, that they ask immediately the sample size and time. When the result will come, how many people you want for the patients, for the agriculture, and also for the destructive testing, and also for the studies related to customer survey. Hyderabad, we use it as a platform for all e-commerce new product introduction. Hyderabad is used in India. I'm not sure, Dr. Pravidas may be knowing. And in the Middle East, I use Saudi Arabia for a trial test marketing. Hyderabad, if it's successful, it will be successful everywhere. The Reliance also tried there itself, the Reliance retail chain. What I'm trying to say, this area is a big gap of sample size selection is in the study design, and the time factor, how long you should test a piece for giving warranty and guarantee. This is becoming a big issue. Though we have solutions, they don't know that this has got a scientific model. I have to do a lot of work to them to speak their language. Then it happens. So youngsters, I wish that you take good importance on study design. What I mean by study design is how much to test, how long to test. It can be by, there was one study I did recently, it came from Hong Kong Chinese. It was a survey. They want to publish in International Urogynecological magazine, journal. It's a high impact journal. This was done in Hong Kong by few healthcare specialists on women's urinary incontinence issue. They have decided everything with a sample of 353 people who have visited in single outpatient center. They invited them, asked them some questions, tools. Then immediately they concluded. Came for the review. This sort of large sampling survey, how much should be minimum taken, how the wide variation is taken, how the proportions are taken, so that the conclusions are valid enough. This area is, they always take that higher the sample, better the conclusion. But it is not always the case. In robotic surgery, you don't need high samples because it is very precise and accuracy. In CNC machine, you don't need, in Huzur CNC machines, there are 700 CNC machines. They have producing Apple phone, and it is very, very specific to micron accuracy. And who will pay for destructive testing of high incidence of production? The CNC machine produces more than 1,000 pieces a shift. 700 machines are there. Then how many samples to be taken? It's a big issue in the statistical quality control in Huzur. What I'm trying to say again, sample size, destructive test, how long to take. This is one important area that the statisticians can play a dominant role in their research. This itself will do. You can write one article on aims and objectives alone and another article on design alone. You may even get PhD. Third one I want to stress is about literature survey. What is the need of the study? What has been earlier done, that has to be studied from the domain literature survey. And the way statisticians can access the digital market digitally, because they are used to software, SPSS software, they are used to SAPs, they are used to STAT, Minitab, and Excel. When they are used to it, their navigation skill is very high. What domain people will take 1 month, the statistical people can do the literature survey in 1 day. I have done literature survey for some new domains, and they were surprised that I got accessed. I gave training to many university students also, how to get access to literature survey. Why I insist this for youngsters is, this literature survey will keep them mum. I need to tell the secret, how statisticians can make their impact in the industry. Do a good literature survey and get the model, which sometimes due to their expertise in the domain, they may not accept what statisticians are saying. But if you are quoting from the literature, then they say where from it is taken, what exactly it is taken. So the literature survey is, in those days it is very difficult. We have to run through 7th floor in ISI and 6th floor to find out which book is telling what, and then it was all hard copies. Now in recent 5 years, I find you can get access to all literature survey and get the journals, and then can interact very well with the people in the domain. This is one area where you can do meta-analysis of your area and then tell what exactly we are trying to do in our aim. Then it makes a good fortune for the statisticians, particularly researchers, to help the other domain people, whether they are in retail, manufacturing, or service. Then comes analysis. I was so happy that in e-commerce, principal component analysis is used. T-distribution embedded neighborhood is used by Dr. Prabir Das, and we missed Dr. Sivaswamy from Botswana. He had done how web design can also help. He has studied ABOS, but I was very much interested in knowing what is that ABOA method. It is not there in the literature. That particular word he has only coined. He has not discussed that. We missed him. We need to interact with him. So, but I find that this session of marketing, not only the methods that we are studying, also the subject needs marketing in other domains, particularly in research areas. That is one important area. What is the analytical method that we are going to take it up? Mostly they are talking about, they can't understand the word relationship. They know relationship is some sort of price and demand. But technical relationship of rank correlation, Pearson's correlations, p-value of correlations, covariance matrix for principal component, what are all the significance of it, how it reduces the dimensions. The previous session people were also explaining how we can do second order study in the reliability analysis. This is very, very important area where finer cut is given in the response surface methods. So this is one area. What descriptive analysis we can start with. Then Second thing is what diagnostic analysis we can do. Diagnosis, I mean, with respect to the key performance indicators, KPI. Third is our predictive analysis, which the principal component analysis will help, which are all the good predictors which are related to other variables. From these predictors, we can tell which are significant. Then using various regression models and AI, definitely this predictive analysis will help them. But they means domain experts are very much in need of it. But we have to put in their words. Then comes the prescriptive analysis. That's the conclusions. This area is something that they are already prescribing, but without the basis of data-driven solutions. This will help a lot in our approach. And I am so happy that this was made as a recent trend with theory and application together, and giving Sunday evening for e-commerce and how to reach customers. It's a good session. I appreciate for making 36 and then 36A separately. Thank you so much, Dr. Satish. I think I can conclude here, wishing the 4-day sessions all success and congratulations. Can you conclude, Dr. Satish?
Seems some technical issue, perhaps.
Yes. Dr. Satish is not there. I think there are something. Dr. Satish, I concluded.
Yeah. There is just a network issue there. That's right.
Yes.
Okay, Professor. Okay, Professor. Thank you, Professor. In fact, we are very much thankful to you, Professor, for making a very excellent session. In fact, the use of statistics, and it is very much beneficial to the young researchers, especially the talk done by Prabir Das is also very useful or a very informative talk, and helpful for the young researchers to attract in such types of areas which are more flourishing now, with the need of the hour, in fact. Thank you so, and also, Professor, you have given a motivating several things. We are very much grateful to you, Professor, for giving that this much, making the chair and as a chair, making that session very vibrant and very informative. Once again, thank you, Professor, for chairing the session, and thank you, Prabir Das, Professor Prabir Das, for giving a very nice talk to the audience. We speak in this conference. We need your help in future also.
Thank you.
Thank you all.
Thank you, Professor. Thank you. Now let us move to the next session. The next session, Bhagyalakshmi is.
Yes, sir.
Please to introduce the chair and do the needful for further procedures.
Sure, sir. Am I audible?
Yeah. Audible.
We are moving to 37 technical session of WSTA 2023, which is a special invited session that shall be chaired by Dr. K.M. Shaktivel. Now, Dr. K.M. Shaktivel is a professor to the Department of Statistics, Bharatiyar University, India. His areas of interest include statistical inference, statistical modeling, artificial neural networks, and statistical quality control. He is a life member of Indian Society for Probability and Statistics and Indian Bayesian Society. He has a lot of publications, including a generalization of draft exponential distribution properties and applications, published in International Journal of Mathematics and Statistics, and a new discrete negative binomial height distribution and its property, published in a Journal of Composition Theory. With great pleasure, I extend a warm welcome to you on behalf of the organizing committee and kindly request you to take over the session. Over to you, sir.
Thank you very much. So I personally thank Dr. C. Satish Kumar sir for having given me an opportunity to chair this section. There are three speakers in this section. First one is respected Professor Manoharan sir. Sir, are you there, sir?
Very much, yeah.
Yes, sir. So it's really indeed great pleasure to introduce our senior professor and member syndicate of University of Calicut. He's a very senior person who needs no introduction because he is a very eminent researcher in the field of statistics. But it's a small brief profile about the speaker of this section, Professor M. Manoharan. Professor completed his master degree first rank with distinction in Cochin University of Science and Technology, and subsequently completed PhD in the same institution with NBHM fellowship, and he completed 3 postdoctoral research, one in UK, another one in Canada, and another one in the same University of Calicut. And our professor visited many countries, including Britain, Scotland, USA, Canada, Israel, Malaysia, and Singapore. And he has many credits and awards in his credit. And to list a few, he has Hasan Avidi Endowment Prize from Cochin University, there 1985, and the NBHM Award for Research 1985, and Commonwealth Fellowship at UK 1997, postdoctoral fellowship at Dalhousie University, Canada 2001, and UGC Research Award 2006. And he appointed as UGC SIM coordinator at University of Calicut with effect from 2018 onwards. He is nominated to the National Colloquium of Assessor of National Assessment and Accreditation Council, NAC, Bangalore, India, from March 2018. And he has a lot of experience, includes research fellow at Tata Institute of Fundamental Research, Bangalore, and QSAT during the year 1985 to 89, and research associate at University of Pune, and lecturer in statistics, Punjab University at Chandigarh 1990, visiting research associate, University of Sheffield, UK 1997 to 98, lecturer and senior lecturer, reader, and subsequently promoted as professor and also promoted as senior professor. He has a lot of educational administrative experience, more than 10 years. He headed the department for several years in the same institution, and he also had a full additional in charge of University of Calicut as a registrar, and he was served as a coordinator and convener of the choice-based credit system for a PG program at University of Calicut for 3 years, and subsequently for another 3 years from 2016 to 2019. And he was a very important position as a director IQAC for the University of Calicut during the year 2017 to 2019. He has more than 3 decades of PG teaching, and he has vast research guidance. He is guided successfully 13 PhD students, and ongoing currently 8. He guided successfully 10 MPhil scholars, and he was external examiner for more than 20 PhD scholars. He is a life member of many associations. To list a few, he is a life member of International Indian Statistical Association, life member of ISVS, life member of Indian Statistical Association, a life member of Kerala Statistical Association, and many more. And his membership in university academic bodies, like he is a syndicate member from 2019 for 3 years, and elected as a Senate University of Calicut and he was served in many universities as a member of PG Board of Studies, including University of Calicut, University of Mysore, University of Madras, Kannur University, Mahatma Gandhi University, Cochin University, Cochin University of Science and Technology, Mangalore University, and many other universities. And also he served as a school board in Mathematical Sciences, Pondicherry University. He's a member of PG Board of Studies, Mathematics and Statistics, St. Joseph College, Devagiri. And he is a member of Academic Council, Cochin University, and the Faculty of Science, QSAT, Kannur University and University of Calicut. And he held many posts. I think the list goes on. And he is a very prominent referee for very reputed international journals like Communication Statistics, Journal of Indian Statistical Association, Upsearch, Indian Journal of Pure and Applied Mathematics, Journal of Kerala Statistical Association, Journal of Probability and Statistical Sciences, Applied Mathematics Letters, Reliability Engineering and System Safety, and the list is very vast. So due to time constraint, I list only very few. And he is a content editor for 28 e-content models on probability theory and optimization in the subject of mathematics, and 12 e-content model in the subject of statistical bioinformatics. And he has very deeply involved in MOOC SUYAM platform. He is a very important person for MHRD for developing such kind of e-content. And he has chapter 15, departure and related characteristics in queuing models, jointly with two prominent authors, Handbook of Statistics. And he attended 92 national international conference. And his research interests include statistical models in queues, inventory and reliability, space type distribution, survival analysis, and longitudinal analysis, inferential problem associated with all of these topics, supply chain, processes, and official statistics. He has very good publications of international repute. Such an eminent personality. He is now going to give a talk on this in the topic of an economic approach to some practical queuing system. So I welcome you, Professor, on behalf of this organizing committee, and on my own behalf, I welcome you, sir. Now you take over the session, sir.
Thank you, Dr. Shaktivel. It was a long introduction.
It's a brief introduction, sir.
Sorry. Anyway, let me at the outset express my gratitude to my dear friend, Dr. Satish Kumar and his team for giving a wonderful opportunity to interact with budding researchers, especially. And also, I am very glad to be in this session because my other the co-speakers in this session are my dear friends, Professor Anil C. Matthew and also Professor Kanchan Jain. Professor Kanchan Jain was once my colleague at Punjab University, Chandigarh. Anyway, let me straight away enter my topic. I will start my presentation. Is it visible?
Yes, sir. Yes, sir.
Thank you. Let me tell you that I've been working in queuing theory, queuing systems for a long time. You know that the queuing system is a very it has been very widely, extensively investigated by several people in the past. And very interesting queuing systems are there. But the main problem in the queuing system is that when you go more towards reality, your model becomes so complicated so that seldom you don't get a clear solution. The exact solution is far distant away. So that people now I'm what the point I would like to make here is that along with in the previous talk the chair was mentioning about how the theory should go with the practical, right? So this is an economic approach to some of the practical queuing systems. I would be taking your attention to some of the usual simple queuing systems and the real life situations wherein we come across this and what is the need for approaching this in an economical way. So an economic approach to some practical queuing systems is of interest. Queuing is an aspect of modern life that encounters at every step in our daily activities. I'm not elaborating with because many of you are familiar with the key ideas and issues, and we have analytical issues. How when you look at the number of customers in the system, the number of customers in the system would be a resultant of the kind of an arrival as well as the service and kind of other processes happening there. And obviously, when your process under consideration as a stochastic process is a Markov process, then the standard Markov theory applies and you can go ahead. Well, right? But when the problem is when you deviate from this exponential assumption on the interval time or the service time, then it becomes a non-Markovian queuing model. But still, people apply some ideas like the supplementary variable technique and also the embedded Markov chain technique in order to identify a Markov chain inside that, right? So I think that is a basic idea. And similarly, we can also alternatively embed the Markov renewal because a more general structure, Markov renewal process inside that, and you get the semi-Markov process, so you can analyze that in that manner as well. So Markov renewal theory plays an important tool, just like Markov theory plays an important tool in the non-Markovian queuing models. You can have a single node queuing systems and queuing networks. And nowadays, a lot of applications are there in the queuing networks. Queuing networks means you have a finite number of queues that are combined in certain, like open queuing networks are there, closed queuing networks are there. And it differs from the way the customers are entering the system and leaving the system. In the open queuing network, the customers can enter from outside and leave. But in the queuing systems, a fixed number of customers would be circling around in the system. So, and anyway, the key elements and underlying mathematical concepts we are like how do you calculate and interpret the operating characteristics, and these are some of the issues that we need to address. And also we have a single server as well as multiple server queuing models. The obvious implication of customers waiting in long and winding queues could result to prolonged discomfort and economic cost to them. So that is the part that we will be investigating in this discussion. However, increasing the service rate will require additional number of servers, obviously, so which implies extra cost to the management. So we attempt to find a trade-off between minimizing the total economic cost, that is the waiting cost and the service cost, and the provision of a satisfactory and reasonably shortest possible time of service to customers in order to assist the management in deciding the optimal number of servers needed. I will in the discussion I will give you some simple numerical illustrations just to understand the key ideas. Okay. Also, in this month in June 23, you could see a lot of people are working in queuing theory, and now this theme of what we call the cost-benefit analysis is of much interest nowadays. A recent article that I find is that appeared in the AIP conference proceedings in this month, June 2023. That was part of the International Conference on Computational Applied Sciences and its Applications. The topic is very interesting: an angry and upset customer, the queuing system cost-benefit analysis. That's the title of the paper. And in fact, the paper is addressing a very simple issue. An effective cost-benefit analysis of MM1N, that is finite capacity single server Markovian queuing model, is addressed. But with what kind of customers? Angry and upset customers. So obviously we will be wondering what is this angry and upset customers. Angry and upset customers, here the authors assume that the arriving customers bark with some probability when one finds a very long queue may not join sometimes, right? So with some probability QK it joins, and with probability 1 minus QK it doesn't join, depending on the state of the system. And reneging is also there, which follows exponential distribution. And the standard Markov process technique is applied, usually, because it's an MM1 coin, MM1N model, and it is applied to find the steady state probabilities. And also metrics from solution is also supplied here. So this is also demonstrated. The model, some with the applications are also given. For queuing systems, the cost analysis constitute a very important aspects of its investigation. In practical situation, it is nothing but a cost factor that enables to survive a queuing system. Many researchers are working on the equilibrium level queue cost model. In the steady state, what is the cost? And also they analyze the two competing cost of providing the service. One is two competing costs in the sense cost of delivering the service and against the cost of delay in providing the service. That is precisely what we call as a waiting time cost. And the computed and the projected total cost per unit for the system would be the objective then, right? So the human behavior is interesting here in this particular model paper. That is, the human behavior is accounted through one barking, another is reneging. And of course, I need not to tell you that it has a significant place for researchers. And here, angry and upset customers with a random service. So in fact, the angry and upset customers, they play a very meaningful place in modern society and also in several real life problems. You can see angry and upset telephone switchboard and customers, right? Also, you can have a hospital emergency room that handle critical patients. That is a typical example of angry and upset customers. And also inventory system with the storage of valuable goods. And these are all instances where we have this kind of models. Okay. So this how to optimize the service rate, and that is of interest. Likewise, in the Craig and Delana et al. Considered a service setting where the provider may have advanced information about the customer's future service needs and may initiate service for these customers proactively. Economic analysis of queuing systems with the strategic customers have also been dealt with. And the Hassin and the Habib 2003, that paper is to queue or not to queue. That is an equilibrium behavior in the queuing systems is addressed. And also queuing systems with the multiple agents, customers, servers, and central managers all act, but in a non-cooperative manner. And that is a rational queuing. That is a book published by CRC+. The Hassin R has written that. And also these provide a comprehensive review of this body of work. And customers who join to choose to join the shortest queue to minimize their individual expected weighting cost may generate a positive externality by reducing variation across queues. That is the idea proposed by Haas in 2016. And so what I would like to tell you is that the study of queuing is important as it provides both theoretical background to the kind of service that we may expect from such a facility, and the way in which the facility itself may be designed to provide some specified greater service to its customers. That is our basic idea. Our study of queuing shall be more concerned with the communication systems and computer networks. A lot of applications are there in the communication systems and also computer networks. Various computers, routers, switches in such a network may be modeled and individual queues. The whole system may itself be modeled as a queuing network, as I mentioned, open queuing, closed queuing systems. And also nowadays, a lot of applications are there in the health sector also. Application, the queuing theory provides a theoretical framework for design and study of such several networks. And also it arises in operation research and industrial engineering, as the facilities studied in these areas may also be modeled as either individual queues or queuing networks. But the exact analysis, as I mentioned earlier, queuing systems is also often difficult. Even with the simplifying assumptions and approximations, it may not be always possible to obtain an analytical solution. In such cases, one has to take recourse to these simulations for the study of these systems. But obviously, the use of phase step distribution and also the metric geometric solutions in stochastic models have paved a better way to analyze several queuing systems. Algorithmic tractable solutions are available for such models. Let me ask a very simple question. When you, this is a, I think I'm sure both cases, this is a, I'm asking this question like there are two cases. One is an MM1, Markov arrival, that is the Poisson arrival. The service time is exponentially distributed. There are two servers. Imagine that these two servers are in the following way. Case one, two independent queues are there. You can note that both the rate is lambda. Now the lambda by 2 is going through the first server, and the lambda by 2 is going to the. So effectively, the total arrival rate is lambda, and there are two servers, and each server has a rate mu. And also, otherwise, the case number 2 is you have a common. There are two. The first case is the two independent queues. And the second case is the common queue, right? It is a common queue. The first is a separate queue, and this is a common queue. So common queue means all customers are standing in the same queue. And it is just like in the, you find this kind of queuing systems in the passport seva counter and other places where you'll be given some like a token, right? And then you'll be sitting in some room, and then people will be taken depending on whoever the server is free, you'll be taken there, right? So this kind of a queue. So you have two. Imagine there are two servers. So both are mu. The rate is mu. Now the question here is which system is better? This is in the better in the sense your criteria would be obviously what is the response time, right? How much time one will take in the system, right? Let us see. So the first case, MM1 model, obviously your lambda by 2 divided by mu is your traffic intensity. And your response in the separate queue would be, that is the first case, expectation is, you can just work out and you will see that it is nothing but 2 by 2 mu minus lambda. Let me come to the final expression here, okay? Now, whereas in the common queue, that is MM2 queue, if you look at the Little's formula, it says expectation of the RC is expectation of NC by lambda. And you can use the expression for this expectation of NC in the conventional way for, you know, you have the expression for the MM S general server model. Therefore, m is equal to 2, you get this result, which is 2 rho by 1 minus rho square. And obviously, using the Dittel's formula, what you get is 4 mu by 4 mu square minus lambda square. And obviously, you can see, let us compare this expression with the earlier expression, 2 by 2 mu. So you have expectation of Rs is equal to, that is for separate Q, it is 2 divided by 2 mu minus lambda. If you multiply by 2 mu plus lambda, you can put it as 4 mu plus 2 lambda by 4 mu square by lambda square. So now we can compare these two, the same denominator. So this would be obviously bigger than the expectation of RC. So the message is that you can have the comparison like this and say that the separate queue, it involves more response time. Therefore, the combined queue is better. Okay. So this is a reason in several places this combined queue system is adopted. It is on a very scientific footing. The decision is taken. Okay, let me look at a very simple situation. Queuing models are everywhere. For example, airplanes queue up in holding patterns. And also waiting for a runway so that they can land. Then they line up again to take off. We have queue systems like so. People line up for tickets to buy groceries, etc. You can have a job lines for machines, order line up to be filled, and so on. So several instances you can see. I cannot forget this name, Eke Airline, who is credited with the founding of queuing theory. By studying the telephone switchboard in Copenhagen for Danish telephone company. And his Erlang's loss formula, recall that this is still in use with the telecommunication industry. We are still using that formula. Many of the queuing results used today were developed by Erlang. Typically a queuing model is one in which you have a sequence of times, such as people arriving at a facility for service. Now then what happens is, let us consider sometimes in a particular system you may have several queuing models. Let me cite a few. Consider a hospital. You have 3 models. That is, the hospital treats a large number of patients on an outpatient basis. Okay. Outpatient plus those admitted to a 600-bed hospital produce a large flow of new patients each day. And most new patients must visit the diagnostic lab. You know that. So each such patient has to be seen by a technician there, right? So after seeing a doctor, a patient arrives at the laboratory and it checks it with a clerk. So obviously patients are assigned on a first-come basis, first-served basis to the test rooms. And they when they become available. And the technicians assigned to that room performs the test ordered by the doctor. When the testing is complete, the patient goes on to the next step in the process and technician sees a new patient. So this is the usual, it's a routine thing, what is happening in a hospital. So we must decide how many technicians to hire. So there is an optimization, right? How many technicians to hire here, right? And also, as part of the, I have a model too, buying the wards line. As part of the remodeling process, the hospital is designing a new communication system, which will include the wards, the wide area telephone service lines. WANS is an acronym for a special flat rate long distance service offered by some telephone companies. When it's now we have all modern systems are there. When all the telephone lines are allocated to WANS are in use, the person dialing out will get a busy signal indicating that the caller call isn't completed, can't be completed. So the question here is, we must decide how many wards line in the hospital should be, the hospital should buy so that a minimum of busy signals would be encountered. And that again is an optimization, right? And we have a third one is the hiring repair people. Your hospital may hire repair people to maintain different, maybe there are 20 individual pieces of electronic equipments to repair them. different types of equipments are there, like ECG machines are there, computers are there, CAT scanners and other equipments are there. So then if the piece of equipment fails and all the repair people are occupied and it must wait to be repaired. Here again, we had to decide how many repair people to hire and balance the cost against the cost of having broken equipment. So all the three of these models fit the general description, obviously as a queuing model. The point I am trying to make is that everywhere you can see a queuing model, right? One is in the first instance, model one, patients are the servers, arrivals, and they have the server is the technician. In the second case, telephone calls and the switchboard is your service facility, and you have the repair people serving, and the broken equipments are the arrivals. So this model should be resolved by using a combination of obviously analytic and simulation models. So this is the modern approach in dealing with this kind of a very huge establishment problems. You try to have a combination of analytical and sometimes the simulation models are to be used. Okay, so I will consider a very simple illustration of the different problems here. Consider a photocopy machine and assume that the users arrive at a machine from a single line. Okay. Then the system is a simple single server, that single channel queue in the conventional way. You can have questions about this or any other queuing systems center on basically 4 quantities: number of people in the system, number of people in the queue, and the waiting time in the system, and also waiting time in the queue generally. And you have the basic assumptions about the arrival process, maybe exponential, in which case you have the Markovian, or the interval times are IAD exponentially distributed. You'll specify the rate of arrival and service process. In the basic model, the time it takes to complete a job, that is your service time, or the response time that we usually call in the computer science models, treated as a response time, treated with the exponential distribution. Then we have the usual MM1 model. Now I will tell you queue size. There is no limit on the number of jobs that can wait in the queue. That is infinite queue length. And if your capacity of the system is finite, then it becomes a finite queue model. The queue discipline is also important. Jobs are served on first come, first based, or last come, first served based, and so on. Time horizon is a system operates as described continuously over an infinite horizon. That is what we assume here. There is infinite population available to arrive, so the source population is also infinite. This is a Kendall's notation. So the values of the parameters lambda and mu are all that is needed to calculate the several important operating characteristics. I just want to tell you that for instance, the expected number in the system is in terms of your lambda and mu, number in the queue, waiting time in the queue, all these can be computed in the usual MM1 model, wherein we assume under steady state lambda is less than mu. Okay. So this is now if I return to the model, it is lambda should be less than mu. I can just show you this illustration appropriate using a spreadsheet worksheet for the MMM case. You can see the arrival rate is 0.05. Okay, service rate is 0.1. And you have the utilization is 50%. That's 1 minus rho. So you have the expected number in the system L, number of people in the system after the queue has reached steady state. That is the interpretation that you should give. So steady state means the probability that you will observe a certain number of people in the system that does not depend on the time at which you count them. So in the steady state, the system is empty with the probability 1/2, right? On the average, 0.5% in the queue. And on the average, an arrival must wait 10 minutes before starting to use the machine. So you have an idea about the waiting time. And on the average, an arrival spent 20 minutes in the system. So you can have this calculated. So these results hold for the basic model and the particular values of the parameter, lambda and mu. Okay. Now, you can have the calculation based on how many hours per day, then how many, if you make 8-hour day, how many people would be there? You can have this calculation. The average, you can see that on the average, each person spends 20 minutes in the system. That is what we have seen. So the total time spent in the system facility is obviously, you have 20 arrivals per day, then multiply by 20, that's 480, that is 8 hours. Okay. Suppose you make the schedule, reduce the 8/6, then what will happen? Okay. So there are plenty of options, like the management feels that 8 hours is too long to spend in the facility. Then what are the possibilities? A new machine might be purchased with a smaller mean service time. So the service rate is better. And another alternative is that another machine might be purchased and both machines used to satisfy the demand. But obviously this would change the system to server, right? And another thing is that some personnel might be sent to different and less busy copying facility, but that also we are changing the arrival process. Okay, so in any case, management must balance the cost of providing service against the cost of waiting. That is sure. So the question is, when it comes to the MG1 queue, the exponential distribution may not fit the service process very well. So, but there is a generalization which we have applied the embedding Markov technique and computed the steady state characteristics. Here a very important point is to be noted. When you look at the service time distribution, the quantities in the steady state, like expected delay, expected number in the system, and those quantities are not really depending on any other quantities except for the parameters, that is mu and the sigma square, the mean service time and its variance sigma square. You can see this expression CL. But important point here is, when the variability increases, obviously your L, LQ, waiting time in the queue, all will increase. So this means the consistency of the server is very important, as the speed of the server. Along with the speed, the consistency should be ensured. That is a very important point. It's a very simple situation. Suppose you want to hire a secretary. You have two secretaries. Secretary number one is very consistent, typing any document in exactly 15 minutes. Exactly 15 minutes. Whereas secretary 2 is somewhat faster, with an average of 14 minutes per document, but with the time varying according to the exponential distribution. So obviously your sigma comes into picture, right? If you work out both secretary 1, you will see that the time here is expected, the average turnaround time is 37.5. Okay. Whereas for secretary 2, though she is faster because of the inconsistency, that is the sigma square is playing a role here. the expected turnaround is 46 point, average turnaround time is 46.667. So this shows even though secretary 2 is faster, her average turnaround times are longer because of the high variability of her service time. So I think I'm approaching my time. I will just try to give you the models. I have the, say, server 1, server 2, and server 3. Each patient joins a common queue, and on arriving at the head of the line, enters the first available examination room. This type of system must not be confused with the system in which queues form in front of each server in a typical grocery store. Okay. Now, suppose that a new patient arrives every 5 minutes on average. So your mean interval is 1 by lambda, which is 5. And all servers are identical. And each service time, let it be 0.125 per minute. So the mean service time for an individual server is 1 by mu, which is 1 over 1.125, which is 8. So note that you have the steady state, your lambda should be less than S times mu. And here, obviously, this would not be satisfied. But for the multi-server, it's a lambda less than S mu, where you have in the 2 servers are there, then obviously this will be satisfied. If there are 2 servers, a steady state will be achieved. Obviously, because your lambda is 0.2, which is less than 2 times 0.125. So the you can calculate the P0, the probability that the system is empty, expected number of people in the queue, and the MMS worksheet can be used to evaluate the for against number 2, what is the waiting time. Okay, so I will speed up now. You can see when S is equal to 3, the time, your expected time in the system is 1.91, whereas for 4 it is 0.3023. So it means that when S is equal to 3, you are having the optimal, right? Okay, so that is a comparison. So adding additional servers may decrease the waiting time. However, you have to consider not only how much extra you will pay for the additional servers, but also if those additional servers will be busy most of the time. So as more servers are added, the percentage of idle time for the technician increases, which could lead to boredom and sloppy work. So that leads to the economic analysis. The cost of hiring additional technician is fairly clear. So determining the cost of waiting, that is the cost to the patient is relevant to the decision, except as it affects the patient's willingness to use the hospital. So besides the possible effect on demand, the diagnostic lab could cost the hospital money. So cost parameters here are, if you are willing and able to estimate certain cost, you could build expected cost model of the queuing systems. In the case, I am taking CS, the cost per hour of having a server available, CW, the cost per hour of having a person waiting the system. So if you use the 2 server with an 8 hour, we have the following server cost components, CS, 8 hours, and the waiting cost is computed. So the total cost using 4 servers for a 6 hour day can also be alternatively computed. So the total cost per hour now we define as the total cost is the CSS plus CW into LS. So it's a simple minimization of the yes with regard to the total cost. So this kind of ideas can be employed in single. I have worked it out for single server and also the multiple server cases and also other queuing networks also. So also people are now approaching this economic analysis is the teamwork. Economic analysis is the teamwork maximizes firms' profit and customers' value by trading off having more service channels like registers in a grocery with a team of workers like a cashier and a bagger working at the same register in a grocery, providing faster service in each channel. You can approach this in the similar manner and find out what system would be better. Okay, I think I'm just stopping now. We have a few important heterogeneous servers models can also be thought of in this manner. A few important references. And thank you.
Yeah, very nice lecture,
you.
Professor. It's a really great privilege to listen to your talk. You very elaborately explained how these queuing theories practically and economically applied in many fields, especially in healthcare sector. So it's a very excellent, nice talk. We are all highly privileged to listen to your lectures. Now, if there is any question to the audience, you feel free to contact or ask Professor M. Manoharan, sir.
Thank you all. Sorry to exceed my allowed time. Sorry.
We did not look at the clock, Professor, because it's very nice and excellent. It's practically applied. I think if there is no questions, so on behalf of this organizing chair, we thank Professor Manoharan sir for having delivered a talk on how practically and economically implemented queuing theory very effectively. So once again, I thank on my personal behalf and also on behalf of this organizing committee. I thank you, Professor.
Thank you, Professor Sadish also. Yeah.
Thank you, sir. Thank you.
Now, the next speaker of this section is Dr. Anil Matthew. He's a professor of biostatistics at PhD Institute of Medical Science and Research, Coimbatore, Tamil Nadu. He got his training in biostatistics from Christian Medical College, Vellore, in MSc Biostatistics and doctorate in biostatistics from Bharatiya University, Coimbatore. He joined the All India Heart Foundation, New Delhi, as assistant statistician in the year 1988. Afterwards, as an assistant professor in 1989 in PhD Institute of Medical Sciences and Research, Coimbatore, and subsequently promoted as associate professor in the year 2003. And also he got his promotion as professor in 2008. He is adjunct faculty in the Department of Medical Education, PhD Institute of Medical Science and Research. His major activity involved teaching of biostatistics and clinical epidemiology to the undergraduate and postgraduate medical students, as a guide for MSc Biostatistics students, consultant for MD, MS students, carrying out independent and collaborative epidemiological research projects, delivering guest and invited lectures, and he served as external examiner for PhD and postgraduate students, a member of selection committee, and also served as a reviewer and member of editorial committee of various national and international journals. The professor received World Health Organization scholarship to attend International Epidemiological Association Southeast Asia Regional Meet at Dhaka, Bangladesh in the year 2008. He was the organizing secretary of 24th Annual National Conference of Indian Society for Medical Statistics in the year 2006, which is conducted in December 1-3. He has contributed more than 30 original articles in various national and international journals. He is a member of International Biometric Society, a life member of Indian Society for Medical Statistics, Indian Association for Study of Population, and Kerala Statistical Association. In 1997, he received Suraj Kali Jain Award from the Indian Society for medical statistics for the best paper published in medical statistics. His area of major research interests include epidemiology and non-communicable disease. He has collaborated with Dr. Yegma, Assistant Professor of Medicine, Division of Preventive and Behavioral Medicine, University of Massachusetts Medical School, USA, and published several papers in the indexed medical journals. Besides this, he also specialized in clinical trial design in 2008, Chief Statistics Consultant at Inter-Head Faculty of Clinical Research, a Canadian Accredited Training Center in Clinical Research and Clinical Data Management. He has been selected and attended Indo-US workshop in clinical research in the year 2007 and 2008. Such a prominent person in the medical statistics, biostatistics. He will be going to give a talk on subgroup and interview analysis in clinical research. So I welcome you, Professor. Now it's over to you.
Yeah, thank you, Shaktivel sir, and also Satish Kumar sir for inviting me to deliver a talk. And today's this talk, I just thought of giving a motivational talk for the postgraduate students on subgroup analysis in clinical research. Share options. So share options.
Sir, it is there. I think fifth button, sir.
Yeah.
With the square upward arrow, there is one icon is there. Press it now. Just you keep the mouse and that.
Yeah, sure.
Yes, sir.
So the topic is on subgroup and interim analysis in clinical trials. And again, this session does not have any much formulas or technical issues, technical things. I won't discuss it, but it is basically a motivational talk for because many of the postgraduate students in the universities, they are showed interest in taking biostatistics as an elective subject. And especially in the COVID epidemic, when we are all looking for a new vaccines, this topic like interim analysis become an important branch in the field in the biostatistics field. So just thought of giving a motivational talk on the issues with the subgroup and interim analysis in clinical trials. The definition of subgroup analysis, it refers to the practice of attempting to determine whether and how the treatment affects the vary among the various subgroups. There are a lot of criticism on this subgroup analysis. The main criticism is they have generally focused on investigators attempting to transform negative studies into positive studies, a subgroup of patients for which the treatment effects may be significant. Especially this you have to look into, like when we developed a vaccine, it may not be significant. It may not give a significant result in the community. Naturally, we may think whether we can do some kind of a subgroup analysis or not. This is which I just wanted to discuss the first 5 or 10 minutes of my talk. Why physicians are interested in subgroup analysis? Most illnesses exhibit in a wide range of behaviors. It seems natural to look to a clinical trials for information about specific subgroup of the patients. For example, the risk-benefit relationship in coronary artery bypass surgery differs for people with a single vessel disease versus triple vessel disease. So the physician may be interested in know how it has effect on the patients with the single well disease. But in reality, it is not like that way. The actual identification of the subgroups is very difficult. Sorting out the important ones may not be that simple as we think. And we may need for large samples. Most clinical trials are only small or moderate in magnitude. There are two ways which we can do the subgroup analysis. The first is the planned subgroup analysis. Another is unplanned subgroup analysis. What I am concerned is about the unplanned subgroup analysis. In general, we discourage unplanned or improper subgroup analysis, since the investigator might just report statistically significant results. Whereas in the planned subgroup analysis, even at the time of protocol submission, we explained the demographic and physiological subjective interaction effects and its status, which we have to mention in the beginning itself when we submit to the project proposal. Here is one example of a subgroup analysis. When we did a trial on new versus the standard antibiotic on febrile morbidity in four age strata, in the beginning, what we found is that the drug does not have any beneficial effect. The odds ratio is coming around 0.9 with a confidence interval of 0.6 to 1.4. That means the results are not statistically significant. But at the same time, when we look into the various strata and when we recalculate the rate ratio, the age 0 to 14 it is 1.4, 0.6 to 3.2. Again, the rate ratio is not statistically significant. Whereas age 15 to 44, the rate ratio is 1.2. Again, the odds ratio, when we look into it, 0.4 to 3.1, it is not statistically significant. The age of 45 to 59 years, the rate ratio is 1.1. Again, when you look into the odds ratio, 0.6 to 1.4, not statistically significant. But elderly people, when we look into it, the rate ratio is 0.3 and the 95% confidence interval is 0.1 to 0.9. Here it is significant. But the issue is, can we project that this drug is effective among the people who are above 60 years? And can we market this drug in that way or not? But when we look into the statistical interaction effects, the p-value is 0.103. So the take-home message which I wanted to tell you is focus on the overall analysis. If the subgroup analysis is relevant, use a test of statistical interaction. And it is improper to do the stratum-specific testing, might highlight the effectiveness of elderly people, which is not actually in the reality correct. The last time when I did a journal review as part of systematic review of these journals, lot of papers are presenting this type of improper analysis and finding that this particular drug is effective among this particular age group of people, which is definitely not a good way of seeing the results. Unplanned and subgroup analysis. Just for the postgraduate students, I just want to again highlight that seeking positive subgroup effects in the absence of an overall effect may fuel the epidemic of subgroup analysis. There's an interesting story which is mentioned in the Lancet, which some of you may have heard about it. I just highlight it is not my story. I have taken this article from a Lancet article. It's a PETO trial of 17,187 patients. It is about aspirin in preventing the death. The results, what they found is that aspirin prevented death 23% reduction, and the odds ratio is 15% to 30%, and p-value they are getting statistically significant. But the Lancet editor, they wanted about 40 subgroup analysis. Initially, usually the other way will happen. The author will request the editor to do the subgroup analysis. But in this story, the editor requested the PETO to do the subgroup analysis. But the author initially declined that I will not do it. But after forceful request from the Lancet editor, he has agreed to do the subgroup analysis. And as long as they could add. So what he has found in this interesting part of the study is, he has looked into the star of the patient also. In this, what he found is that aspirin does not prevent death in Gemini or Libra. Born under other astrological signs, 28% reduction with a p-value statistically significant result. But he has forced the Lancet editor to publish this particular finding, that even it can, when you do the subgroup analysis, it is not according to what you request. So finally, the editor of the Lancet forced to publish this paper in 1998 and saying that if you are born in Gemini or Libra, there is no hope for you to get beneficial effects from the aspirin drugs. So this is a story which actually what happened is that The Nancy Reagan asked who would not bet. She was also much interested in the astrological findings of it. Anyway, that story goes like that way. But basically, the take-home message at this junction, what I wanted to tell you, only planned subgroup analysis is recommended. Unplanned subgroup analysis definitely not recommended. So all the subgroup analysis should perhaps be taken less as evidence about who benefits than as evidence that much analysis are potentially misleading. That is the major finding of this study. So these intermediate trials, when you look into it, the answer to a randomized control trial that does not confirm one's beliefs is not the conduct of several sub-analyses until one can see what one believes. Rather, the answer to re-examine one's beliefs carefully. This is also taken from British Medical Journal 1991, which I have taken. So concluding thoughts on conducting the subgroup analysis, just to say no to it. And if you are keen on doing, use the statistical test of interaction for it. And I just also just thought of highlighting another 10 minutes or 10 minutes on about the interior analysis. There are two topics which I just wanted to cover in this session. One is on subgroup analysis and the other is on interim analysis. And the definition of this interim analysis is analysis of clinical trial data performed at a point at which enough data have been gathered to derive preliminary but not necessarily complete the conclusions. Why interim analysis is required? As we all know, this talk, if I give a lecture on 3 years back or 4 years back, it is more difficult for us to understand what I'm saying it. But after this COVID epidemic came, it is easy for us to understand what I'm saying. Because we are all looking, there was a time which we are all looking for a vaccine. And we wanted to have a vaccine. When we will get the vaccine, there's a time which we are asked this question to ourselves. So naturally, we can't wait for a long period of time till the time is over. So looking into the ethical, economical, and administrative reasons, we may have to do the interim analysis and may have to take certain decisions of it. What is the ethical part of the interim analysis? Monitoring may help to ensure that individuals are not exposed to unsafe, interior, or ineffective treatment regimens. That's one way of seeing the ethical part of it. But the COVID time, other way, which we wanted to get a vaccine as early as possible so that many deaths can be prevented also. That way also which we can look the ethical part of it. And economical part of it. For trials with a positive result, early stopping means a new product can be exploited sooner. For trials with a negative result, no treatment differences. Early stopping ensures resources are not wasted. For example, the same COVID trial, if you had planned a trial and even 1 year we are not getting any good results, whether we have to wait another 2 years when a lot of patients are dying in that situation, whether we have to wait another 2 and later we say there is no benefit for the new drug. So that is the economical part. Instead of it, we can aim for another product which we can do the trial and see whether that will give a beneficial effects. And the administrative part of the interim analysis also we have to look into it. Early examination of interim results may sometimes reveal problems. Adherence to the protocol and trial need less patients with a trial with a fixed sample size where the decision can be made at the end of the study. When we can do the interim analysis, there are two ways which we can do the interim analysis. One is based on the number of events. So total events expected, this total events including the treatment arm and the control arm. The total events expected is 100. The interim analysis can be conducted with 25 events. This 25 is the sum of the treatment and the control arm. 50, 75, and 100 events. Each of this time we can do an interim analysis. Another way of doing the interim analysis is total duration. Based on 3 months, if the total study duration is 1 year time, the interim analysis we can do at 3 months, 6 months, 9 months, and 1 year. So there are two ways which we can look into it. If the total events is we are considering, we can make an interim analysis after 25 events, after 50 events, after 75 events, and after 100. That's the last analysis of it. But if the trial duration is for 1 year period, 3 months after, 6 months after, 9 months after, and 1 year after, we can do the interim analysis. And as far as the stopping rule is concerned, you can see a blurred face because it's not very clear for us. Even today, it is not clear whether to stop or not to stop. That is the take-home message of my trial. There are two take-home messages. One is about interim analysis, one take-home message. Another is on the stopping rule, one take-home message. What is the stopping rule in the clinical research? The trial stops in favor of one of the treatments if the difference in outcomes between the treatments at interim or final analysis falls outside the boundaries and suitable for comparison between the two active treatments. For the prevention trials, treatment versus placebo trials, other relevant information presented to the data monitoring committee must also be considered. So these are the things which you are looking into it when you do a stopping a trial for it. And data safety and monitoring boards are often given the responsibility of monitoring and accumulating data. And this Data Safety and Monitoring Bureau is responsible for assuring that the study participants are not exposed to unnecessary or unreasonable risk. The Data Safety and Monitoring Bureau is also responsible for assuring that the study is being conducted according to high scientific and ethical standards. So interim data monitoring responsibilities are principal one responsibilities. The primary responsibility of the Data Safety and Monitoring Bureau are to safeguard the interest of the study patients and to preserve the integrity and credibility of the trial. Principle 2, composition. The DSMB should have multidisciplinary representation, including the topic of experts from relevant medical specialties and the biostatisticians. And principle 3 is about the conflicts. Individuals with the important conflicts of interest, financial, intellectual, professional, or regulatory, should not serve on the DSMB. And confidentiality issues is a principle 4. The trial integrity requires DSMB members not to discuss details of meetings elsewhere. Now, interior monitoring is considered. The decision to stop a trial early is a complex, requiring a combination of both the statistical and clinical judgment. This is a very important thing which I am highlighting. It is not totally based on the statistical judgment. A part of the clinical judgment also we have to look into it. Stopping a trial too late means necessarily delaying some participants from receiving the better treatment. Stopping a trial early may fail to persuade others to change practice. And statistical methods have been developed for interior monitoring of clinical trials to minimize the role of subjective judgment. And safety versus efficacy. Efficacy is assessment whether there is a meaningful difference on the primary outcomes of the study. And safety involves all other aspects of the difference between the groups in adverse outcomes. Focus is on the monitoring adverse outcomes. See, this is one of the interior analysis done for 6 months for 5 years. The p-value is shown for the comparison between the treatment and the comparison group. Efficacy monitoring methods. We have 3 methods commonly used. Pocock 1977 described stopping boundaries with the same critical value at each of the interior look. O'Brien and Fleming 1979 proposed a sequential plan where nominal significance levels needed to reject H0 increase as study progresses. And Petto in 1976 suggested a simple form of sequential monitoring where null hypothesis is rejected only when modulus ZK greater than 3 for all interior tests when small k less than capital K. Some of the PEs can look into these models whether they can develop a better monitoring methods also. For the beginners, I just wanted to tell you what is this Pocock and Petto and O'Brien methods. In Pocock, if you are planning to have 2 interior analysis, the p-value which you should consider is not 0.05, it is 0.029. And for Petto, if you are planning 2 trials, the first trial, the p-value is 0.001, and for the second trial, it is 0.05. Whereas in O'Brien, the first trial, it should be p-value not 0.05, it should be p-value 0.005, and second trial it is 0.048. It is not actually p less than 0.5. But Pocock, the specialty is number of trials is immaterial for Pocock. Whether you do 2 trials or the p-value remains the same thing. If you have 2 trials, the p-value is 0.029. If you're planning to do 3 interior analysis, the p-value is 0.022. So this is, if you wanted to have 4 trials, this is the Pocock table, Petto table, and O'Brien table. If you are planning 5 trials, this is the Pocock trail, Petto trail, and O'Brien Fleming tables. And early termination and bias. If DSMB stops a trial early based on a group of sequential procedure, random fluctuations towards greater treatment effects would more probably result in early termination. When a trial is stopped early, readers need to grasp effects to prone to exaggerations. This is just one example from a Lancet journal I just wanted to highlight you. We are all designing HIV vaccine trial. What they mentioned is HIV negative high risk woman will be randomized either vaccine or placebo. We designed 90% power to detect 50% rejection in HIV incidence, hazard ratio 0.50 with a two-sided alpha of 0.05. Just to have a look on the number of total sample size required for the 88 events as the sample size required. And the primary efficacy analysis, the null hypothesis is hazard ratio is 1 against the hazard ratio not equal to 1. And plan to use this test using Cox proportional hazard model when HT is H0 T V raised to beta into treatment. Treatment 1 refers for vaccine and 0 refers for placebo. And beta is a log hazard ratio. Beta less than 0 for hazard ratio less than 1, and beta greater than 0 for hazard ratio greater than 1. And the test statistic is Z value is equal to beta divided by standard error of beta. And why Cox model is preferred? Allow us to analyze the effect of different factors on survival simultaneously, the effect of the treatment adjusting, the effect of prognostic factors, effect of other patient characters besides treatment on survival, etc. And it is the most efficient estimator, especially if the smallest variance is concerned. But the main drawback is calculations cannot be performed by hand. We need calculator for it. So decide to stop the trial early with an event on clear early evidence of efficacy, clear early evidence of harm, and early evidence of harm based on additions. This is the things which Lancet editor has considered for it. And plan to test primary hypothesis at 4 points, 3 interim analysis and 1 final analysis. 22, 44, 66, and 88. The total events is 88 events. The overall objective is maintain the overall probability of type 1 error at specified 0.05 level. And he has taken the 3 group sequential stopping boundaries. Petto, O'Brien, and Pocock, and the O'Brien Fleming boundary. So parallelly, the first graph I put for the Petto graph, and second graph is for this study, it is for the O'Brien graph, and the third graph is meant for the combined graph of Pocock and the O'Brien. But the interesting part of the study is what they found is that the trial started enrolling the patients in January 2008. On June 15, 2000, event number 22 detected. And data were looked, interim analysis run, DSMB medical, 6 events in the vaccine arm and 16 in the placebo arm. The hazard ratio what they obtained is for the Cox model is 0.38 and beta value is minus 0.97 and standard error of beta is 0.48. The Z value is minus 0.02, unadjusted p value is 0.0434. And next interim analysis was done for the 44 events and 14 events in the vaccine arm and 13 events in the placebo arm. Hazard ratio is again 0.40, beta value is minus 0.76 and standard error of beta is 0.32, unadjusted p value is 0.0174. And next interim analysis was done on 66 events, 21 events in the vaccine arm and 45 events in the placebo arm. Unadjusted p value was 0.0036. And we thought that it is success of the trial. But when you plot this graph, what actually happened is that it came to the acceptance region at the event of 88. This was one of the crucial thing which we are worried about when we do the interim analysis. Can these boundaries be reliable or not? Anyway, this is a motivational talk only. The PGs can look more on the details of it. The simplest statistical test in data monitoring part is Z is equal to A minus B by root of A plus B. For example, if there are 46 and 25 deaths in the treatment and the placebo, easiest way of calculating Z value is 46 minus 25 divided by root of 46 plus 25, which is equal to 2.49 with a p-value approximately 0.013. The calculation usually agrees well with the p-value based on log rank test important when it is not reliably known how long each patient had actually been followed. These are some of the references for my team. So the take-home message is proper subgroup analysis is needed, and second part, the take-home message is still there's no clarity. We need more clarity on the how to do the interior analysis. We may have to develop better indicators and more valid documents on this particular topic. Thank you.
Thank you, Roser. It's really very useful insights into this subgroup and interim analysis in clinical research. A wonderful talk. Now I request the audience if there is any queries or question to our beloved Professor Anil C. Matthew, please you can post it now. I think if there is no question, really it's a completely new topic, and it's very useful insights into this subgroup and interim analysis in the clinical research. So I thank you, Professor. You gave wonderful introductions about and motivated talk in this area. So on my own behalf and also on behalf of Professor Satish Kumar and his team, University of Kerala, I thank you, Professor Anil C. Matthew, sir. Thank you.
Thank you, sir. Thank you, sir.
Thank you, Professor. Now we shift to the third speaker of this section, Professor Kanjan Jain, a very eminent person. He also doesn't require any introduction. All the professors, research scholars in the fraternity of statistics, she is a well-known and eminent person. Now I take a privilege of introducing Professor Kanjan Jain. She was a professor in the Department of Statistics, Punjab University, Chandigarh, and she has a very reputed honor of Fellow Royal Statistical Society, London. She is elected member, International Statistical Institute, Netherlands, elected member, National Academy of Science, India, ex-chairperson and head Department of Statistics, Punjab University, Chandigarh. Professor got Excellence in Research Award by Indian Association for Reliability and Statistics on birth century of living legend Professor C.R. Rao. Madam elected as a distinguished woman researcher in statistics under the science discipline by Venus International Foundation, Chennai. Madam got a very good I-10 index 14 and H index of 13, Scopus index of 12. Madam got his PhD in statistics in the year 1986, MPhil in statistics in 1980, and master in statistics in 1979. And she got BA honors in English in 1977. And also she got a certificate course in French with very high 80%. And Madam has curious to know more about actuarial science. So as a result, she got Institute of Actuary, London, and Institute of Actuary of India, Mumbai, and qualified in many exams include financial economics, probability, mathematical statistics, stochastic modeling, survival models, financial mathematics, actuarial mathematics, economics. She got interest and did very good research in the area of reliability, survival analysis, actuarial statistics, distribution theory, stochastic process, statistical inference, measurement error models. She got very good collaborators in the Indian Statistical Institute, Chennai, Indian Statistical Institute, Delhi, Department of Operational Research, University of Delhi, TBRL, Defense Research Development Organization, Chandigarh, University of Business School, Punjab University, Department of Mathematics and Statistics, Central University of Punjab, and Accenture Chicago Innovative Hub, Madison Stadium, Chicago University, United States, a Center for Development of Advanced Computing, Mohali. Madam had more than 4 decades of teaching and research in the Department of Punjab University, Chandigarh. She held many administrative experience as chairperson and head of the department for many years, and she served as an advisor to UPSC and also member UGC Expert Committee for drafting of learning outcome-based curriculum framework for statistics in the year 2018 to 19. She served as a member for various departmental committee, which include Board of Studies, and also she served as a Board of Studies for many universities like Islamic University of Science and Technology, and placement coordinator for the department where she served, and also for Board of Studies for Maharishi Dayanand University, Rohtak, and to Kurukshetra University and many other university. Under her guidance, 13% got PhD and 8% got MPhil. Number of candidates presently working towards PhD 3. She completed summer projects and destination supervised 9 and 6 students from IESER Mohali. She got book authorship for SAM's Outlines in Probability, Special Indian Edition 2010 from reputed publisher Tata McGregor. And also she drafted, wrote 4 book chapters, and for want of time, I cannot able to read it because her biodata, brief biodata itself is 10 pages. She got affiliation, Fellow of Royal Society, London, an elected member, International Statistical Institute, Netherlands, and National Academy of Science, India, life member, Calcutta Statistical Association, International Indian Statistical Association, Indian Society of Probability and Statistics, Indian Association for Productivity, Quality and Reliability, Calcutta. She also got membership in the International Society for Business and Industrial Statistics, Institute of Actuary of India, Mumbai, Association of Women in Science, USA, Organization of Women in Science for Developing World. And she served as an editorial board member in many journals, to list a few: Journal of Indian Society of Probability and Statistics, Advances in the Reliability, USA, Journal of Graphic Era University, Intrastate Yahoo Electronic Journal, and many other journals. And Madam participated in 6 conferences in global level, and 3 in USA, 1 in Portugal, France, and Hong Kong, 1 each. Within India, include more than 50 invited talks. Madam visited USA, Canada, France, Hong Kong, Singapore, Portugal, Dubai, Thailand, Cambodia. And she is a reviewer for many international reputed journals like Statistics and Probability Letters, Communication Statistics, Simulation Computation, Statistical Papers, Mathematical Review of American Mathematical Society, and many other journals. She has a very good track of excellent publications. I can't read huge in numbers, and also she held many academic positions, and she coordinated many prominent researchers in the globe. For example, Professor N. Balakrishna, Distinguished Professor, Department of Statistics, McMaster University, Canada. Professor Barry C. Arnold, Distinguished Professor, Department of Statistics, University of California. And Professor Saleh, Indian Institute of Technology, Kanpur. And she served many as a member of organizing committee of organizing national and international symposiums. She has many achievements under his list, and a member of a UGC Expert Committee in Statistics, a content review for 25 models for all statistics related work, and chief guest of Statistics Day celebration by NSSO. And she visited the Department of Statistics, University of Calcutta, and she held many responsibilities. And recently, I think 2003, she visited Department of Statistics, University of Waterloo, Canada. And I think the list is very vast. So on behalf of organizing committee of University of Kerala, I tired to read out the brief biography of Professor Kanchan Jain. She's a very vast experience, and everyone knows she's no need of introduction. But in spite of all, since it is a formal forum and also under record. So it's a bounden duty to list a few achievements of most respected Professor Kanchan Jain. So on behalf of our organizing committee, I welcome you, Professor. Now you can give a talk on estimation and testing for complete future lifetime. So it's now over to you, madam. Thank you.
Thank you, Professor Shaktivel. Thanks for the nice and detailed introduction. And I also wish to thank Professor Satish and his team members for extending this invitation. And I'm really honored. So I think I'll... Can you see, sir?
Yes, madam.
Is my present?
No, your screen not visible, madam.
Screen not visible?
Not visible. You do it one more time.
Okay. Generally, that has never happened before. Oh my God. It says you lost your network connection.
You are visible, madam, but I think it is slow.
I am visible, but why
Yes.
my presentation is not visible?
You
Because when I'm going
you take fifth button, madam, from left. I think within a square there is one upward arrow. You can press that button and you can share the full screen mode. Yeah, yes.
that's what I'm doing.
But still, I think anybody from the
Is
audience.
it visible now?
Your photo is visible, not your presentation.
No, I think it has never happened with me. What is the problem?
Not
It has
open.
never
Not
happened.
open the slides.
I have opened.
Okay. Is just to move.
Just a minute.
Madam, just click on that presentation.
No, it's
I'm clicking on it.
just clicking. It's presenting is there. It is coming, but your screen is not visible. That presentation screen is not visible, madam.
I'm surprised because when I'm presenting, it says to observe your screen.
You try one more time. Yes. Now I think it's better. Now you open your presentation slide.
Just a minute. Is it okay now?
Your screen is visible, but your presentation. You open your slide, madam, so that
I opened, sir.
Open? Okay. Now it's visible.
My slide.
Yes. Now it's visible, ma'am.
Now it's fine.
Yeah,
okay.
now it's fine.
Oh, sorry. Because I think it never happened with me before, so I didn't experiment with it. So my talk will be on complete future lifetime. No, this is not my slide. I'm sorry. I think I'll have to exit and come back. So, Is it visible now?
Yes, ma'am. Yes, ma'am. First slide is visible, ma'am.
No, something wrong.
You
No, but
press the
something
downward
wrong
arrow
is
in your
coming.
keyboard so that it will move to next slide.
Why is this happening? I'm so sorry.
It's okay, ma'am.
There is some issue, so I think I'll start from here. Is it okay, sir?
It's visible, ma'am. But you press next slide, ma'am, so that.
I'm taking single page.
It take time to display. I think
It's okay.
network is slow. It seems, ma'am.
I think my network is creating problem today. Okay, so I think I'll start. I already have less time.
Okay, ma'am. Go ahead.
So you see,
Shaktivel sir.
Yes, sir.
Sir, ask madam to mail the presentation slides to organizers, sir. From your end, you can present.
Yes,
no,
yes,
I
yes.
think if I'm opening a wrong one, then it will be a problem. So I know how to control it. Just
Madam,
a minute. Can
not at all
everyone
problem.
see
Your
my
network
screen?
is slow, ma'am. That's a problem. That's a problem. You share your slide
If we
to this.
actually complete future life is an actuarial. Sir, actually that's what I'm saying. There is some issue, I think, because I had changed my slides.
Yes,
Okay,
yes.
now it is changing.
Now it's changed.
And now it is visible.
Yes, ma'am. You go ahead, please.
Okay. I'm sorry. I think I should have tried earlier. For a newborn child, this is actually an actuarial concept. When we consider the age at time of death, it's a continuous random variable whose CDF is capital Fx and survival function is 1 minus capital Fx, which is this probability that the lifetime will exceed small x. When we consider a non-living object, x represents the age at failure. In actuarial science, this is the survival probability that a person, object survives for at least x years and is denoted by px bar. This px bar actually is the notation for this when x is discrete. And this is with support 1 to so on, and for support this, px bar is this. I think, sir, I have opened a wrong file. Can you give me 2 minutes, sir?
Yes, ma'am. Yes, ma'am.
Hello? Professor Shaktivel, I am going back actually.
Okay, okay, ma'am.
So stop sharing and share it once again. So
huh?
Stop and share it once again.
I'll share it once more. I made so many changes. I don't know where is that. So I think I'll control this one only. And I'll have to screen again, share again, na?
Yes, ma'am. You can do that. Or otherwise, you can send your slides to my
is it
email.
Visible now?
Yes,
Professor. Professor, you have Google Chrome.
No, that's what I'm saying. You see what happens is I made changes, and it seems that I don't know where are those changes now. So that's what I'm saying. If I send the file, the person will not know where to control. I know which slides to control. So that's why I'm not sending. So this I have already discussed. And this notation, if I write x within brackets, this is a life aged x, and t of x is the complete future lifetime of x. This will be the notation. This qxt is the probability that x dies within t years, and it gives us the CDF of capital Tx. The corresponding survival function is denoted by pxt, which is probability that this complete future lifetime is exceeding t. It's already past age x. So this is the ratio of these two notations. You see, this financial and actuarial models, they are built around the future lifetime random variable of the individuals. And this is required for statistical measurements, analysis, and inference. There are two approaches. In the first approach, a theoretical distribution is assumed. In the second, empirical or observed survival and mortality data are used for construction of life mortality tables. And these are the references. So this future lifetime plays a significant role, and importance of this distribution is highlighted when dealing with continuous whole life and term assurance contracts. These are insurance contracts, and death benefit is paid at the moment of death. This also plays a role when we consider other type of continuous annuities, and distribution and of future life time and its properties. They are also utilized for finding expected present values, which are known as actuarial values, and other variances. In reliability, force of mortality, alternately known as failure rate or hazard rate, is defined through its density function. And if I take expected value of t of x, this is termed as mean residual life function. So this Tx, as I said, denotes the future lifetime. If policies are not surrendered or do not lapse for whole life assurance, then we consider them to be uncensored. But when policyholders surrender the policy before the expiry of the contract, then there are censored observations. In some cases, even if the insured does not pay regular premium amount, the policy lapses. So the case of censoring comes in insurance contracts as well. So in literature, many authors have explored the aging properties of Tx, and this was done by, one of them is Lai and Z. Distributional properties were studied by Kapoor and myself, and parameters of the corresponding distributions of Tx are estimated using maximum likelihood approach for uncensored and censored cases. Nth order moment can be written like this, and this comes out to be in this form using pxt. So expected value of Tx is integral of pxt, and this is called the complete expectation of life and denoted by Ex with a circle on its head. And variance of Tx is obtained as this expression, and they are same as derived in Bowers, Earle and Dixon and all. And so actually they have not derived the nth order moment. that was done by us. So we can find the mu3, third order moment, mu4, and then we can talk about the kurtosis and skewness as well. But my emphasis here is not on skewness or kurtosis. Now, if we have to find survival probability and force of mortality, if we take these distributions are commonly used in actuarial science. First is Gompertz, exponential, Weibull, Pareto, Burr, and exponentiated exponential. PXTs are written. Mu x plus t is the force of mortality, which is just like hazard rate, and so PDFs of future lifetime distributions of x can be obtained by multiplying pxt and mu x plus t. And distributions of tx will be termed as future lifetime distributions. These remarks are actually about skewness or kurtosis. So if I estimate the parameters for uncensored case, you see, in insurance sector, a whole life assurance policy provides cover till the death. And it is assumed that insured takes out this assurance by either paying a single premium or a series of premiums and does not surrender the policy till his death. Suppose factory workers, they buy a whole life assurance policy by paying a single premium. So insurer is liable to pay claim at the moment of death of that individual. So it's important for the insurer to predict the future lifetime of the insured for deciding the premium amount so that this contract is mutually advantageous. And future lifetime can be modeled by assuming some continuous distribution of x and then finding the distribution of tx and parameters estimated. So we have done ML estimation, exponential, Weibull, Pareto, Burr, exponentiated, exponential, and Gompertz. So for a sample of n individuals who are aged x, they're all of age x, small tix is denoting the future lifetime of the ith individual. For exponential and Pareto, the ML estimators can be written in a closed form, whereas for others, we have nonlinear equations. And then we use BFGS method in our software. So when we consider if x follows exponential, PDF we know, likelihood can be written. This is the PDF of capital TX. And then we are finding the likelihood equation function, then maximizing, this is my estimate of lambda. It's 1 over t bar. Here, my t bar, actually we could have written t bar of x as well. It is the mean for those who have already attained age x. So it is of similar type as for exponential. Future Pareto, again likelihood is found, then log, take the derivatives, differentiate, equate to 0, usual procedure. We have theta cap as this. So everywhere I have x involved, where x is the age which has already been attained. Then for Weibull, log likelihood is of this form. derivatives give me this, and then we find the MLEs by equating and solving, and which we cannot do manually. So we will be using our software. Similarly, for bar, the derivatives have the forms which have to be solved through some numerical methods. So we use these nonlinear equations for finding MLE estimators of theta and gamma. Future exponentiated, same thing happens. So these are the two equations, nonlinear. For Gompertz, again we have to use numerical methods. Now when we come to censored case, I explained what we mean by censoring in these policies. So they do not continue the contract. Insured people, they surrender the policy or don't pay the premium after a few years, and they are considered to be censored. Their time of death is not known. Time of occurrence of such events is not known in advance. It is a random variable which is censoring, and this is right censoring. So CX here for a person of age X is the time at which the insured leaves the contract or stops paying premium. So there is random right censoring, we can say. These TX and CX are assumed to be independent and estimation is considered. So we first consider a term assurance contract whose term is T0. This is a contract under which an insurer pays the sum only if insured dies within the term of the contract. So it means a policy holder aged X will get the benefit if he dies between X and X plus T0, where X is the age at which he took out the policy. So insured persons who survive at T0 or those who surrender the policy, they are lost to further follow-up. So they are right censored at time T0, and those who surrender the policy, they are randomly censored. So likelihood, we define this random variable Z is Tx, Cx and T0 for these cases. And Tix is the future lifetime, Cix is the censoring time. We assume there are n observations, aged X in the cohort, and total of M leave the cohort due to death or some other reason. Out of M, R is assumed to be the number of observations leaving due to death. So there will be n minus m observations in the cohort at time T0. So likelihood function will be written in this manner. F bar Tx is the survival function for T. G bar is the function for capital C, and this is the probability density function. And small ft is the probability density function of capital Tx. So again, we consider the same distributions as mentioned earlier. And for all cases, we assume the distribution of censored random variable to be uniform on 0 eta, where this eta is depending on the percentage of censoring. And this is obtained by writing this as assumed percentage of censoring. I've not shown the expressions here. For future, exponential lambda cap comes out to be this. theta cap is this. And when we assume 30% censoring, so this probability is 0.3. Values of eta are obtained for different combinations of parameters. We generate them from the future lifetime and uniform distributions. And we assume X to be 20, 40, 60, small n to be 50, 100, 500, and this term of the insurance to be 10, 20, 30, 40, and 50. So for this, we have the tables. I'm taking the random observations from Weibull, from Burr, from Gompertz with these parametric values. And this table shows us estimates and root mean square errors for censored Weibull. So we can see that these values, these are the RMSEs in the brackets. So if alpha is 1.5, we can see here we are getting the values estimates to be close to 1.5. And for lambda also, the estimates are coming out to be close when n becomes large. But here also we are almost getting not very bad results. For Burr, theta has been assumed to be 3 and gamma to be 2. Again, these are the estimates, and we are getting good estimates. For X40, actually values of eta have been obtained, and then again we show these. This is in continuation of the previous table. This is for Gompertz. First, actually, this lambda is 1.08. These are for lambda. These are for alpha. And again, X40, X60. So it's observed that root mean square errors decrease with an increase in the sample size, initial age X, and term of the contract. So if we increase the term, we increase the initial age, then RMSEs are decreasing. For whole life assurance contract, again, same thing was, similar exercise was carried out. And again, we are getting good estimates. This is for Weibull, Burr, Gompertz. So here, as sample sizes increase, RMSEs decrease. As initial age increases, RMSEs increase. Here, I'm not getting decrease, except for Burr future lifetime distribution. So for Weibull and Gompertz, we don't get this to be decreasing. Then next thing is complete expectation of life, which we abbreviate as CEL. This is the expected future lifetime. Insurance companies are interested in knowing these so that they can determine the premium accordingly. If a person suffers from a particular disease, at the time of taking out policy, insurer gets more interested in knowing the complete expectation of life. And if an annuity is purchased at age X, the company will make lower regular payments if the CEL is low. CEL is also known as mean residual life function in reliability studies. And these people have studied the importance of this function in biological sectors. And we can also find applications of this in a review paper by Guess and Proschan. So myself, Kapoor and Diwan, they proposed a new test for testing equality of complete expectations of life. Powers have been calculated and compared with the tests given by Berger et al. And Ali. And it is observed that the proposed test statistic is more powerful.
Madam, sorry for intervening you.
Yeah.
5 more minutes, madam, just to remind you.
Trying to hurry up.
Before 7:30, you can finish, madam. Okay, you plan accordingly, madam.
Yes, sir. Thank you.
Sorry for interruption.
But there are no tests for CEL in the form of CELs in the context of actuarial studies. Examples can be that company may like to test for equality between CELs of smokers and non-smokers, rural and urban, males and females, white-collared, professionals and laborers, policyholders with an active or sedentary lifestyle. So we consider 2 random variables with these CDF and survival functions. TX is the complete future lifetime for first. This is for second. I don't think we need cut dates here. So actually cut date is the discrete part of this is the integer part of this. So PXT is for first group, for second group, these are the survivals, probabilities, expectation we denote by this, and for Y we denote by E0 X. Why? If we don't put a circle on the head, it is for cut date. And complete expectations of life can be written as this. This is mean residual life. We can see. And relationship between complete and cut date, that is this. Now Gompertz, as I talked about it earlier, it's a continuous distribution whose failure rate increases at exponential rate, widely used in actuarial science for modeling human mortality, since death rate of adult humans increases exponentially. Survival function and the complete expectation of life expressions are these. And it was generalized by Makeham by adding another parameter, which is known as Gompertz-Makeham or Makeham. So Makeham has 3 parameters. These are the restrictions, and the survival function and the complete expectation of life are given. So they are used for developing life tables, and parameter ranges are restricted. So Makeham parameters are usually confined to these ranges, and these are given by Jordan and Skolnick. So test statistic is now for this. Here we are assuming X from 0 to 120. Generally, human life may go to 100, but still we have given some flexibility that we take till 120. And H1 is the first group has more CEL. So when we consider this inequality, we get this. So delta X, which is the measure of deviation here, comes out to be this, and it is greater than 0. So for testing H0, T is considered to be this, del X, dfx plus dgx. Under H0, T is 0. Under H1, T is greater than 0. We consider 2 samples, N of size N and M. X size and Yj's are the order statistics. Capital Ri, Sj are the ranks. And empirical distribution functions are Fn and Gm. So test statistic is now given. We replace by the empirical survival functions and empirical CDFs. And in terms of order statistics, this is how the statistic can be written. And this is the final form. So large values lead to the rejection, and exact and asymptotic distribution are not tractable, but simulations support the normality. So this is also an open problem to see that it is asymptotically normal. So we consider Gompertz and Makeham distributions, and normality of the test statistic is checked through KS test, Shapiro-Wilks and Anderson-Darling. This is with equal sample sizes. Everywhere p-value is greater, so we reject H0. We don't reject H0. So it is concluded that T and M will follow standard normal distribution when N and M are equal, even for unequal sample sizes. It was observed, though table have not been shown, that it follows normal. Then size of the test for Gompertz have been calculated. This is the size of the test for equal samples at different levels of significance. And when sample size is increased, the test attains its desired size. And this is for unequal samples. Here also, attained size slightly deviates as difference between N and M increases. So as I said, we are considering two distributions, and we are considering some relationships between the parameters. So these are my distributions: Gompertz versus Gompertz, Makeham versus Makeham, and Gompertz versus Makeham. So powers for different, this is for Gompertz because we are not considering A here, and Ali and Burgers and this TNM is our test. And if we see, our power is more than these two, though it's not too good, but it's better. And when we take C2 to be 1.025, then it improves. And similar is happening here. These are the powers again for Gompertz. For Gompertz, our power is highest in all the cases. So our test is more powerful for all considered values, and some more observations were there based on values of BIs and CIs. Now these are Makeham versus Makeham, and here again, sometimes our power is not highest. Sometimes it's not highest. This is Makeham versus Makeham. So these are the observations on the basis of the tables. This is again when sample sizes are equal. Here again our powers are more. For some situations, our powers are more than Ali's and Burgers. So these are for unequal sample sizes. Here also our powers are higher. So I think these are all the tables. So these are the observations from the tables. Power increases when difference between N and M increases. Then we have to order these BIs and CIs. And similarly, on the basis of these parameters, relationships between parameters, our power of the test proposed by us is more. And similarly this. So just our last 1 minute. So
Yes.
here we test the equality of rat life length on restricted diet and on ad libitum diet. You see, when we calculated the value, it came out to be this. So we conclude that there is a significant impact of diet on longevity. So this is the illustration and these are the references. Thanks. I'm sorry about the technical hiccups. My
It's okay.
throat is also
It's
my
very
throat
much.
is also not very
It's very much part of this technical era, madam. It's a problem with the network, not with you. So we thoroughly understood your situation. And in spite of all these hurdles, you have presented excellently and very good topic of estimation and testing for a complete future life time. Very extensively used in actuarial science. I think as far as my limited knowledge is concerned, actuarial is the field, it's more random. Statistics very completely used. And you thoroughly, used two distribution, Comforts and Megam, for equal and unequal sample size. Your lecture is very nice and excellent. So I thank you, madam. So it's a great privilege and honor to listen to your lectures, and I'm so fortunate to chair this session. So on my own behalf and also on behalf of University of Kerala for organizing committee, I thank you, madam. Now I request the audience, if there is
Thank
any
you.
question.
Any question?
You are most welcome. If there is any question.
Actually, today my throat is also not too good.
Yes, ma'am. Yes.
Yeah, I am Sutish here from ISI, Chennai.
Yeah.
Madam, hi. No, I actually you use the empirical for developing the test.
Yes.
So the same thing actually
Yes.
I wrote in terms of use cases and developed one test, and it is recently published. The same thing you can write in terms of expectation. Whatever you use for test statistics, the same thing.
No, with Professor Diwan, have you done it?
Yeah. Diwan.
I think I had an idea that you have done something. And Dr. Sudhish, I was thinking that if this can be extended, generalized.
Yeah.
This is only for 2 groups.
Yeah, we will see.
So I want to extend it to more than 2 groups.
Yeah, we will
also prove the longevity.
Okay.
We'll talk about it.
Yeah.
If we can do it for more than 2 groups, that will be great.
Yeah.
Thank you, Dr. Satish. Is there any other questions from audience? If there is no question, so once again I thank most respected Professor Kanchan Jain from Punjab University. It's really a wonderful talk, madam. We got few research problems, open problems from your lectures. That is very much useful for us. We do interested in working on these areas. Thank you very much, madam.
So thank you, Professor Shaktivel. And I'm sorry, I feel sorry to everyone that there were some problems. And that has happened for the first time.
Yes. It's happened frequently to me, madam. It's for the first time. Okay.
Thank you, Professor Satish.
Thank you, madam. Thank you so much for your excellent talk. In fact, we have a very wonderful session, in fact. Professor Manoharan and Professor Alici Matthew and Professor Kanchan Jain. We are grateful to you, Professor, for your support to WSTA 2020.
Thank you, sir. Thank you.
Thank you. Also, we wish to express our thanks to Professor Shaktivel for chairing the session in a very nice way. Thank you so much.
Thank you, sir. Thank you, sir. It's thank you.
Now let us move to the next session. Yes, 38. Professor Anjana, please introduce the chair and
yes, sir.
Do the needful for its further procedures.
Of course, sir. So good morning, good
Yeah,
afternoon,
please.
and good evening to all the participants from around the world. We are moving on to the last technical session of WSTA 2023 that will be chaired by Dr. B. Sarojama. Professor Sarojama is a distinguished faculty at the Department of Statistics in Sri Venkateswara University, Tirupati, India. She has over a decade of teaching and research experience in the field and is deeply invested in areas of time series and forecasting, operations research, distribution theory, regression analysis, and biostatistics, among others. Dr. Sarojama has over 100 research publications to her credit, published in the form of articles in various national and international journals, and 2 books, one titled Some Contributions to Criminametric Models, and the other, Some Aspects of Applied Forecasting Methods. She has guided several students for their doctoral and MPhil degrees and been an active participant, having taken part, organized, as well as presented in various national and international conferences, seminars, and symposiums. Dr. Sarojama is also a life member in various professional bodies such as Indian Society for Probability and Statistics, Andhra Pradesh Society for Mathematical Sciences, International Indian Statistics Association, Indian Mathematical Society, and many more. It is with immense joy and honor that I extend a warm welcome to you, Professor Sarojama, on behalf of the organizing committee of WSTA 2023, and cordially invite you to chair the session. Over to you, ma'am.
Thank you, sir. Thank you, Anjana, and thank you, sir. Can I start session now, sir? Is it audible?
Yeah, audible.
Ah.
Okay, you can start, man.
Okay. First talk of today's session is Jagannatha Krishna from Regional Cancer Center, Trivandrum, India. The title of the presentation is Joint Modeling of Heterogeneity in Time-to-Event Data through Longitudinal Submodel. Sir, Jagannatha Krishna sir is there?
Yes, I am here.
Continue your talk,
Yeah,
sir.
thanks for the introduction. Yeah, I share my talk now. Is it visible?
Yes, sir. Visible, sir.
This fine.
Yeah. Yes. Okay. So, thank you. I wish to thank Sadiq sir for this opportunity. And here I am going to present on joint modeling of heterogeneity in time-to-event data through longitudinal submodel. So this is a work with my students Anand Hari and Divya Dennis. So first I will talk about the longitudinal data. As we know, longitudinal data is more frequent in cancer research or cancer survival studies. And here what longitudinal data means is the repeated measurement of the same variable or same unit over the a long period of time. And the main problem with longitudinal data is the component of variability, that is heterogeneity between the individuals. That is, because for the same individual, there exists heterogeneity and result in random effects. And second is the serial correlation between the individual repeated measures. And due to these, there occur some measurement error. So in survival studies, the covariate information of the patient is collected longitudinally, as I said, at different time points during the follow-up period. So the patient may experience multiple events during the follow-up, and the repeated event measurement in longitudinal studies were intermittently collected. So they can be subject to some measurement error. So this patient experience multiple events in the sense it can be, if it is a cancer survival studies, when you look at it can be a recurrence, metastasis, death, progression, anything like that. So here I am looking into a colon cancer data. So here some patient characteristics and their trajectories are given here. For the longitudinal data, here the CA, carcinoembryonic antigen, has been taken. Here in the graph, you can see that log CA value has been given. And each of the individual randomly selected some 12 patient characteristics has been given here, and shows that it is not in an even manner. So there is a heterogeneity exists within the longitudinal data. So these longitudinal variables are often correlated in structure, and that is the observations made on the same individuals or unit are likely to be more similar than observations made on different individuals or units. So a separate modeling of longitudinal and survival outcome is inefficient as it could not fully exploit the correlation between the repeated measurements and its hazards. So this leads to a biased estimation of the corresponding risk or the hazards. So taking into account the correlated structure, the risk for longitudinal and time to event data can be estimated using a joint model approach. So here we are looking at the joint modeling approach. And coming to the longitudinal data analysis or modeling, and the Olson and Siasis in 1997 is the first, seems to be the first article which discussed on the joint model. And later in 2000, Henderson et al. Formulated a class of models for the joint behavior of longitudinal and event time data. Siasis and Davidi in 2004 also look into different forms of the joint models. Singh et al. 2005 introduced the AFT model, accelerated failure time model, into the joint modeling approach. Shea et al. 2006 used the semi-parametric Cox model into the joint modeling framework. And Rizopoulos 2010 has introduced the JM package in R for carrying out the analysis in joint model. Obsers et al. 2010 included rate of change of longitudinal trajectories within a joint model framework. Rizopoulos 2012 introduced the competing risk into the parametric modeling setup. And there are a lot more studies has been came up on joint model. Yu et al. 2012, Crowther et al. 2012, and Tang et al. 2015 are some among them. So now the question, why we need a joint model? As I mentioned earlier, due to the correlated structure, we have to consider the longitudinal or the serial correlation as well as the correlation between the events, that is longitudinal and time to event. So coming to the standard model like Cox proportional hazard model, that is most commonly used statistical model in modern survival analysis. This model assumes that covariates have a multiplicative effect on the hazard for an event that is defined as equation number 1. So the Cox PH model assumes that the hazards are proportional across the levels of the covariates. Also, when the covariates are time dependent, extended Cox model with exogenous variable will be better, give a better prediction. So that means the variable is time dependent, but it is independent of the error term. But when the time dependent covariates are of endogenous in nature, like longitudinal biomarkers, which is serially related, then extended Cox model becomes inappropriate. So there comes the role of joint model. The two basic components of a joint model are the longitudinal and time to event. The longitudinal component consists of a model of the longitudinal biomarkers, which include fitting a linear mixed model in our study. So it need not be a biomarker, it can be any other variable, it can be an imaging, it can be anything which has been repeatedly measured. So survival analysis include fitting semi-parametric Cox hazard model in the present modeling setup. For that, let us assume T star be the true event time, CA the censoring time, TA denotes the observed event time of the ith subject given by TA equal to minimum of TA star CI, and delta is the indicator function. Let OA of T denote the longitudinal outcome of the ith subject at time point T. And considering the fact that the longitudinal marker is an endogenous time-dependent covariate measured with error, we assume that the unobserved true value of the ith subject at any time point T denoted by Mi of T is related with the observed value OA of T. So therefore, this OA of T comprises the true value Mi of T contaminated by a random error term epsilon it. The true value represented by a linear mixed model is given by OA of T equal to Mi of T plus epsilon I of T. And it is given in equation number 2, where epsilon it is the error term follows normal with 0, mean 0 and variance sigma square. And Bi, the coefficient follows normal with 0, D. Xi of t is a vector containing the value of the covariate associated with the ith patient at time of their jth measurement. Beta be the effect of changing the value of the covariate and are represented by the corresponding element of the fixed effect parameter vector. Xi of t is a vector of random effect designed matrix and Bi the corresponding random effects. Epsilon I t is the measurement error terms are assumed mutually independent of Bi and normally distributed with mean zero and variance sigma square. So the random effect describe how the patient-specific true biomarker value deviate from their expected behavior. So for fitting the linear mixed model in the present study, we used a random intercept and a random slope model. And this model introduces an additional random effect term which assumes that the rate of change in CA value is different from patient to patient. The model is represented by equation number 3. To assess the strength of association between Mi of t and the risk for an event, we postulate a proportional hazard model of the form given in equation number 4. And here, Mi of t is the set of all Mi of S for S between 0 and t, denotes the history of the true unobserved longitudinal process up to the time point t, and Wi is a vector of baseline covariate, and lambda naught is the baseline risk function. Gamma is the vector of regression coefficients, and alpha quantifies the effect of the underlying parameter. And here, in addition to these, in the equation 4, if we introduce a frailty parameter like nu, then we can have a joint frailty model. And in the present study, we are comparing the joint model with joint frailty model. And the longitude, the log likelihood formulation also here shown for the joint model, and similarly we can extend it for joint frailty model. To define this joint distribution, we will assume that the vector of time independent random effect Bi account for both the association between the longitudinal and event outcome and the correlation between the repeated measurement in the longitudinal process. And thus we have the probability of Ta delta I Oi given Bi theta is given by the product of the conditional probabilities and is given here. Here, theta equal to theta t prime, theta y prime, theta b prime, whole prime is the full parameter vector, where theta t denoting the parameter for the event time outcome, theta y represents the parameter of longitudinal outcome, theta b the parameters of the random effect covariance matrix, and Oa be the Ni by 1 vector of longitudinal response of the ith subject. So then the log likelihood of the ith subject is given by log P of probability of Ta delta I Oa theta is given by the expression given here, and probability of Ta delta I given Bi theta t beta is given by in terms of the hazard rate as lambda I of Ta given Mi of Ti theta t beta raised to delta I into Si of Ti given Mi of Ti theta t beta. And this joint density for the longitudinal response together with the random effect is given by the probability of Oi given Bi theta into probability of Bi theta, and is given in the expression given below. So
Dr. Jagannath, your slides are not changing.
Sorry.
Your slides are not changing.
Okay, just I will stop share and come back. Okay, just. Is it visible now? Sir?
Yes.
Yes. Okay. Yeah, now in slide 13. Is it visible?
Yes, sir. It's changing, sir.
Now it is okay.
Okay, thank you. So maximization of the log likelihood function L theta is given here, and it is maximized with respect to theta can be achieved using either expectation maximization algorithm or Norton-Raphson algorithm. Here we used expectation maximization algorithm. And the key component for applying either of these two algorithms in joint model is the score vector of the observed data corresponding to the log likelihood function L theta. So the score vector can be written as S of theta given here, where A dot A theta bi denotes the complete data score vector. So here, in addition to this, we used piecewise constant baseline hazard function for the choice of baseline hazard. And for piecewise constant baseline hazard function, the approach involves partitioning the time scale into several intervals and assuming that the baseline hazard is constant with each interval. This method is relatively simple to implement and can be flexible when the hazard changes non-linearly over time. So considering the partitioning the time scale into j intervals which cut points 0 equal to tau naught less than tau 1 etc. less than tau j equal to infinity, the jth interval is defined as tau j minus 1 tau j ranging from j minus 1th boundary to the jth and including the former but not the later. So the baseline hazard is assumed to be constant within each interval. So lambda naught of t equal to lambda j for t in tau j minus 1 to tau j. Thus, we model the baseline hazard lambda naught of t using j parameters lambda 1 etc. lambda j, each representing the risk for the individual in one particular interval. Under the piecewise constant model, the baseline risk function takes the form lambda naught of t equal to j equal to 1 to j epsilon j into indicator function, and it uses the standard Gauss-Hermite quadrature rule for approximate integrals with respect to random effect. And in addition to that, we modified it and we used the pseudo-adaptive Gauss-Hermite rule as to estimate the piecewise constant baseline hazard. So it approximates the baseline hazard function using piecewise constant function and utilizes the pseudo-adaptive Gauss-Hermite quadrature rule, which is a numerical integration method for approximating definite integrals of a function with respect to probability distribution. So now coming to the real data, what I have discussed on colon cancer. For illustration, we have used a 343 patient of colon cancer registered in Regional Cancer Center, Thiruvananthapuram during the year 2016, and they were followed up till 2022. So a joint model approach was used to analyze this data. Pseudo-adaptive Gauss-Hermite rule was used as the baseline hazard function. The analysis was performed using JM package. The versatility of the JM package allows many versatile to fit the joint model, and hence we also use the joint frailty models. The longitudinal variable used was the carcinoembryogenic antigen CEA value, which is repeatedly measured over the time period of the follow-up. The covariates used were the age, sex, composite stage, perineurial invasion, lymphovascular emboli, obstruction, perforation, comorbidity, and family history of cancer. And this is the patient individual trajectories. The first one shows the trajectories of all the cases, and sorry, is it visible?
Visible, sir.
Yes, yes.
Yeah. And the second one shows the selective cases. Sorry, it is not moving, I think. Okay, I think it's visible now. So coming to the joint model, coming to the comparison here, we compared the joint model with the joint frailty model for all the variables. And we found that joint frailty model is giving better AAC and BAC values for all the variables. Irrespective of the variables, we are getting joint frailty as a better model. And we have the longitudinal submodels, that is for the linear, fitting the CEA values. And corresponding to that, all the factors has been assessed, and we got almost the similar coefficients for both joint model and joint frailty model. And coming to the hazard ratio or hazard rate for the survival submodel, we found that this alpha is the link function which shows that the C carcinogenic embryo values is highly correlated with the survival outcome. So this longitudinal joint model has a significant role in this study. And apart from that, the frailty model also shows that it is highly significant. And we can see that there is a change in the hazard with respect to joint model and joint frailty. And joint frailty is giving a better, has shown to be a better model. You can see that based on the composite stage 4 versus 1, you can see there is a overestimation in joint model, whereas it is totally reduced using a joint frailty model. That is, the effect of frailty has taken up that overestimation, and we can see those overestimation in most of the variables. And coming to the multivariate analysis, we have seen that again, joint frailty is performing better compared to that of joint model. And here the joint model for the longitudinal data, we can see that each of the covariate is found to be almost similar. Slight differences are there, but even it is comparable. And when it comes to the submodel, survival submodel, it can be shown that the overestimation is slightly reduced in a joint frailty model, and frailty has shown to be significant. And the longitudinal submodel which links, or the alpha which links between the longitudinal model and longitudinal survival submodel, also shown to be a significant factor. So based on this fitted joint model, we have made a projection or a prediction for this, and we can see that for the subject 4, the first line, the scatter plot shows the longitudinal trajectories or the longitudinal data of the CA value which is being used, and the composite stage is the only predictor variable, and based on that we predicted the survival, and we found that it is fitting pretty well. And for 4 subject has been randomly chosen and has been shown here. And to sum up, the dynamic version was observed among individual specific CA values. The longitudinal data was modeled separately using linear mixed model. I forgot to specify the model name. The linear mixed model was used here. And the terminal event was modeled using Cox proportional hazard with baseline hazard as piecewise constant, pseudo-adaptive Gauss-Hermite rule. 2 separate joint modeling approach was used for identifying the risk factors, namely joint model and joint frailty model for longitudinal and time to event data. Based on the information criteria, it was observed that frailty has a significant role in jointly predicting the risk for survival. Using the colon cancer patient data, it was observed that the longitudinally measured CA and the composite stage were joint predictors for the overall survival. The coefficient of the covariates corresponding to the longitudinal model showed that much significant difference between JM and joint frailty model. Both JM has showed the significance of link function and were found to be similar, indicating CA as a longitudinal predictor. The frailty parameter was also found to be highly significant, and hence most of the hazard rate were found to be different for both models. Slightly overestimation in hazard rate was observed for the model based on joint and compared to that of joint frailty model. The present study identified CA and composite stage as the significant prognostic factors for survival among colon cancer patients. The advantage of joint model is in the individual specific prediction. So once you have the joint model, for each patient we can predict what their survival will be, and whether the recurrence can happen. All those can be predicted. So based on the identified prognostic factors, the remaining lifetime of the patient can be predicted accurately. And that's all. Thank you.
Any questions from audience? No questions? Thank you, Jagannath Krishna sir, for giving lecture on cancer patients data. using modeling of heterogeneity. And next speaker is Suresh R from Bangalore University, Bangalore, India. He is speaking on the title Limiting Behavior of the SACF and PSACF in the Presence of a Large Seasonal Level Shift Outliers.
Yeah, sure. Hello, am I audible? Am I audible?
Yes, sir. Continue, sir.
Yeah, thank you, madam. Good evening, everyone. Before I start my talk, I would like to thank Professor C. Satish Kumar for the opportunity. Thank you, sir. Let me share the screen. Yeah, is it visible? Is the screen visible?
No, sir.
Not it.
Just a minute, sir. Share the screen. Window. Yeah, how about now, sir?
No, sir.
Hello?
Yeah, now it is fine. Now it is fine.
Okay, yeah. Yeah, shall I start, madam?
Yes, sir.
Okay.
Continue, sir.
Yeah, this the topic which I've chosen for today's talk is limiting behavior of the sample autocorrelation function and sample partial autocorrelation function in the presence of a large seasonal level shift outlier. This work is jointly carried out with my research scholar, Sri Vallabha. Yes. This is the outline of my talk. And the abstract, the presence of outliers in time series can strongly influence many statistics in time series analysis. So in the present study, we have explored the limiting behavior of the SSCF and SPSCF in the presence of a large level shift outlier. Henceforth, this seasonal level shift is abbreviated as SLS. We have found that due to the presence of a large-sized SLS outlier, the SASCF decays exponentially at seasonal lags, and the sample partial autocorrelation function shows the significant single significant spike at the first seasonal lag, irrespective of the data generating process. Introduction. Outliers. The existence of outliers can be attributed due to many reasons, like external or internal. Some of the instances are measurement errors, classification mistakes in sampling, or some non-repetitive exogenous interventions. And these can attributed. These can be seen as outliers. In economics and business time series, we sometimes they are subject to the influence of strikes, outbreak of wars, sudden change in the market structure of some group of commodities, technical change, or new equipment in a communication system, or simply unexpected pronounced changes in weather, etc. So these are some of the reasons for the existence of outliers in time series. The motivation for the present work. See, we know that in time series analysis, the sample autocorrelation function and the sample partial autocorrelation functions plays a vital role in the analysis part. Some of the main uses of it are in the identification of the model, and even in the estimation of the underlying parameters of the underlying model also, they have been extensively. We make use of this SSCF and PSCF. So effects of outliers and SSCF and SPSCF, review of literature, short review of literature. Studies which discusses the effects of outliers in time series analysis, especially on sample autocorrelation function, exist in the literature. Some of them are due to Chan, 1985, who have studied on the effect of the different types of outliers on SSCF. Further, Marona et al. In 2006 have discussed the effect of a patch of additive outliers on the first order SSCF of the series. And keeping Marona in the background, Suresh, myself, I have extended the results of Marona in 2006 to higher orders. And further, a different type of outliers called as doublet outlier. So I have considered doublet outlier and explored what is the impact of it on the sample autocorrelation function and the sample partial autocorrelation function. Before I get into the SSCF and SPSCF, I'd like to brief something about the the types of outliers what we come across in time series. For that, okay, first I need to let me define what do you mean by time series. So it is as given here in the slide, definition 2.1. And then outliers can take several forms in time series. Unlike in regression analysis, we have different types of outliers in time series. The formal definitions and the classification of outliers for the first very beginning first was proposed by Fox in 1972, and say in 1988, okay, he gave more information. He has discussed more about other types of outliers in time series context. When outliers or structural changes occur, this XT, which is a time series, we assume that the XT, as defined in equation 1, follows Box-Jenkins univariate model. In this case, the outlier can be modeled as yt is equal to f of t plus xt, where f of t is a parametric function representing the exogenous disturbance of xt. In practice, ft is specified by data analysts based on the subjective information of the substantial information of the disturbances and the process yt. It is assumed that ft is as given in expression 7, where in it of t, which is an indicator function, which is given as in 8. And this omega of t is a polynomial in B of degree S, and delta of B is another polynomial of order R. When it comes to the types of outliers, mainly there are 5 types of outliers: additive outlier, innovational outlier, transient change, level change, and variance change. These are all particular cases of this ft function, which is given in equation 7. When it comes to additive outlier, if in that expression 7, if delta naught is delta and this omega of b divided by delta of b is equal to 1, it turns out to be an additive outlier. And the definition for additive outlier is as given in equation 2. And the outlier model will be yt is equal to xt plus delta times it of t. And in the same expression 7, if delta naught is equal to delta and this ratio of omega of b divided by delta of b is equal to theta of b divided by phi of b, then it turns out to be an additive outlier, and the model appears to be as given in equation 10. And transient change, when it comes to transient change, delta naught will be delta, and this ratio of omega of b divided by delta of b will be 1 divided by 1 minus omega of b, where omega is the rate parameter, which will be exponentially decaying, and its value lies between 0 and 1. And the model will be as given in expression 11. And when it comes to level change, this delta naught will be delta, and the ratio of omega of b divided by delta of b will be equal to just 1 divided by 1 minus b. And the model will turn out or appears to be okay as given in equation 12. And now for the deterministic, see, whatever we have discussed in the previous these 4 types of outliers, we assume that f of t is deterministic, and it takes various forms, and accordingly we get the different types of outliers. But if in case ft is stochastic in nature, then it takes the form, you can assume, okay, it will be of this form as given in equation 13. And from this, okay, a new type of outlier can be derived, and that is called as variance change, wherein delta naught will be equal to delta, and omega, this ratio will be equal to theta of b divided by phi of b, and jt will be equal to EAT. And the variance change model will be as given in equation 14. Whatever outliers, those 5 outliers that was discussed previously, they do not take into consideration the seasonal models. So to bring in or to generalize the outliers, what Kaiser and Marvel did was they identified a new type of outliers which arise in seasonal time series, and such an outlier is called as they named it as seasonal level shift, SLS. And the seasonal level shift is as given in equation 15. And if there is an incidence of an outlier, say at time point n by 2, capital T, which is equal to n by 2, then the series will be affected as given in equation 13. So before the incidence of outliers, we don't see any effect of the outlier. Whereas after the incident, at each successive seasons, the effect can be seen. I mean, the effect of the seasonal level shift will going to impact, okay, at all the seasons subsequent to time point t, and rest of the other time points there is no effect. So this is how the seasonal level shift is going to affect the time series. Now, when it comes to the results pertaining to the effects of outliers and SSCF and SPSCF, as I discussed earlier, Chan, okay, he has discussed the effect of additive outlier, innovative outlier, seasonal level shift, and transient change, transient change, and that has been summarized in this table. So when there exists a large additive outlier, the kth order sample autocorrelation function tends to 0. And similarly, the incidence of a large IO will give you the partial, I mean, it gives you the theoretical kth order autocorrelation, whereas the existence of a large LO will give you the kth order sample autocorrelation function, which will be equal to 1 minus k by t minus 1, and transient change, this omega raised to the power of k. Now, along the lines of Chan, the effect of DO and SSCF has been addressed by Suresh in 2013, and these are the results pertaining to that work. The SSCF, the kth order SSCF will be equal to minus of in the presence of a large doublet outlier at the first order autocorrelation. At rest of the lags, it will be equal to 0. When it comes to the partial autocorrelation function, the kth order the limiting value of the sample partial autocorrelation function will be equal to minus 1 by k plus 1. So hence, it is clear that in the presence of a large doublet outlier, the SSCF is finite and cuts off after lag 1, and the SPSCF is decaying. Hence, when it comes to the identification of the model, it always suggests an moving average 1 model, irrespective of the data generating process, where now the identification has gone for the toss. It is under question. Similarly, Marona et al. We have worked on the patch of additive outliers. I've shown that the first order when the large patch of additive outliers, when the magnitude of additive outlier is very large, then the limiting value of the first order sample autocorrelation function is as given here. It will be equal to m minus 1 divided by m, where m denotes the number of additive outliers in the series. Further, the results which have been extended, the results of Marona et al. Which have been extended by me is given here. The higher order partial autocorrelations, the limiting value of the higher order partial autocorrelations will look like this. And when it comes to the sample partial autocorrelation function, the partial autocorrelation function is as given in this expression. So hence, we can conclude that from these two results, the results pertaining to SSCF and SPSCF in the presence of a patch of m large outliers. The SSCF is finite and cuts off after lag m minus 1, and the SSCF will decay. Hence, when it comes to the identification of the model, it always suggests a moving average model of order m minus 1. So keeping this the background, what we did was we wanted to explore what will be the effect of the seasonal level shift, a large seasonal level shift on the SSCF of the series. So that is what this slide sheds light on. We know that the mth order autocorrelation function is as given in the expression 7. When m is equal to 1, we do get the first order autocorrelation, and substituting the values for xt, for substituting by t in terms of xt, we get equation 19. So dividing the numerator and the denominator of above equation by delta square, we do get equation 20. And further simplifying this and taking limit as delta tends to infinity, where delta is the seasonal level shift outlier, we do get equation 22. It means that the first order autocorrelation will be equal to 0, irrespective of what its actual value is when there exists a large seasonal level shift. So when we extend this to higher orders, even the higher order, I mean the second order autocorrelation will also be equal to 0. So likewise, if we go on, we do get all the autocorrelations up to lag s-1, where s is the seasonality frequency, will be equal to 0. When it comes to the autocorrelation at a seasonal period, say yes, it will be given by equation 24. And due to the presence of a large outlier, we see that it turns out to be equal to k by 2 divided by k by 2 plus 1, where k denotes the number of years, complete years. Similarly, for m is equal to s plus 1, s plus 2, so on, 2s minus 1, the limiting value will be equal to 0. Now, if we explore this for the case of for the order where m is equal to 2 times s, means that is the second season, the limiting value will be as given in equation 28. So likewise, if we generalize the limiting behavior of the sample autocorrelation function in the presence of a large seasonal level shift outlier, it is as given in equation 29. It is clear that at the seasonal and non-seasonal lags or orders, the sample autocorrelation limiting value of the sample autocorrelation function will be equal to 0. Whereas at the seasonal lags or seasonal orders, it will be it will be equal to k by 2 minus L minus 1 divided by whole thing divided by k plus 1, k divided by k by 2 plus 1. That is what the result we have obtained. And similarly, working on the SPSCF, exploring the impact of the seasonal level shift, large seasonal level shift on the SPSCF. So for that, we consider the Darwin-Levinson algorithm, which is used to estimate the sample autocorrelation function. So these are the two equations along with this third one, which will be used to estimate the sample autocorrelation function given by Darwin and Levinson. Now, using the limiting value of that sample autocorrelation function that was obtained earlier, we plug in those values here in this expression and try to evaluate it for different values of m, where m is the order, and we proceed in that same manner. Okay, we do get this final result. This is what the result that has been obtained. So it is clear that at the non-seasonal orders, it will be equal to 0, and at m is equal to s, it will be equal to k by 2 divided by k divided by 2 plus 1, and the rest of the lags it will be as given here. Now, to gain more insight into this theoretical result, a simulation study was carried out. So design was as given here. It is we try to simulate an outlier-free time series with errors assumed that it follows IID normal 0,1 for illustrating the effect of a large side SLS on the SLF. An outlier-free time series of size n is equal to, say, n is equal to 120 is simulated for different values of the parameters, say phi and theta, and then an SLS outlier of large magnitude, say 500, is artificially inserted in the simulated series at time point, say t is equal to n by 2. The SSCF and the SPSCF of both the uncontaminated series and the contaminated series, which follows SAR1, SMA1, and SARMA1,1 are plotted respectively in the figures 1, 2, 3, 4, and 5, 6, 7, 8 respectively. And these are the SSCF and PSCF plot. The blue lines are the plot which has blue spikes. They are related to the SAR1 model without the outlier. The first panel tells you about the partial autocorrelation sample autocorrelation function, and the second panel, this one, tells this is the plot of the SPSCF. And it is clear and the second row in this graph is the SSCF plot, this one in the presence of a large outlier, and SPSCF, the corresponding SPSCF plot in the presence of a large outlier. It is clearly evident that the SSCF is decaying, and it has significant spikes at seasonal lags, and it is decaying exponentially. And we have one significant spike at lag, yes. Similarly, for other values of the underlying parameter of SAR1 model, we do have this, and the interpretation is almost the same. Now, when it comes to SMA1 model, this is the plot. So it is clear from this plot that irrespective of the data generating process, the SACF and the SPSCF, in the presence of a large seasonal level shift, okay, is very much same. There is no change in the pattern. Similarly, these plots are related to the SAR MA 1,1 model. So these are the conclusions. Some conclusions can be drawn from that graphs as well as from the theoretical result. So pertaining to SAR model, without SALS, the SACF should have exponentially decayed and should have patterns at lags S, 2S, 3S, depending on the sign of the autoregressive parameter. Whereas is a large outlier, the pattern, there is no change in the pattern. It is also it is behaving similar to that of when there is no outlier. When it comes to SMA1 model, we should have add a single spike, significant spike at lag S. Whereas due to the presence of a large level shift, seasonal level shift, it is exponentially decaying at lags S, 2S, 3S, etc. Similarly, for when it comes to SAR SARMA 1,1 model, this is how the actual pattern should have been. Whereas the presence of a large level shift shows that it is exponentially decaying at lags 2S, 2S, S, 2S, 3S, etc. And these are the conclusions pertaining to SPSCF. So there should have been a single significant spike at lag S without an outlier. And of course, there is no change when it comes to the presence of a large outlier. But when it comes to SMA1 model, the SPSCF should have exponentially decayed, whereas the presence of a single outlier, it has seen to that it has impacted the sample partial autocorrelation function, and we have just one spike at lag. Yes, same thing is true when it comes to SARMA 1,1 model. So these are the discussions that can be drawn from those conclusions and the theoretical result. The limiting behavior of SACF and SPSCF in the case of SLS, which have not been discussed so far, is a new effort in this work. To summarize, we have demonstrated that relying purely on SACF and SPSCF plots for model identification may not serve the purpose, since for any data, a large SLS seasonal level shift with large outlier appears to suggest an SAR1 model always. The role of SACF and SPSCF plots in the context of identification of the model in Box-Jenkins methodology is crucial for time series analysis. In the case of SLS, results in section 4 and 5 provide a caution when data is contaminated with the SLS of high magnitude. Theoretically, in the presence of a seasonal level shift of a large magnitude, it masks the true model for time series, thereby seriously jeopardizing the function of SACF and SPSCF as model identification tools. So the implications of this theoretical result are extensive for univariate time series analysis. These are some of the references that have been used for the current work. Okay, thank you. Hello?
Hello, sir.
Hello, thank you, madam.
Thank you,
Yes,
sir.
madam.
Questions from audience? No question? Okay. Third speaker of the today's session is
Sorry, madam. I would like to thank Satish Kumar. Thank you, Saraja madam, as well for chairing this session. And thanks for the opportunity, sir, Satish Kumar, sir. Thank you. Shall I stop sharing?
Thank you, sir. Dr. Suresh. Thank you.
Thank you, sir.
Thank you, sir.
Next member in the session is Lishmal Stomy.
Let me start the presentation. Hope the slides are visible.
Yes, visible.
Okay, thank you. As an introduction, statistical distributions play a vital role in data modeling. The present day situations, including spreading of epidemics like COVID-19, climate changes, etc., reveal the importance of statistical data modeling. As we all know, numerous distributions exist in statistical literature. Still, developing new probability distributions are encouraged due to the relevance of most appropriate fitting, which will lead to reduce the errors in data forecasting and further studies. In this talk, I would like to introduce a new distribution and discuss its applications in various fields. The work is titled as A New Trigonometric Distribution with Applications in Engineering, Climatology, and Ethology. This slide gives an overview of the contents of the presentation. It will introduce the new distribution. Its properties will be discussed, including the inferential analysis. Then real data analysis is done. Then conclusion and references. As I mentioned in the beginning, deriving new distribution is an evergreen area of statistics. Among them, trigonometric distributions are of recent interest. In the present work, a new trigonometric version of an existing distribution, namely modified Linley distribution, is introduced. Its utility is explained in terms of applications in fitting data from areas like engineering, climatology, and ethology. This slide lists out the importance of statistical studies in engineering ethology, the study of animal behavior, and climatology. By analyzing patterns, quantifying variability, and enhancing system performance, statistics in engineering data enables data-driven decision-making, process optimization, quality assurance, and risk assessment. Regarding ethology, statistics empowers ethologists to analyze and interpret animal behavior, deepening our understanding of its complexities and ecological significance. In climatology, statistics is used to analyze and interpret weather and climate data, identify trends and patterns, assess variability and extremes, and make predictions about future climate conditions. In the realization of the new distribution, we will be analyzing data from these three fields. Moving ahead, we may cite some existing distributions which form base for the new distributions. Bakoch et al. 2018, who developed a three-parameter distribution named the New Exponential Trigonometric Distribution. This distribution is considered an oscillatory generalization of the exponential distribution. Then the Cauchy-Linley distribution developed by Chesneau et al. 2023 is a remarkable weighted trigonometric distribution. And of course, the mentioned modified Linley distribution developed by Chesneau, myself, and Jiju in 2021, which forms the baseline of the newly deriving distribution. The importance of the new distribution is due to the oscillation and periodicity in the shapes of its PDF and HRF, which we will see as the talk progresses. The baseline distribution is modified Linley, and we will further show that the new distribution overcomes the modified Linley in terms of its modeling superiority for some data. This slide, in equation number 1, the probability density function of the weighted cos-modified Linley distribution is given. The PDF is actually derived by applying a weight function in terms of cos function to the modified Linley distribution. By using the series expansion of cosine function, an alternate form of the PDF is also given as equation number 2. The coming figures actually gives the shapes of the PDF with varying parametric values. Here, oscillatory behavior can be seen, whereas in this figure, for varying values of the parameters, oscillatory shapes with a non-monotonic tendency is seen. Then here, unimodal shape is also seen. So from these figures, observations about the shape of the new distribution is that the overall tendency of the curve seems to increase or decrease as alpha varies. As beta varies, the overall tendency of the PDF becomes more spread out with less visible signs of periodicity. And as theta increases, the shape of the PDF is visible with a peak, single mode, and no periodicity. For complex, we have obtained the closed form expression for the CDF. It is given in this slide. Then regarding the hazard rate function for different combinations of the parameters, the shapes are revealed in the coming figures, figure 2. In figure 2a, we can see the shapes for the HRF having a particular behavior. This is having another behavior, and this figure shows that in particular from figure A, with constant values of beta and theta and varying alpha, we can see periodicity in the shapes of the HRF. As alpha increases, it is more evident that the overall tendency of the HRF begins with lower probability values. Then with different values for beta, the overall tendency of the HRF begins with lower probability and shows periodic nature. With same values for alpha and beta, where we have seen the third figure, different values for theta, the overall tendency of the HRF displays prominent peaks, indicating that it can be bimodal or multimodal. Regarding the shape analysis, the tail behavior is also explored. Here, the parameters theta and alpha have significant effect on the initial values, but no effect on the infinite limit. As limit y tends to 0, the PDF takes values of the form theta square by 1 plus theta into 1 minus alpha. This depends on theta and alpha, but for limit y tends to infinity, it takes the value 0. Regarding the mode of the new distribution, we have obtained an expression by taking the equation as the first derivative of the PDF equal to 0. Then it is actually, this equation can be very complicated to solve because we can have a large number of modes. As observed graphically, our distribution can be exaggeratedly multimodal. We have given an equation to get the form of the mode. Moment analysis is also done. Here mu r dash, which is actually expectation of y raised to r, is the expression is given for the rth raw moment of the new random variable. Expressions for incomplete moments are also derived when only a portion of the data is available, or if it is challenging to compute complete moments. Such incomplete moments can be used as approximations of population moments. Regarding the inferential analysis, we develop the estimates of the parameters alpha, beta, and theta based on the maximum likelihood estimation method. Consider a random sample from the following the particular random distribution. Then the log likelihood is constructed here. And our aim is to maximize the log likelihood function with respect to the parameters alpha, beta, and theta. Of course, as you know, it is the theory of maximum likelihood estimation. To this aim, one can investigate the derivatives of the log likelihood function with respect to the parameters alpha, beta, and theta. These derivatives are obtained as follows. It is given in the equation dll by d alpha, dll by d beta, and dll by d theta. These derivatives are then equated to 0 to obtain the estimates of alpha, beta, and theta, respectively. These estimates cannot be obtained by solving the equations manually. Here we use the R software to compute their values. Now coming to the application part. We are considering data, real data from different areas. In the discussion and the introductory slides itself, I have mentioned that we are considering data sets from engineering, ethology, and climatology. Here, the first data set, which is collected from Patel et al. 1987, gives the positions of 68 snakes that were discovered while paddling. This is actually a data on animal migration, whereas the second data set is from engineering that refers to the time between failures for repairable items. It has been received from Murthy et al. 2004. Coming to the animal migration data sets, based on the data, the mean of the distance is obtained and the standard deviation is also measured. The corresponding skewness and kurtosis are also measured, stating that the shape of the data is positively skewed and mesokurtic, which we can see in the figure 3 also, the box plot. It shows that the data is positively skewed, and in the second part of the figure, figure 3b, the TTT plot for the animal migration data set is given. Here, the TTT plot of the data shows that it is nearly concave and mostly above the 45-degree line. It indicates the data is a distribution with the increasing HRF. This gives the interpretations of the box plot and the TTT plot we have seen. Now coming to the numerical analysis table, 1 gives the estimates and standard errors of the models for the animal migration data sets. The estimates are given. Actually here we are considering our distribution, the weighted cost modified linear distribution. It is compared with the 3 competing distributions, the NET distribution, then the cost linear distribution, and the exponential distribution, which seems to be competing with our distribution. The parameter values are the estimates of the parameters are obtained in all these 4 distributions. And the adequacy measures and the goodness of fit measures for this particular data sets are given by table 2. Here you can see that the p-values are also given in table 2. Here we can see that as we know, the distribution having the highest p-value and the lowest values for the goodness of fit measures and adequacy measures is considered as the best distribution for modeling. And here we can see that our new distribution, cost modified linear distribution, is superior in terms of these measures to the other 3 distributions we have considered. That is an explanation of the results in table 2. This WSTML distribution provides the highest p-value with least values for the AIC, BIC, AD, KS, and CVM statistics. These findings are supported with the illustration of EPDF and ECDF in figure 4A, and this is for A. The EPDF are given, and here the ECDF plots are given for the 4 distributions. Now coming to the second data, that is the failure data sets. Here also the mean and standard deviation is calculated, and the skewness and kurtosis measures are also obtained. From the box plot, the data is positively skewed data. Also from the numerical measure, it is positively skewed. Then TTT plot shows that the data has an increasing HRF. So for the numerical analysis, the estimates and their standard errors are obtained for the same 4 distributions, our new distribution and the competing other 3 distributions. The estimates are obtained in table 3. Then table 4, the adequacy measures and goodness of fit measures are given. Also p-values are given. From table 4, it can be observed that the NET distribution has the highest p-value, 0.9794, but the WCML, our new distribution, has a competitive p-value of 0.939738, where all the other measures are supporting our new distribution, the lowest AAC and BAC values compared to the other distributions. Then figure 6 provides a visual illustration in terms of EPDF and ECDF of the considered models, which supports the findings in table 4. Figure 6a, the EPDFs, and figure 6b, the ECDFs. Now coming to data from climatology, climatic data sets, we are considering two different data sets. Here the first one is a monthly precipitation data set, and the second one is monthly rainfall data sets. Details are displayed. For the precipitation data set, the mean, median, standard deviation, skewness, and kurtosis, their measures are also obtained and is given in table 5. The descriptive statistics is given in table 5. Then from the table, we are getting some ideas about the nature of the data set. That is, the data set is positively skewed and it is leptokurtic in nature. Figure 7 displays the box plot, which shows the positive skewness of the data, and the TTT plot shows that the data has an increasing HRF. So from figure 7, the conclusions that it is almost symmetric, but positive skewness, right side positive skewness is there, slight positive skewness, and increasing HRF is also for the data. Then for the analysis part, the estimates of the distribution, our new distribution WCML, then the Coase-Linley and exponential distribution estimates are given in table 6, and table 7 provides the numerical measures, the adequacy measures and the goodness of fit measures for the precipitation data set. From table 7, it can be observed that the WCML distribution has the highest p-value with the least values for adequacy measures and goodness of fit measures. Figure 8, the coming figure shows a visual representation in terms of EPDF and ECDF, which supports which depicts the support to our or the competing behavior of our the superiority of our new distribution. From climatology, the second data set is rainfall data set. Table 8 gives the descriptive statistics of the rainfall data sets, mean, median, standard deviation, then measures of moment measures of skewness and kurtosis are given. Then here also the box plot and the TTT plot exhibits the behavior of the data sets. This data is almost symmetric and it is having an increasing HRF. These are the interpretations of the two figures, box plot and the TTT plot. For this last data set, table 9 and table 10. This table 9 gives the estimates of the estimates and standard errors for the rainfall data sets for the different three distributions we have considered, we have compared. Table 10 gives the adequacy measures and the GO measures, the goodness of fit measures. Here also the new distribution, WCML distribution, has the highest p-value with the even though it is not that high. Comparing, it is having the highest p-value with the lowest values for the AAC, BAC, AD, and CVM statistics. From these results, we can conclude that the WCML distribution provides the better fit to the rainfall data set also. These figures, figure 10A gives the visual illustration that is based on EPDFs, and this is based on ECDFs. Concluding my talk, in this article, we developed a trigonometric weighted distribution by merging a trigonometric weight function with the functionalities of the modified Linley distribution. Actually, I have mentioned that this distribution is developed with the aid of a trigonometric weight function. So the goal of this weighing is to expand the modified Linley distribution's functional potential by including the oscillating behavior of the cosine function. The new distribution is improved in terms of applicability to actual data sets. We have seen that here the different properties of the new distribution are also explored, and basic functions associated with the distribution are also developed. Then in comparison with the new exponential trigonometric function, exponential and cos-linear models, the applicability of the proposed model to real-world data set is examined. The results of the comparison demonstrate that for some criteria, the suggested model is superior to the competing other three distributions. These are the references. This third one is the paper where a new modified linear distribution with the properties and applications are developed, and this distribution is actually the baseline distribution for our new distribution. These are the other references. Thank you.
Any questions from audience? Well presented, Vishnu's story.
Thank you so much.
Next speaker of today's session is L. Manju from Sri Gokulam Medical College and Research Foundation, Trivandrum, India. Topic is generalized logistic picture distributions. Manju, are you there?
Yes.
Okay, continue.
Yes, ma'am. Good evening, all. Today I am going to present a work on generalized logistic mixture distributions. So these are my contents: introduction, definition and properties, then location, scale, extension, testing of hypothesis, simulation, and conclusion. Logistic distribution was introduced in the 19th century for the description of growth of population and the course of autocatalytic chemical reactions of chain reactions. And it was named by the Belgian mathematician Verlast. The logistic distribution has been one of the most important statistical distributions because of its simplicity and also its historical importance as a growth curve. This distribution has several important biological applications, and in addition to this, it has applications in actuarial field and engineering field. The significance of this model in agricultural data was established by Schultz and Oliver. Logistic function and distribution have found several applications in various fields of public health, survival, and analysis. And detailed properties are available in biology. So a continuous random variable X is said to have standard logistic distribution if its probability density function is of the following form for X in R. F1 given by equation number 1. And the corresponding cumulative distribution function F1 of LD is given by this expression 2 for where X belongs to R. So Balakrishnan and Lang in 1988 proposed two generalized logistic distributions of type 1 in short LD1 and type 2 in short LD2 respectively through the following F2 and F3 where alpha and beta both more than 0. The corresponding CDF of LD1 and LD2 are respectively given by equation number 5 and 6. So if Z follows LD1, then minus Z follows LD2. And this LD1 is negatively skewed for alpha less than 1 and positively skewed for alpha more than 1. And LD2 is positively skewed for beta less than 1 and negatively skewed for beta greater than 1. And both these classes of distributions have applications in several areas of scientific research. Kumar and Manju 2017 developed a new logistic distribution, which is a mixture of these two distributions. In short, it is called as LMD through the following PDF number 7, where this P lies between 0 and 1 and both alpha and beta more than 0. So distribution with PDF 7 we denoted by LMD P alpha beta. So when P become 1, this LMD reduces to LD1, and when P becomes 0, LMD reduces to LD2. When either P equal to 1 and alpha equal to 1, or when P equal to 0 and beta equal to 1, LMD reduced to LD. And the CDF of LMD with PDF 7 is given by this expression number 8. And the characteristic function of LMD with PDF is given by the following expression number 9, where real part of 1 minus it greater than 0 and real part of beta minus it greater than 0 for t in a and I equal to square root of minus. And mean and variance of this LMD is given by these expressions 10 and 11, in which this psi is the psi or digamma function. Now coming to an extended version of LD1. So LD1 has several applications. So here we have introduced an extended form of LD1, that is type 1 generalized logistic distribution, and named it as generalized logistic mixture distribution, GLMD in short. So a continuous random variable X is said to follow GLMD if its CDF is of the following form. Third, where X belongs to R and sigma Pj equal to 1 and alpha j greater than 1. Corresponding PDF is given by equation number 30. So when G equal to 1, P1 equal to 1 and alpha equal to 1, this reduced to standard logistic distribution. And when J equal to 2, this reduced to logistic mixture distribution, LMD of Kumarman mentioned. And the probability plots of GLMD for particular choices of P and alpha are given by this following diagram. So from the diagram, we can see that for particular values of P and alpha, it takes a bimodal distribution, and for specific values, it can be negative skewed, and some specific values it can be positively skewed. So here, since we have used a series expression for this corresponding PDF, so using this Taylor series expansion and we substitute in this PDF, we got another expression for this PDF fx given by equation number 60. And the corresponding cumulative distribution function for this GLMD is given by this equation 16 for x greater than 0 and x less than or equal to 0. And the characteristic function is given by this equation number 70. At the nth raw moment of GLMD is given by this following expression for n equal to odd and when n equal to even. So from this we can obtain the mean and variance and different moments. Mean deviation is given by this following expression when mu less than or equal to 0. It is given by the expression number 20, and when greater than 0, it is given by equation number 21, where omega alpha j is denoted is Pj alpha j combination of minus alpha j minus 1 combination k. So these are some derivations of this. I am skipping this. And the Laplace transform is given by this expression. Fourier transform of this GLMD is given by this expression 32. And the median of this corresponding distribution is obtained by solving this equation. Similarly, mode we can obtain through this equation, solving this particular equation. Next, coming to the location scale extension. So we said follows GLMD with alpha P with PDF6, then x equal to mu plus sigma z is said to have extended LMD with parameters mu sigma p alpha. And the PDF is given by this expression number 35, where this mu naught alpha greater than 0 and the sigma pj equal to 1. So here I have used the maximum likelihood estimation method for obtaining the parameters of this extended form of GLMD, that is in short EGLMD. So the log likelihood function is given by equation number 36. On differentiating this with respect to this parameter mu sigma p alpha and getting 0, we have obtained the following likelihood equations 37, 38, 39, 40 and 41. So on solving this equation, we will get the maximal likelihood equation. Now for application purpose, we have considered a data set, which is a IQ data set of H7 white males. So this is a bimodal data set. So maximal likelihood estimators are obtained through the MaxLike packaging or software. And I have compared it with the logistic distribution, simple logistic distribution and logistic distribution of type 1, type 2, LMD, that is combination of LD1 and LD2 and EGLMD. And I have obtained the information criteria measures AAC, BAC, CAC and HQAC. So from this we can see that all these information criteria measures are minimum for this newly developed distribution. Next, for testing the parameters of this proposed distribution, we have done all these tests against H naught P1 equal to 0 versus P1 not equal to 0, P1 equal to 0, alpha 2 equal to 1 versus P1 not equal to 0, alpha 2 equal to 1, H naught 3 P1 equal to 0, alpha 2 equal to 1, alpha 3 equal to 1 versus P1 not equal to 0, alpha 2 not equal to 1, alpha 3 not equal to 1. Test for P1 equal to 0, P2 equal to 0, alpha 3 equal to 1 versus P1 not equal to 0, P2 not equal to 0, P3 not equal to 1 and H naught 5 alpha equal to 1, alpha 1 not 2 equal to 1, alpha 3 versus alpha 1 not equal to 1, alpha 2 not equal to 1, alpha 3 not equal to 1. So test statistics is given by this expression 42. So where omega is the maximum likelihood estimate of omega with no restriction and omega star is the maximum likelihood estimator when P1 equal to 0 in the case of test 1 and P1 equal to 0 alpha 2 in the case of test 2 and P1 equal to 0 alpha 1 alpha 3 equal to 1 in the case of test 3 and P1 equal to 0 P2 equal to 0 alpha 1 in the case of test 4 and alpha 1 alpha 2 alpha 3 equal to 1 in the case of test 2. Since the critical value and the significance level 0.05 and degrees of freedom 1, 2, 3 for the two-tailed test are 5.04 and 7.37 and 9.38 respectively, the null hypothesis is rejected. The following table shows the test statistic value. So test statistics is more than, so the null hypothesis is rejected to establish the existence of the parameters. Next, we have done a simulation study to assess the performance of the estimates of the parameters. We have conducted a deep simulation study based on the following two parameter sets. Here we have adopted the acceptance rejection method for generating the random numbers, is the EGLMD. So first we simulate X from the G, where G is the PDF, the type 1 logistic distribution, then simulate Y equal to U MGX, where U is the independent uniform random variable on 0, 1 and M is such that Fx by Gx less than M for all X. So accept X equal to Y less than X equal to X if Y less than Fx, if Y greater than Fx, go to step 2. So this is the acceptance rejection method adopted, and I have computed the absolute bias and mean square errors for different different sample size 30, 100, 200, 300. From this we can see that both the absolute bias and mean square error are in decreasing order as the sample size increases. So this is for data set 2. So the computed values bias and mean square error corresponding to sample size are given. From the table you can see that this absolute bias and mean square error in respect of each of the parameters are decreasing order as the sample size increases. So in conclusion, through this work, we have developed a new distribution, which is an extended version of type 1 logistic distribution, and named it as generalized logistic mixture distribution. Some important properties of the distribution is derived and compared with the existing for similar distributions with the help of dataset. And it was observed that distribution gave better fit compared to the already existing one. So these are some references I have used. Thank you.
Any questions? Okay.
Thank you, Sadish sir, for giving me this opportunity to present here. Thank you, sir.
Thank you, Satish Kumar sir and organizing team for giving me this opportunity.
Thank you, Madam Satyajam, Madam Professor Satyajam, Madam, for chairing the session. And thanks to all, let us give a big clap to all the speakers of the session. Dr. Jagannath Krishna, Dr. Sudesh, Dr. Dishamal Tommy, and Dr. Manju.
Thank you, sir. Thank you so much for this opportunity.
Yeah. Thus, we come to the conclusion of the. Let us conclude the conference, WSTA 2023 International Webinar or Conference. For the time being, let us move to the validatory function without wasting much time. I hope that one of the let me to wait for some 1 or 2 minutes only.
Satish sir, good evening, sir.
Hello, teacher. ഞാൻ വെയിറ്റ് ചെയ്യുന്നേ. ഓക്കെ, നമുക്ക് അങ്ങനെയാണെങ്കിൽ സ്റ്റാർട്ട് ചെയ്തേക്കാം. ജസ്റ്റ് കാര്യങ്ങൾ പറഞ്ഞേ. പ്രിൻസിനകത്തുണ്ടോ? ഹലോ പ്രിൻസ്. നിഖിൽ.
Hello.
Hello. Let us conclude the award. ആ സമയത്ത് ഡിസ്പ്ലേ ചെയ്യണം.
Okay.
That's why.
Okay.
Declare ചെയ്യുമ്പോൾ whenever we declare this that national quiz competition prizes.
Okay.
Winners, details of the winners. Okay, teacher, let us start.
Okay, sir. So, good evening, good afternoon, and good morning, everyone. So, we have reached the final part of our 8th international webinar on recent trends in statistical theory and applications 2023. Actually, it was a very fruitful journey, a very intellectual journey that all of us have taken together for the past few days, and finally we have reached a culmination point. So, this is actually a very short function. And first of all, I would like to invite Dr. Satish Kumar sir, the convener coordinator of the program, to please say a few words. Satish sir.
Yes. Good morning, good evening, and good afternoon, everybody. In fact, there are several sessions we have conducted through these 4 days of the international webinar of WSTA 2023, in which around 18 plenary talks and more than 80 invited talks, and there are several more than 80, so around 80 or 60, I think so. Contributory talks were conducted through these 4 days. I'm very much grateful to the professors, the stalwarts of our area of statistics, who have delivered talks through this international webinar. I utilize this occasion to extend our gratitude to each one of them. Not mentioning the name because there are several, and we are not interested to extend the validity function more time. By the time I would like to know whether there is anyone in the group who has to say their response, their feedback about the conference. We would like to know. Another thing, in this occasion, we would like to announce the national level, the winners, details of the winners of the national level Professor PC Mahalnobi's quiz competition, online quiz competition at the graduate level and the postgraduate level. I would like to extend our gratitude to each one of the members. I hope that Kalyanam sir is there in the group, isn't it?
Yes, sir. Yes.
Thank you, sir. Thank you, sir. Thank you so much for your blessings. And we have concluded this conference.
Due to age, unable to sit all through the sessions. I just attended.
Okay, sir.
So,
okay, sir.
Even though I was interested, I couldn't do that of late. Yes, thank you for everything.
Thank you, sir. Thank you.
Well, and continue to do this with more vigor. That's all.
Okay, sure, sir. With your blessings, blessings from sir, and like that, we shall try our best to continue our activities in future also. And in this occasion, I would like to invite each one of you to the December ICSTC conference, which we hope to conduct during 3rd week of December. We shall inform the details with regard to the conference in the meantime. Shall I invite Kalyanam sir? You just mention the winners of the national level quiz competition. Shall I, Nikhil, would you please WhatsApp that details to Kalyanam sir?
Okay.
So, you want me to say a few words?
Just the announcing the details of the winners of the national level quiz competition. We held it on 28th June.
So you have announced it?
Sir.
Yes.
Can you hear me, sir?
I can hear you, but
yeah. Please just to see your WhatsApp, sir, and in which we have sent details of the winners, the names of the winners.
Please.
Yeah, I have to announce the winners.
So I have to announce?
Yes.
Ramesh sir, actually, we have shared the details of the winners in your WhatsApp.
Right.
We have conducted the Professor PC Mahalnobi's Memorial National Level Quiz Competition.
Okay.
So the results are in your WhatsApp, sir. Kindly announce the winner.
Yes.
Yeah.
Yes.
Okay, sir. Please announce the winner, sir.
Okay, right. Professor, I'm very happy that I'm having this opportunity to announce the results of Professor P.C. Mahalanobis Memorial National Level Online Quiz Competition 2023. The winners, undergraduate level, Miss, see, of late, eyes are going down, ears are going down.
Okay, they will display, sir, Professor.
NC Das, St. Xavier's College, Autonomous, Calcutta. And Sri Sanjot Sunil Shir Sagar, R.A. Poda College of Commerce and Economics, Mumbai. And Mr. Raunak De, Acharya Prafulla Chandra College, Kolkata. And Miss Kargi Shakal Kar, Ramnarayan Ruya College, Mumbai. And Miss Sahila E, Farooq College, Autonomous, Kerala. Mr. Vallabhapuram Shekhar, YSR Horticultural University, Horticulture, Manasali, Venkata Ramana Mangalam. Miss Devanshi Vanastali Vidyapit, Rajasthan. And Mr. Aditya Manoj Vadekar, R.A. Podar College, Commerce and Economics, Mumbai. And Miss Chaitrali Dalvi, R.A. Podar College of Commerce, Economics, Mumbai. And Mr. Pavan Hemraj Sabkhale, MJ College, Jalgaon. Miss Shada Nahar, Farooq College, Autonomous, Kerala. So I congratulate all of them at the undergraduate level. I move on to the postgraduate level. Miss Pinal Agarwal, Dayanchand Anglo-Vedic College, Kanpur. Miss Vidyanjali V.A., University of Kerala, India. Miss Yadav Pranali Tanaji, Shivaji University, Kolhapur. Then Miss Alina Thomas, St. Thomas College, Palai. Miss Dilpriya D.A., University of Kerala, India. Miss Josna Jos, St. Thomas College, Palai. And over 1,000 candidates from all over India took part in the competition for testing their knowledge. Congratulations to all the participants as well as the winners. So it's a great effort, and in fact, openly I say, I never expected that the department will be doing things at this level, and you have been doing it wonderfully well. And all the winners, I say that these certificates are not ordinary certificates. Certificates are coming from an institution where people work day and night together throughout the year to continue to provide information on statistics and make you all better in your subject. So I congratulate both participants and the organizer and all the winners once again, and continue to, I pray for the continuous success of your efforts in the field of statistics to come. And thank you all for that. Yes.
Thank you so much, sir. Thank you.
Thank you, sir, for your kind words and wishes, and congratulations to all winners. So, Sadiq sir, shall we ask some of the participants to say a few words, their feedback, opinions?
If there is anyone, one or two is enough.
Okay. So we request one or two of the participants at least to say a few words regarding the program. Are the winners of the quiz program here in the meet?
Probably we have not. In fact, we have announced the validity function little bit late.
Yes, true.
Yeah, we have since we are not interested to waste our time, we can find that. That's right.
Yeah. Okay, sir.
So probably we can send the details to them.
Okay,
individually.
Sure, sir.
If there is no one, please, teacher, please can conclude the.
Okay, so as we are sure that all the participants of this webinar series or this on, Riyaz, please say.
Manoharan sir is now joined. Manoharan sir.
Manoharan sir. Hello, Manoharan sir. Good evening.
Good evening. Good evening.
Good evening, sir.
Yeah. Please share your one or two words.
Oh, sure.
Please share.
It was a wonderful gathering, really. We enjoyed all the 4 days. I couldn't attend all the sessions, but at times, whenever I was free, and I made it a point to attend many of the sessions. In fact, it is a real hard work behind this 4 days arrangement. I'm very thankful to Professor Satish Kumar and his team. I know that it's a very tedious and very laborious work, watching all the 4 days and taking care of each and every session. Whenever there is some network issue, he was trying his level best to present from his own part, and that way it was a wonderful meeting. And I thank the Department of Statistics, Kerala University, and in particular Professor Satish Kumar and his team, and also KSA and also Indian Society for Probability and Statistics for supporting this event in a big way. Hearty greetings to everyone, and thanks.
Thank you, sir.
Thank you.
So some of the participants, they are posting their responses and feedbacks in the message box.
Okay, chat box.
Yeah, in the chat box. Thank you, dear, for your valuable feedback, because we appreciate your feedback and your opinion, and we really hope that all of you will be a part of our journey in the future also. So Satish sir, shall we wind up the program?
It's okay, teacher. It's okay. Once again, thanking you all. Let us say good night. Thanks. We are always grateful to you, each one of you, the participants, professors, and my teachers, and all of you. Let us meet in the next time, and let us try our best to arrange the academic events for the benefit of the youngsters and for the future generation. Let us try our best.
Yeah.
Thank you.
Just a few words of formal gratitude to all of you. Actually, these 4 days was 4 days of great importance to our department. And on behalf of the Department of Statistics, on behalf of Dr. Satish Kumar sir and his team members and the University of Kerala, we would like to express our sincere gratitude to all the dear professors, to all the participants, the plenary speakers, the invited speakers, the contributory speakers, the students, the nearly 1,000 students who participated in the quiz competitions. We express our sincere, heartfelt gratitude to each one of you for your cooperation, and because your cooperation is our motivation, and the support that you have given us all through these years, and the energy, the synergy with which each and every one of you took part in all our events is actually the real motivation. And personally, from the statistical fraternity, we would like to thank you, dear Satish Kumar sir, for the effort that you put in, for the leadership that you show, and the guideship that you give us in organizing these programs. Actually, the opportunity given to us students is beyond words, because we get the opportunity to meet with international fraternity of statistics, to know the research, the latest research that is going around in the globe. And that is a great opportunity. And we have to thank you on behalf of all of us for that effort that you put in each and every session, every day, for each and every program that you coordinate. So once again, thanks from our hearts to all those who participated in the event. We really hope that each and every one of you will be with us in the international conference that we will be arranging in December also. That will be in the offline mode, hopefully. And we hope that you will be present in person to make that program also a great success. So thanking you again once from our hearts. Good night, and wish you a great night.
Thank you so much.
Yeah, good night. Good night, everyone. Thanks.
Good night. Good night. Bye.